streaming. So I'm gonna just read a bunch of stuff today and then maybe look at the code depending on how long I spend reading stuff. I found a new one. I think I had an account on this one, so I knew about it, but for some reason I used the other one, the text-to-speech thing. And this one seems to be a lot better because I can go a lot faster. So I'm gonna be reading this stuff about data availability sampling, dank sharding, and the yellow paper and the Casper documents. So I'm gonna switch the thing here and just read. And also, I think I'm gonna start with this Lagrange polynomial thing because it is used on the data availability sampling. So yeah.
Lagrange polynomial. In numerical analysis, the Lagrange interpolating polynomial is the unique polynomial of lowest degree that interpolates a given set of data, given a data set of coordinate pairs, with 0, less than or equal to, the, are called nodes and the, are called values. The Lagrange polynomial has degree, less than or equal to, and assumes each value at the corresponding node, equals. Although named after Joseph Louis Lagrange, who published it in 1795, the method was first discovered in 1779 by Edward Waring. It is also an easy consequence of a formula published in 1783 by Leonard Euler II. Uses of Lagrange polynomials include the Newton-Cotes method of numerical integration and Shamir's secret sharing scheme in cryptography. For equispaced nodes, Lagrange interpolation is susceptible to Runge's phenomenon of large oscillation. Definition edit. Given a set of plus 1 nodes, 0, 1, which must all be distinct, is not equal to, for indices, is not equal to, the Lagrange basis for polynomials of degree, less than or equal to, for those nodes is the set of polynomials, 0, 1, each of degree, which take values, equals, 0, if, is not equal to, and, equals, 1. Using the Kronecker delta this can be written, equals, each basis polynomial can be explicitly described by the product. Notice that the numerator, pi, is not equal to, has, roots at the nodes, is not equal to, while the denominator, pi, is not equal to, scales the resulting polynomial so that, equals, the Lagrange interpolating polynomial for those nodes through the course. We wish to interpolate, equals, 2, over the domain, 1, less than or equal to, 3, at the three nodes, 1, 2, 3. The node polynomial is. The barycentric weights are. The Lagrange basis polynomials are. The Lagrange interpolating polynomial is. In second, barycentric form. Notes edit. The Lagrange form of the interpolation polynomial shows the linear character of polynomial interpolation and the uniqueness of the interpolation polynomial. Therefore, it is preferred in proofs and theoretical arguments. Uniqueness can also be seen from the invertibility of the Vandermonde matrix, due to the non-vanishing of the Vandermonde determinant. But, as can be seen from the construction, each time a node xk changes, all Lagrange basis polynomials have to be recalculated. A better form of the interpolation polynomial for practical, or computational, purposes is the barycentric form of the Lagrange interpolation, see below, or Newton polynomial. Lagrange and other interpolation at equally spaced points, as in the example above, yield a polynomial oscillating above and below the true function. This behavior tends to grow with the number of points, leading to a divergence known as Runge's phenomenon. The problem may be eliminated by choosing interpolation points at Chebyshev nodes for. The Lagrange basis polynomials can be used in numerical integration to derive the Newton-Cotes formulas. Remainder in Lagrange interpolation formula edit. When interpolating a given function f by a polynomial of degree k at the nodes 0, we get the remainder, equals, which can be expressed as 5. Where 0 is the notation for divided differences. Alternatively, the remainder can be expressed as a contour integral in complex domain at. The remainder can be bound as, clearly, is 0 at nodes. To find, at a point, define a new function, equals, and choose, equals, pi, equals, 0, where is the constant we are required to determine for a given. We choose, so that, has, plus, 2, zeros, at all nodes and, between, 0, and, including and, An explanation of the sharding plus DOS proposal. Along with proof of stake, the other central feature in the Eth2 design is sharding. This proposal introduces a limited form of sharding, called data sharding. As per the roll-up-centric roadmap, the shards would store data and attest to the availability of 250 KB-sized blobs of data. This availability verification provides a secure and high-throughput data layer for layer 2 protocols such as rollups. To verify the availability of high volumes of data without requiring any single node to personally download all of the data, two techniques are stacked on top of each other: I, attestation by randomly sampled committees, and 2, data availability sampling, DOS. Eli 5, randomly sampled committees. Suppose you have a big amount of data, think 16 megabytes, the average amount that the Eth2 chain will actually process per slot, at least initially. You represent this data as 64 blobs of 256 KB each. You have a proof of stake system with 6,400 validators. How do you check all of the data without I, requiring anyone to download the whole thing, or 2, opening the door for an attacker who controls only a few validators to sneak an invalid block through? We can solve the first problem by splitting up the work. Validators 1, 100 have to download and check the first blob. Validators 101, 200 have to download and check the second blob, and so on. The validators in each of these subgroups, or committees, simply make a signature attesting that they have verified the blob, and the network as a whole only accepts the blob if they have seen signatures from the majority of the corresponding commit. But this leads to a problem. What if the attacker controls some contiguous subset of validators, e.g. 1971, 2070? If this were the case, then even though the attacker controls only 1.5% of the whole validator set, they would dominate a single committee. In this case, they would have 70% of committee 20, containing validators 2001, 2100, and so they would be able to control the committee and push even invalid/unavailable blobs into the Random sampling solves this by using a random shuffling algorithm to select the committees. We use some hash as the seed of a random number generator, which we then use to randomly shuffle the list 1, 6400. The first 100 values in the shuffled list are the first committee, the next 100 are the second committee, etc. The RNG seed is chosen after validators deposit and each validator's index is fixed, so the attacker has no way to try to put all their validators into a single committee. They may get lucky once in a while by random chance, but only if they control a very large fraction, 1/3, of all validators. Eli 5, data availability sampling. Data availability sampling is in some ways a mirror image of randomly sampled committees. There is still sampling going on, in that each node only ends up downloading a small portion of the total data, but the sampling is done client-side, and within each blob rather than between blob. Each node, including client nodes that are not participating in staking, checks every blob, but instead of downloading the whole blob, they privately select n random indices in the blob, each n equals 20, and attempt to download the data at just those positions. The goal of this task is to verify that at least half of the data in each blob is available. If less than half of the data is available, then it is almost certain that at least one of the indices that any given client samples will not be available, and so the client will reject the blob. Note that this mechanism is efficient, as a client only needs to download a small portion of each blob to verify its availability, and also 2, highly secure, as even a 51% attacker cannot trick a client into accepting unavailable blob. To cover the case that an attacker makes available 50 to 99% of the data, which can easily lead to some clients accepting and other clients rejecting the blob at first, we use a technology called erasure code. Erasure coding allows us to encode blobs in such a way that if at least half of the data in a blob is published, anyone in the network can reconstruct and republish the rest of the data. Once that republished data propagates, the clients that initially rejected the blob will converge to accept it. Note, there is no time limit to accepting a blob. A client accepts a blob as available whenever it has received responses to all of its sample indices. The simplest mathematical analogy to understand erasure coding is the idea that 2 points are always enough to recover a line. If I construct the file consisting of 4 points, 1, 4, 2, 7, 3, 10, 4, 13, all of which are on one line, then if you have any 2 of those points, you can reconstruct the line and compute the remaining 2 points. We assume the x-coordinates 1, 2, 3, 4 are a fixed parameter of the system, not the file creator's choice. With higher degree polynomials, we can extend this idea to create 3 of 6 files, 4 of 8 files, and generally n of 2 n files for any arbitrary n, with the property that if you have any endpoints of the file, you can compute the remaining ones out of 2 n which are missing. It is also possible that an attacker by default makes none of the block available, and only selectively publishes chunks in response to sample queries that it sees, but this would only fool a small number of clients before the attacker would need to publish more than half the block to answer all the queries. We assume clients publicly rebroadcast all responses they receive. We use polynomial commitments, specifically, k commitments, instead of Merkle roots as pointers to these data blobs, because polynomial commitments let us easily prove that a given value actually is the correct evaluation of a particular degree and polynomial at the desired coordinate. Otherwise, we would have to either prove, using SNARKs, for example, that a Merkle root encodes a low-degree polynomial, the likely eventual solution once we need something post-quantum, but too expensive for now, or rely on fraud proofs which can be broadcast in case of incorrect encoding, adding high complexity and more synchronicity assumptions. Why not use just committees and not DOS? Using only committees has the following weaknesses. Weaker protection in case of an actual 51% attack. In current, non-scalable blockchains, a 51% attack can only revert transactions or censor. It cannot push through invalid block. A committee-based system would remove this guarantee. Furthermore, it would be very difficult to effectively penalize a 51% attacker, as only a very small portion of their deposits, the deposits that participated in that particular committee, would be provably implicated in the malicious behavior and could conceivably be penalized. Requires a specific threshold. What percentage of a committee needs to approve a blob for the chain to accept it? If the threshold is low, or is some dynamic mechanism, if that threshold is high, then the sharding functionality shuts down entirely in periods where few validators are online. If the threshold is low, or is some dynamic mechanism like a threshold share only of recently online validators, then an attacker can try to knock many nodes offline to increase their share of the remaining online nodes and push a bad blob through. DOS is slightly easier to make quantum proof than committees, which would require post-quantum aggregate signatures. Why not just use DOS and not committee? Using only DOS has the following weaknesses. DOS is a new and untested technology, with key components, e.g. this, having literally been developed in the last year, so having committees as a backstop seems wise, in case DOS breaks or takes an unexpectedly long time to develop. DOS has higher latency than committee. DOS has more edge cases, which committees can help plug. One particular example is that in a DOS-only system, it's difficult to avoid the beacon block proposer being one of the first actors to make DOS queries to verify blob availability. This creates heightened risk that an attacker will publish unavailable blobs and release responses only to the proposer's queries. This will not cause the rest of the network to accept the unavailable blobs, but it may lead to easy attacks with the goal of causing beacon blocks constructed by honest proposers to be rejected and fork away from the canonical. Committees can remedy this. Committees are more forward compatible with future edition of in-shard execution. Why is data availability important and why is it hard to solve? This has been discussed at length in other materials too long to copy here. I recommend a note on data availability and erasure coding, the original introduction to the data availability problem. The paper by Alberto Sunino, Mustafa Al-Bassam, and Vitalik Buterin expanding on these concepts. The dawn of hybrid layer 2 protocols, exploring the game theory of data availability. Base layers in functionality escape velocity, specifically the section on data scalability expanding on the above ideas. The data availability problem, Ethereum Silicon Valley meetup, much of the same content in video. A key takeaway is that BitTorrent, IPFS and similar systems do not solve data availability. While BitTorrent is a good scalable data publishing source, it does not provide a guarantee of consensus about whether or not a piece of data is available, leaving open the possibility of inextricable edge case attacks where nodes disagree on when a piece of data was published, preventing hybrid layer 2 protocols from working. To achieve consensus on data availability, the stronger techniques described in this document are required. How does sharding work on the P2P layer? In order to achieve the scalability gains of sharding, we need a P2P system that avoids the need for every node to download all the data. Fortunately, we have a form of P2P layer sharding already live in phase 0. Specifically, there are 64 subnets that are being used for aggregation of attestation. Each validator need only be on I, the main, global subnet, and 2, their own attestation aggregation subnet. They do not receive any data from the other 63 attestation aggregation subnet. In committee plus DOS sharding, we expand this out to a grid structure, with 2048 horizontal subnets, one for each shard, slot, parent and epoch, and 2048 vertical subnets, one for each index within a blob. During each slot, we select a proposer for each shard. Each proposer is entitled to propose a blob, a lump of arbitrary data of size up to 512 KB, which we interpret as a collection of samples of 512 bytes each, along with the erasure code extension as well as extra proofs to allow each part of the blob to be independently verified. Structure of a blob. The full body of a blob consists of the original data, the extended data, and the proofs, though if desired, for data efficiency the extended data can be left out as it is relatively fast for each node receiving the blob to reconstruct it. The header of a blob is the kate commitment to the blob, plus a bit of other miscellaneous data, slot, shard, length proof, and a signature from the proposed blob publication process. When a blob is published, the header is published on the global subnet, and the blob is published on the horizontal subnet corresponding to the slot number and shard I for each 3 and 0. Samples _per_ block 1. The ITH sample is published on vertical subnet 3, along with the proof that the ITH sample actually is the evaluation of the polynomial committed to in the header at the ITHX coordinate. In practice, there would be 2048 horizontal subnets, to allow one horizontal subnet per shard, slot, combo in each epoch. This is done to ensure that each validator can join a single horizontal subnet where they will only receive the blob corresponding to the committee that they were assigned to, in addition to the small number of vertical subnets they join to participate in sampling. Each validator must join the following subnets. The global subnet. The horizontal subnet corresponding to the shard, slot, combo, i.e. the committee, that they were assigned to. The vertical subnets corresponding to indices that they are assigned to. Each validator computes this for themselves using a private seed. There is a procedure by which a blob proposer can broadcasting blocks. There is a procedure by which a blob proposer can distribute the samples to all subnets without the proposer being part of the subnets themselves. This procedure is as follows. Publication. The proposer publishes the blob, along with a proof for each sample, on the appropriate horizontal subnet. Direct sample distribution. The other participants on the horizontal subnet publish the chunks to each vertical subnet that they personally are. Indirect sample distribution. Proposers reveal a few, 4, of the vertical subnets they are on to their peers. Hence, each participant in the horizontal subnet can also look at the vertical subnets that their peers are on, and broadcast the appropriate chunks to those peers. For example, if the chunk size is 512 bytes, and the maximum data blob size, without erasure code expansion, is 512 KB, then with erasure code expansion it's 1 megabyte. So there would be 2048 vertical subnet. If each node has 15 private vertical subnets and 5 public vertical subnets, and 50 peers, and assuming a worst case scenario where there are 128 members in each horizontal subnet, just the committee, then the subnet members alone would directly publish to 128 * 20 equals 2560 subnets, 1461 after taking into account redundant publishing, and including peers this would increase to 128 * 4 * 50 equals 25,600 subnets, all 2048 subnets 99.2% of the time after taking into account redundant publishing. Note that it is theoretically possible for a malicious block proposer to publish samples to the vertical subnets without publishing the full block. To cover this case, we add a procedure by which a partially published, meaning equals 50% available but not 100% available, block can be self-healed. The self-healing procedure has 3 basic steps. Reverse distribute, a procedure identical to the distribution procedure above is used, except that in this case peers on a vertical subnet propagate samples from that vertical subnet to the horizontal subnet corresponding to the blob that the sample is a part of. Reconstruct, if there are equals 1024 samples on the horizontal subnet, or generally, half of the sample count, anyone can reconstruct the full blob, and publish the reconstructed blob to the horizontal subnet. Distribute, the distribution procedure above is repeated. How does the beacon chain work? In each slot, we randomly select a proposer for each of the 64 shard. The proposer has the right to create a shard blob, and broadcast it using the procedure above, as well as broadcasting the shard header of the blob to the global subnet. The shard header can be included in the beacon chain in that slot or any subsequent slot in the same or next epoch. The beacon chain keeps track of a list of pending shard header object. A pending shard header stores I, the key information in a shard header, the shard in slot, a commitment to the blob, and its length, and 2, a bit field keeping track of which validator is out of a randomly selected committee. In fact, the same committees is already introduced in phase 0, signed off on the blob. The attestation data struct is expanded to include a shard _header _root, a root hash of the shard header that the given attester is voting for. Attesters can also vote for an empty root if they see no valid and available shard blob for the shard, slot, pair they have been assigned to. If a shard header gets the support of 2/3 of the committee, it is confirmed immediately. If a shard header has the support of a larger share of the committee than any other shard header, including the default empty one, at the end of the next epoch, then it is confirmed at the end of that epoch. Fork choice rule. The fork choice rule is changed so that a block is only eligible for consideration if all blobs confirmed in that block or its ancestors have passed an availability check. This is called tight coupling. If a chain points to, meaning, has confirmed, even a single invalid blob, the whole chain is considered invalid. This is a key difference from sidechain architectures, where it's possible for a sidechain to fail while the central chain remains valid. See here for a further exploration of tight coupling and why it's valuable. The low validator count case. If there are less than 262,144 validators, 32 slots * 64 shards * 128 minimum committee size, then instead of selecting a proposer for all shards, we select a proposer for a limited subset of shards, cycling through the shards. If there were 32 * 128 * 50 validators, and its slot n the start shard was 0, then slot n will assign a proposer for shards 0, 49, slot n plus 1 will assign a proposer for shards 50, 63 and 0, 35, slot n plus 2 will assign a proposer for shards 36, 63 and 0, 21, etc. This is done to ensure that committee sizes remain sufficient even under conditions of low participation. Gas prices for shard data. An EIP 1559-like mechanism is added by which shard data is charged for per byte, and this price is adjusted. If blocks are on average more than 50% full, it is increased, and if blocks are on average less than 50% full, it is decreased. Hence, an average block size of 50% is targeted. Security assumptions. The data blob-only sharding design is powerful because it is surprisingly light on security assumptions compared to other sharding schemes. In particular, it avoids both honest majority assumptions, as DOS can detect unavailable blobs pushed by a majority, and timing assumptions, as unlike earlier DOS schemes, this scheme uses kate commitments instead of fraud proofs, and so does not rely on any assumption that fraud proofs will be broadcasted quickly enough. A malicious 51% coalition can censor blobs, but 51% censorship is possible in non-sharded chains as well. The main new assumption that is added is the honest minority DOS assumption that there are enough nodes sampling that an attacker cannot satisfy them without publishing more than half the blob. If there are 2048 samples in a blob, with 1024 needed to recover, 2048 *ln 2 equals 1419, taking into account that some clients will sample the same points, and each client takes 20 samples, then the system is secure if more than 70 clients are sampling each shard. Forward compatibility. The data blob only sharding design is forward compatible with many approaches for adding execution in shards if this is later desired. In particular, the scheme could be modified to require blobs to include a pre-state and post-state root, and we could use either fraud proofs or ZK snarks to verify that the state transition in a blob is correct. Note that in either option, ensuring correctness of execution in shards would not depend on any honest majority assumption. Enjoy. 8. Other resources. Proto Lambda is work in progress implementation. Dark mode toggle. The dawn of hybrid layer 2 protocols. 2019 August 28th. See all posts. Special thanks to the Plasma Group team for review and feedback. Current approaches to layer 2 scaling, basically, Plasma and state channels, are increasingly moving from theory to practice, but at the same time it is becoming easier to see the inherent challenges in treating these techniques as a fully fledged scaling solution for Ethereum. Ethereum was arguably successful in large part because of its very easy developer experience. You write a program, publish the program, and anyone can interact with it. Designing a state channel or Plasma application, on the other hand, relies on a lot of explicit reasoning about incentives and application-specific development complexity. State channels work well for specific use cases such as repeated payments between the same two parties in two-player games, as successfully implemented in Sealer, but more generalized usage is proving challenging. Plasma, particularly Plasma Cash, can work well for payments, but generalization similarly incurs challenges. Even implementing a decentralized exchange requires clients to store much more history data, and generalizing to Ethereum-style smart contracts on Plasma seems extremely difficult. But at the same time, there is a resurgence of a forgotten category of semi-layer 2 protocols, a category which promises less extreme gains in scaling, but with the benefit of much easier generalization and more favorable security model. A long-forgotten blog post from 2014 introduced the idea of shadow chains, an architecture where block data is published on-chain, but blocks are not verified by default. Rather, blocks are tentatively accepted, and only finalized after some period of time, e.g. 2 weeks. During those 2 weeks, a tentatively accepted block can be challenged. Only then is the block verified, and if the block proves to be invalid, then the chain from that block on is reverted, and the original publisher's deposit is penalized. The contract does not keep track of the full state of the system. It only keeps track of the state root, and users themselves can calculate the state by processing the data submitted to the chain from start to head. A more recent proposal, ZK Rollup, does the same thing without challenge periods, by using ZK snarks to verify blocks' validity. Anatomy of a ZK rollup package that is published on-chain. Hundreds of internal transactions that affect the state, i.e. account balances, of the ZK rollup system are compressed into a package that contains 10 bytes per internal transaction that specifies the state transitions, plus a 100-300 bytes NARC proving that the transitions are all valid. In both cases, the main chain is used to verify data availability, but does not, directly, verify block validity or perform any significant computation, unless challenges are made. This technique is thus not a jaw-droppingly huge scalability gain, because the on-chain data overhead eventually presents a bottleneck, but it is nevertheless a very significant one. Data is cheaper than computation, and there are ways to compress transaction data very significantly, particularly because the great majority of data in a transaction is the signature and many signatures can be compressed into one through many forms of aggregate. ZK rollup promises 500 TX/SEC, a 30x gain over the Ethereum chain itself, by compressing each transaction to a mere 10 bytes. Signatures do not need to be included because their validity is verified by the zero-knowledge proof. With BLS aggregate signatures, a similar throughput can be achieved in shadow chains, more recently called optimistic rollup, to highlight its similarities to ZK rollup. The upcoming Istanbul hard fork will reduce the gas cost of data from 68 per byte to 16 per byte, increasing the throughput of these techniques by another 4x, that's over 2,000 transactions per second. So what is the benefit of data on-chain techniques such as ZK/optimistic rollup versus data off-chain techniques such as Plasma? First of all, there is no need for semi-trusted operator. In ZK rollup, because validity is verified by cryptographic proofs, there is literally no way for a package submitter to be malicious. Depending on the setup, a malicious submitter may cause the system to halt for a few seconds, but this is the most harm that can be done. In optimistic rollup, a malicious submitter can publish a bad block, but the next submitter will immediately challenge that block before publishing their. In both ZK and optimistic rollup, enough data is published on-chain to allow anyone to compute the complete internal state, simply by processing all of the submitted deltas in order, and there is no data withholding attack that can take this property away. Hence, becoming an operator can be fully permissionless. All that is needed is a security deposit, e.g. 10eth, for anti-spam purposes. Second, optimistic rollup particularly is vastly easier to generalize. The state transition function in an optimistic rollup system can be literally anything that can be computed within the gas limit of a single block, including the Merkle branches providing the parts of the state needed to verify the transition. ZK rollup is theoretically generalizable in the same way, though in practice making ZK-SNARKs over general-purpose computation, such as EVM execution, is very difficult, at least for now. Third, optimistic rollup is much easier to build clients for, as there is less need for second-layer net. ZK rollup is theoretically generalizable in the same way, though in practice making ZK-SNARKs over general-purpose computation, such as EVM execution, is very difficult, at least for now. Third, optimistic rollup is much easier to build clients for, as there is less need for second-layer networking infrastructure. More can be done by just scanning the blockchain. But where do these advantages come from? The answer lies in a highly technical issue known as the data availability problem. See note, video. Basically, there are two ways to try to cheat in a layer 2 system. The first is to publish invalid data to the blockchain. The second is to not publish data at all, e.g. in Plasma, publishing the root hash of a new Plasma block to the main chain but without revealing the contents of the block to anyone. Published but invalid data is very easy to deal with, because once the data is published on-chain there are multiple ways to figure out unambiguously whether or not it's valid, and an invalid submission is unambiguously invalid so the submitter can be heavily penalized. Unavailable data, on the other hand, is much harder to deal with, because even though unavailability can be detected if challenged, one cannot reliably determine whose fault the non-publication is, especially if data is withheld by default and revealed on demand only when some verification mechanism tries to verify its availability. This is illustrated in the Fisherman's Dilemma, which shows how a challenge-response game cannot distinguish between malicious submitters and malicious challengers. Fisherman's Dilemma. If you only start watching the given specific piece of data at time t3, you have no idea whether you are living in case 1 or case 2, and hence who is at fault. Plasma and channels both work around the Fisherman's Dilemma by pushing the problem to users. If you as a user decide that another user you are interacting with, a counterparty in a state channel, an operator in a Plasma chain, is not publishing data to you that they should be publishing, it's your responsibility to exit and move to a different counterparty/operator. The fact that you as a user have all of the previous data, and data about all of the transactions you signed, allows you to prove to the chain what assets you held inside the layer 2 protocol, and thus safely bring them out of the system. You prove the existence of a previously agreed operation that gave the asset to you. No one else can prove the existence of an operation approved by you that sent the asset to someone else, so you get the asset. The technique is very elegant. However, it relies on a key assumption, that every state object has a logical owner, and the state of the object cannot be changed without the owner's consent. This works well for UTXO-based payments, but not account-based payments, where you can edit someone else's balance upward without their consent. This is why account-based Plasma is so hard, and it can even be made to work for a decentralized exchange, but this ownership property is far from universal. Some applications, e.g. Uniswap, don't have a natural owner, and even in those applications that do, there are often multiple people that can legitimately make edits to the object, and there is no way to allow arbitrary third parties to exit an asset without introducing the possibility of denial of service, DOS, attacks, precisely because one cannot prove whether the publisher or submitter is at fault. There are other issues peculiar to Plasma and channels individually. Channels do not allow off-chain transactions to users that are not already part of the channel. Argument, suppose there existed a way to send $1 to an arbitrary new user from inside a chain. Then this technique could be used many times in parallel to send $1 to more users than there are funds in the system, already breaking its security guarantee. Plasma requires users to store large amounts of history data, which gets even bigger when different assets can be intertwined, e.g. when an asset is transferred conditional on transfer of another asset, as happens in a decentralized exchange with a single-stage order book mechanism. Because data on-chain computation off-chain layer 2 techniques don't have data availability issues, they have none of these weaknesses. ZK and optimistic rollup take great care to put enough data on-chain to allow users to calculate the full state of the layer 2 system, ensuring that if any participant disappears a new one can trivially take their place. The only issue that they have is verifying computation without doing the computation on-chain, which is a much easier problem. And the scalability gains are significant, 10 bytes per transaction in ZK rollup, and a similar level of scalability can be achieved in optimistic rollup by using BLS aggregation to aggregate signature. This corresponds to a theoretical maximum of 500 transactions per second today, and over 2,000 post-Istanbul. But what if you want more scalability? Then there is a large middle ground between data on-chain layer 2 and data off-chain layer 2 protocols, with many hybrid approaches that give you some of the benefits of both. To give a simple example, the history storage blowup in a decentralized exchange implemented on Plasma Cash can be prevented by publishing a mapping of which orders are matched with which orders. That's less than 4 bytes per order, on-chain. Left, history data a Plasma Cash user needs to store if they own one coin. Middle, history data a Plasma Cash user needs to store if they own one coin that was exchanged with another coin using an atomic swap. Right, history data a Plasma Cash user needs to store if the order matching is published on-chain. Even outside of the decentralized exchange context, the amount of history that users need to store in Plasma can be reduced by having the Plasma chain periodically publish some per user data on-chain. One could also imagine a platform which works like Plasma in the case where some state does have a logical owner and works like ZK or optimistic rollup in the case where it does not. Plasma developers are already starting to work on these kinds of optimizations. There is thus a strong case to be made for developers of Layer 2 scalability solutions to move to be more willing to publish per-user data on-chain at least some of the time. It greatly increases ease of development, generality, and security and reduces per-user load. 8. No need for users storing history data. The efficiency losses of doing so are also overstated. Even in a fully off-chain Layer 2 architecture, users depositing, withdrawing and moving between different counterparties and providers is going to be an inevitable and frequent occurrence, and so there will be a significant amount of per-user on-chain data regardless. The hybrid route opens the door to a relatively fast deployment of fully generalized Ethereum-style smart contracts inside a quasi-Layer 2 architecture. See also. Introducing the OVM. Blog post by Carl Loading mathjax/extension/mathzoom.js. On-chain scaling to potentially 500TX/SEC through MassTX validation. We can actually scale asset transfer transactions on Ethereum by a huge amount, without using Layer 2s that introduce liveness assumptions, e.g. channels, Plasma, by using ZK snarks to mass validate transaction. Here's how we do it. There are two classes of user, I, transactor, and 2, relayer. A relayer takes a set of operations from transactors, and combines them all into a transaction and makes a ZK snark to prove the validity, and publishes the ZK snark and the transaction data in a highly compressed form to the blockchain. A relayer gets rewarded for this by transaction fees from transactors. The system is managed by a contract, whose state consists solely of 2 bytes 32 values representing Merkle roots, address book, A, and balances plus nonces, B. A starts off as a Merkle root of 2/24, 2242/24, 0 entries, and B is a Merkle tree of 2/24, 2242/24, 0, 0, tuple. There are 3 types of operations for transactors, I, registration, 2, deposit/withdraw, and 3, sending. To register, a user needs to provide a Merkle branch showing some index I, where either I equals 0 and AI equals 0, or I0 and AI equals 0 and AI1 equals 0. The Merkle tree is updated so that AI now equals the message sender's address, and the Merkle branch is logged so that a client reading logs can get all of the data they need to create their own Merkle branches. To deposit or withdraw, a user needs to provide a Merkle branch showing some index I, where AI equals the message sender's address, along with the corresponding branch for BI, and the amount they want to deposit or withdraw, D, negative for withdrawals. The contract checks that BI0 plus D equals 0. If D0, it verifies that, if the system is for ETH, message value equals D asterisk 1012, i.e. the base unit of the system is 10 carat minus 6. 10 6 10 carat minus 6. ETH, or otherwise calls transfer from, message sender, self, D asterisk 1012, to the appropriate of 20 token contract, if D. The contract then updates the Merkle root so that BI0 plus equals D. Note that for efficiency, we can combine together the registration and deposit steps for not yet registered transactor. To send, a user constructs the data, from address index, 3 bytes, to address index, 3 bytes, amount, ETH's 100M supply requires 47 bits, so we can say 6 bytes, but most of the time. The user broadcasts, from, to, amount, fee, nonce, plus a signature. A relayer can gather together many of these operations, and create a ZK snark proving that, when processing all of the operations in sequence, at that start of each operation B from 0 equals amount plus fee, B from 1 equals nonce, and that a valid signature is known from A from, and then updating the Merkle root with B from 0 dash equals amount plus fee, B to 0 plus equals amount, B relayer 0 plus equals fee, B from 1 plus equals 1. A log is issued to alert users that the transaction is a payment batch transaction and they would need to recompute their Merkle tree witnesses. The cost of a ZK snark verification with the latest protocols is 600,000 gas, and we can add 50,000 gas for overhead, base TX cost, log cost, storage slot modifications. Otherwise, each transaction included costs 68 gas per byte, unless it is a 0 byte, in which case it goes down to 4 gas. Hence, for a regular transfer, we can expect the marginal cost to be 68*3, from, plus 68*3, to, plus 68*1, fee, plus 68*4 plus 4*2, amount, plus 68*2, nonce, or 892 gas. In the best case, a relay transaction would consume a block's full 8 million gas, so the marginal costs could take up 91% of the total costs, so the total cost would be. In practice, it would be more at first, as while the system has low volume, users would prefer faster smaller batches even at higher cost per transaction over slower larger batches, but once the system gets to high volume, it should be able to get efficiency levels close to this. Note that anyone can be a relayer, there is no assumption of even an untrusted special operator existing. Because all the data needed to update the Merkle tree goes on-chain, there are no data availability issues. We can optimize further by allowing a relayer to, with ZK snarks proving the operation, rebalance the tree, moving more frequent users into lower indices, changing the encoding for the value so that common values, each round numbers of ETH, are represented, and changing the nonce scheme so that, for example, details in the signature change every 100 blocks and so the nonce can reset every 100 block. Popular links. There are 82 replies with an estimated read time of 23 minutes. At vbuterin. Good day, Vitalik. Posting block in the logs is a great approach, although I may add the following points for clarification. To actually verify that what was posted in logs corresponds to the state update that is proved by a ZK-SNARK, you have to include every field of the transaction as a public input to the snark verification. It is an extra 1-point multiplication per input parameter. If the transaction is short, you can pack and reduce this number of inputs, but still, right now it's 40,000 gas per multiplication in G1 of B. As an alternative, you can make only a sparse Merkle tree of all transaction as a public parameter and include this root as a public input. In this case, a sponsored MEMC calculation on-chain is required, or an internal R1CS grows 25,000 constraints per SHA-256, and assuming 1,000 transactions per proof, it's 25 million constraints for a block Merkle root only. Snark-based sidechain for 20 tokens. This proposal is inspired by earlier posts from @vbuterin, link 53, and @Barry Whitehat, link 53. Overview. In the post, we introduce a Snark-based sidechain for an 20-like token. This is useful for organizations that wants to issue their platform tokens, games, streaming platforms, and more. The token is governed by an on-chain smart contract, which maintains the token balance for each user. However, different from a standard 20 token, in our case a special role called operator regularly submits blocks to the smart contract. Each block contains a list of token transfer transactions, along with a snark proof which only proves the validity of the user signatures. The smart contract verifies the snark proof and then executes the transactions to update the token balance for the user. Compared to Barry Whitehat's proposal, this scheme might require much less computational overhead for snark generation, and yet the runtime complexity of the on-chain smart contract is the same. Below are the details. System spec. System spec. There are 3 roles. The users, a Plasma operator, and an on-chain smart contract. User responsibility. Users submit token transfer transactions to the operator. A transaction TX is the concatenation of 5 strings. TX equals FT and VSIG. Here F is the address of the from account, T is the to account, N is the nonce of the from account, V is the amount of tokens to be transferred, and SIG is the signature of the from account. Plasma operator responsibility. As the Plasma operator accumulates the transactions, he packs them into blocks. A block is the concatenation of multiple transactions, thousands of transactions. BLK equals tx1 tx2, txn. The operator also calculates the hash of the block BLK. HB equals hash, BLK. Then, the plasma operator generates a snark proof, which proves the validity of the signatures of the transaction. To be more specific, the snark proves that for input HB, there exists a witness string BLK equals tx1 tx2, txn, such that HB equals hash, BLK, and verify, TC, SIGI, equals true for I equals 1, 2, n. The plasma operator then submits a tuple, BLK, HB, to the smart contract. Smart contract responsibility. The smart contract stores the balance of each user's on-chain. It has two responsibilities. 1. Penalize the plasma operator if he behaves maliciously, and 2. Process the blocks submitted by the plasma operator. To achieve the first goal, the plasma operator needs to deposit a certain amount of ethers into the smart contract as the collateral. The smart contract can detect malicious operator behaviors. Such behaviors include but not limit to, the block submitted contains invalid transactions, e.g., trying to send more tokens than the from account's balance, or the snark proof is invalid, or the operator has not submit new blocks for a certain period of time. If any malicious behavior is detected, the operator will lose his collateral. To process the blocks submitted, the smart contract needs to carry out the following tasks. Firstly, it verifies the snark proof with input HB. Secondly, it validates HB equals hash, BLK. This is necessary since HB is the input to the snark verification. If the snark verification passes, it means the submitted block BLK indeed contains valid signatures from the senders. Finally, the smart contract execute each transaction in the block and update the account balances. Smart contract runtime analysis. This proposed scheme can reduce processing time per transaction significantly compared to a fully on-chain 20 smart contract. Firstly, the verification of the signatures for each transaction in the block is replaced by one single snark proof verification. The snark verification can be executed in constant amount of time, typically a couple milliseconds, since its input HB is simply a hash, whose length is a constant. Secondly, let us look at the transaction execution time. At the first glance, it might appear that in our proposal does not have advantage compared to a fully on-chain smart contract. However, we note that the plasma operator can pack many transactions, e.g. thousands, into one block. It could happen that many of these transactions have the same sender in/or receive. Processing these transactions in batch reduces the time spent on account lookup and balance update. Let us look at an example. Assume a block contains multiple transactions between two accounts A and B. TX1, sends 60 tokens, TX2, TX3, TX4. When the smart contract processes these transactions together, it only needs to look up the account of A and B once. It then calculates the final balance of A and B, and then update the accounts just one. In comparison, with a fully on-chain smart contract, each of these transactions is processed individually. Each time the accounts of A and B need to be retrieved and updated. Thus the runtime complexity for our framework is O, m log n plus k. Here m is number of distinct accounts accessed by the transactions in the block. N is the total number of token holders, and k is the number of transactions in the block. On the other hand, with a fully on-chain smart contract, the runtime complexity is O, k log n. Since m could be much smaller than k, considerable speedup can be achieved. Finally, we note that the smart contract needs to validate HB equals hash, BLK. Even with thousands of transactions, the size of a block is still in the range of sub-100 kilobytes, with some compaction. So validating the hash should only take at most a couple milliseconds. With the above runtime estimations, the transaction throughput should reach at least hundreds of TPS, maybe even 1000 plus TPS for the token. Snark generation complexity. One significantly difference of the proposed framework compared to Barry Whitehead's proposal is that our snark proof only proves the validity of the sender signatures. It does not prove the validity of state transfer, i.e. the validity of the account balance update. This is intended to significantly reduce the snark generation time. Compared to Barry Whitehead's approach which calculates the account balances off-chain, in our proposal, the balances are calculated by the smart contract. However, the overhead is minimal, since calculating the account balance only involves simple addition/subtraction. The account lookup/update complexity are the same for the two approaches. This trade-off leads to substantial reduction in terms of snark generation complexity. The runtime complexity of the snark generation is a quasi-linear function of the total size of the input and witness string, e.g. O, s log s, where s is the total size. If we want to prove both the state transfer and the sender signatures are valid, this size is in the order of O, m log n plus k. Here the notations are as above. M is number of distinct accounts accessed by the transactions in the block, n is the total number of token holders, and k is the number of transactions in the block. On the other hand, if we only generate the proof for the signature, the size of the witness string is only O, k. To get a more concrete idea, in Barry Whitehead's post, it is estimated that with optimization, for each transaction, proving the account is part of the state tree takes 29k*2 equals 58k constraints, while confirming one signature could only requires as little as 2k constraints. Thus, this could lead to more than 30x speedup for snark proof generation. With 1000 transactions per block, the total number of constraint for signature verification is only 2k*1000 equals 2 million transactions. Potentially the snark generation can be done on a single machine rather than using a high-end server cluster. Remarks. Snark is mining. An interesting variant of the proposed framework is to let users generate the snark proof instead of the plasma operator. Each time a new block is submitted to the smart contract by the operator, users can compete to generate the snark proof for the block. The first user submit the proof wins some newly minted tokens similar to mining reward. This way users can play the role of snark miners to enhance the security of the system. If instead a user finds out that a block contains invalid signatures, he can inform the smart contract. If this is indeed the case, the smart contract can slash the ether collateral of the plasma operator and award a portion of the collateral to the user. Block and state pruning. We also note that after the smart contract validated a block and updated the account balances, the block is no longer needed. It can be deleted from the smart contract storage to save space. Thus, our proposal does not incur much extra space overhead besides the user account storage. Links. Is this a correct summary of your approach? The snark validates signatures and the EVM performs state transitions? If so, what are the gas costs of these state transitions per transaction? A note on data availability and erasure coding. V. Buterin edited this page September 25, 2018. 18 revisions. Pages 5. Edit September 25, 2018. https://ar14.org/abs/1809.09044 for a paper version of this. What is the data availability problem? In order to understand the data availability problem, it is best to first start off by understanding the concept of fraud proofs. Suppose that an attacker makes a block which is invalid in some way. For example, the post state root is wrong, or some transaction is invalid or malformatted. Then, it is possible to create a fraud proof that contains the transaction and some Merkle tree data from the state and use it to convince any like client, as well as the blockchain itself, that the block is invalid. Intuitively, one can think of this fraud proof as containing just the parts of the state required to process the block in question, plus some hashes to prove that the parts of the state provided actually do represent the state that the block claims to be building on top of. Verifying the fraud proof involves using the given information to try to actually process the block, and see if there is some error in the processing. If there is, then the block is invalid. The possibility of fraud proofs theoretically allows like clients to get a nearly full client equivalent assurance that blocks that the client receives are not fraudulent, nearly, because the mechanism has the additional requirement that the like client is connected to at least some other honest nodes. If a like client receives a block, then it can ask the network if there are any fraud proofs, and if there are not, then after some time the like client can assume that the block is valid. The incentive structure for fraud proofs is simple. If someone sends an invalid fraud proof, they lose their entire deposit. If someone sends a valid fraud proof, the creator of the invalid block loses their entire deposit, and some small portion goes to the fraud proof creator as a reward. Although this mechanism is elegant, it contains an important hole. What if an attacker creates a possibly valid, possibly invalid block but does not publish 100% of the even if succinct zero-knowledge proofs can be used to verify correctness, an attacker getting away with publishing unavailable blocks and getting them included in the chain is still very bad, as such a thing happening denies all other validators the ability to fully calculate the state, or to make blocks that interact with the portion of the state that is no longer accessible. There are also other bad consequences to accepting valid blocks with unpublished data. For example, schemes such as hash locks for atomic cross-chain swaps or coin for data trading rely on the assumption that data published to the blockchain will be publicly accessible. Here, fraud proofs are not a solution, because not publishing data is not a uniquely attributable fault in any scheme where a node, fisherman, has the ability to raise the alarm about some piece of data not being available. If the publisher then publishes the remaining data, all nodes who were not paying attention to that specific piece of data at that exact time cannot determine whether it was the publisher that was maliciously withholding data or whether it was the fisherman that was maliciously making a false alert. Notice that from the point of view of someone who only checks on the data after T3, case 1, and case 2 are indistinguishable. This then creates an impossible choice. Suppose that an attacker engages in an attack where they withhold data, wait for a fisherman to catch them, and then release the data immediately. In such a scenario, is the reward of the fisherman net positive? If so, malicious fisherman raising false alarms is a money pump vulnerability. Is the reward 0? If so, this is a cost-free dose vulnerability that can be exploited to force nodes to download all data in the blockchain, nullifying the benefits of like clients or shard. Is the reward negative? If so, then being a fisherman is an altruistic act, and so an attacker need only economically outlast altruistic fishermen, at which point they are then free to include blocks with data unavailable unimpeded. Erasure codes is a solution. One natural solution to this is to have like clients all verify data availability of a block before accepting it as valid, but do so probabilistic. A like client might pick 20 random chunks of a block, try to download them from the network, using the Merkle root in the block header to verify each chunk, and only accept the block if all 20 requests get a valid response. If this check passes, and assuming an honest minority assumption that there are enough honest users making these checks that the honest users together are making enough requests to download most of the block, a like client knows that with very high probability that the majority of the block is available. However, there are still very dangerous attacks that could take place from only withholding a few hundred bytes of data, and such an attack would still slip through most clients making such a check. To solve this problem, we use erasure codes. Erasure codes allow a piece of data m chunks long to be expanded into a piece of data n chunks long. Chunks can be of arbitrary size, such that any m of the n chunks can be used to recover the original data. We require blocks to commit to the Merkle root of this extended data, and have like clients probabilistically check that the majority of the extended data is available. If the majority of the extended data is available, the like client knows that one of three things is true. The entire extended data is available, the erasure code is constructed correctly, and the block is valid. The entire extended data is available, the erasure code is constructed correctly, but the block is invalid. The entire extended data is available, but the erasure code is constructed incorrect. In case 1, the block is valid and the like client can accept it. In case 2, it is expected that some other node will quickly construct and relay a fraud proof. In case 3, it is also expected that some other node will quickly construct and relay a specialized kind of fraud proof that shows that the erasure code is constructed incorrect. If a like client receives no fraud proofs for some time, it will take that as evidence that the block is in fact valid. See here for sample code implementing all of this logic. Optimization. If one uses the simplest kind of Reed-Solomon code, the size of a fraud proof in the above scheme is, unfortunately, equal to the size of the entire erasure code. The fraud proof simply consists of m Merkle proofs. The proof checking algorithm verifies the proofs, then it uses those m chunks to compute the remaining chunks, and it checks whether or not the Merkle root of the full set of chunks is equal to the original Merkle root. If it is not, then the code is malformed. Here are some approximate statistics for applying a one-dimensional Reed-Solomon code to 256 KB and 1 megabyte of data, using 256 byte chunks. Size of like client proof, 256 KB 20 branches asterisk, 256 bytes plus 10 Merkle tree intermediate hashes asterisk 32 bytes per hash, equals 11,520 bytes. Size of like client proof, 1 megabyte 20 branches asterisk, 256 bytes plus 12 Merkle tree intermediate hashes asterisk 32 bytes per hash, equals 12,800 bytes. Time spent to encode in C++, 256 KB 2.4 seconds. Time spent to encode in C++, 1 megabyte 21 seconds. Time spent to verify fraud proof, 256 KB 2.4 seconds. Time spent to verify fraud proof, 1 megabyte 21 seconds. Size of fraud proof, 256 KB 256-512 KB. Size of fraud proof, 1 megabyte 1-2 MB. The computation times include partial optimizations. 3/4 of the Lagrange interpolation is sped up to subquadratic runtimes using caret sub multiplication, though multi-point evaluations are still done in quadratic time. This is because it was found that subquadratic algorithms for multi-point evaluation are both more difficult to implement and had much higher constant factors, and so it was deemed a less worthwhile trade-off to implement them. The above runtimes also are done on a single core. All algorithms involved are highly parallelizable and highly GPU-friendly, so further speedups are possible. One can go further by making the erasure code multidimensional. In a simple Reed-Solomon code, the original data is interpreted as a set of points representing the evaluation of a polynomial at x equals 0, x equals 1. X equals m1. The process of extending the data involves using Lagrange interpolation to compute the coefficients of the polynomial and then evaluating it at points x equals m. X equals n1. We can improve on this by instead interpreting the data as a square, representing the evaluation of a polynomial at x equals 0, y equals 0, x equals sqrt, m-1, y equals sqrt, m-1. The square can then be extended to a bigger square, going up to x equals 2 sqrt, m-1, y equals 2 sqrt, m-1. This reduces, in such a model, this reduces the computational complexity of computing the proofs as the polynomials involved are lower degree, and also reduces the size of the fraud proof. In such a model, we add some further complexity to the data structures involved. First of all, instead of having a single Merkle root, we now have 4 sqrt, Merkle roots, one for each row and one for each column. Like clients would need to download all of this data as part of a like client proof. For a 1 megabyte file with 256 byte chunks, i.e. 4096 chunks in the original file in a 64x64 shape, so 128x128 in the expanded version, this would consist of 256 32 byte hashes, or 8192 extra bytes in the proof. Additionally, the number of branches required goes up from 20 to 48 to compensate for the fact that the 2D erasure code is more fragile. On the plus side, the size of a Merkle branch is A major benefit of this is that the size of a fraud proof is much lower. A fraud proof now consists of m values in a single row or column plus Merkle proofs for these values, and the process of verifying the proof involves recovering the missing data from these values, computing the Merkle root, and showing that this does not match the Merkle root provided. Note that the fraud prover has total free choice about whether the Merkle proofs provided come from the Merkle trees for the row or the column. This allows fraud proofs to cover both malformed rows and columns and inconsistencies between the row and column Merkle tree. We now present the new statistics, still with 256 byte chunks, for 1 megabyte, 4096 chunks, and 4 megabytes, 16,384 chunks. Note that these are estimates. The algorithms for doing this in full have not been fully implemented. Size of light client proof, 1 megabyte 48 branches asterisk, 256 bytes plus 6 Merkle tree intermediate hashes asterisk 32 bytes per hash, plus 128 Merkle roots asterisk 32 bytes per hash, equals 25,600 byte. Size of light client proof, 4 megabytes 48 branches asterisk, 256 bytes plus 7 Merkle tree intermediate hashes asterisk 32 bytes per hash, plus 256 Merkle roots asterisk 32 bytes per hash, equals 31,232 byte. Time spent to encode in C++, 1 megabyte 7.5 sec. Time spent to encode in C. Time spent to verify. Time spent to verify. Maximum size of fraud proof, 1 megabyte 6 Merkle tree intermediate hashes asterisk. Maximum size of fraud proof, 4 meg. How could this fit together into a complete mechanism for data availability and fraud proofs in a blockchain? A simple and generic approach is as follows. Every top-level block would contain a Merkle root of erasure-coded data. The data would be the entire data that makes up the top-level block in some canonical serialized form, including the contents of every shard. Whenever there exist parts of a block that might have variable length, either they are padded with 0 bytes up to their maximum possible length, each as determined by the block size or gas limit, or a table at the start of the encoded data is used to denote the start and end of each chunk. There would then be two kinds of fraud proof. The first kind is a fraud proof of the erasure code itself, which depends on the specific algorithm used. The second kind is a fraud proof showing that the data committed to in the erasure-coded Merkle root does not follow the rules of the protocol. If, for example, the rules of the protocol specify that the bazook should be equal to the SHA-3 of the concatenation of the kblug and the marys, and the canonical encoding of the block places the bazook at bytes 1000, 1031, the kblug at bytes 50,000, 50999 and the marys at bytes 55,000, 55999, then one can make a proof consisting of the Merkle branches from the erasure-coded Merkle root pointing to the bazook, kblug and marys, and one can verify that the three values do not satisfy the relation that the protocol says they should satisfy. Isn't this basically the same thing as proofs of retrievability? Sort of, but not quite. Four protocols generally work as follows. Alice creates a file, sends it to Bob, and then Bob proves to Alice using some tricks that usually also involve erasure coding and random sampling that he still has the file. Sometimes, Bob needs to prove to Carol instead of Alice, and there are some restrictions on what information can be shared between Alice and Carol. These protocols often involve max or in more advanced cases various partially homomorphic schemes including elliptic curve. In all cases, Alice is assumed to be trusted, in the sense that we assume that any check data added by Alice was added correctly, that the file actually exists, and that any kind of public key given by Alice to Carol was generated correct. In our model, the potential adversary, Bob, is themselves the one creating the file. Bob submits some small piece of data, think, the Merkle root of the erasure-coded data, to Carol, and Carol is seeking an assurance that the Merkle root actually does represent a piece of data, that it was constructed correctly, and that this data is retrieved. Carol trusts no one except for herself, and the assurance that there exist enough other Carols also making spot checks that between them, they can either find a flaw in the data or they can download the entire file. A key desired property is consensus. If Carol verification algorithm for some file returns true, and we assume there are enough verifying clients in the network, then with very high probability David will also, perhaps after some time bound based on network latency, return true for the same file. It cannot be possible for different participants to permanently disagree on the result, even if Bob crafts and publishes data malicious. What are the challenges in making these proofs really big, like multi-gigabyte? There are two major challenges. If we simply take the two-dimensional scheme and try to make it higher dimensional, then the number of intermediate Merkle roots that would go into a light client proof becomes extremely large, and instead of including those Merkle roots directly in the light client proof, we make yet another data availability proof of them, which would then need a much smaller number of Merkle root. If the proofs are extremely large, then we cannot rely on a single node making the entire proof. Instead, we would need to rely on some kind of collaborative generation. However, this makes fault identification harder. If row X does not match with column Y or shaft Z, and the two were made by different validators, how do we tell whose fault it is? This is likely solvable, perhaps by having validators point to a justification for the row/column/shaft, e.g. a bit mask for which existing values they used, which could then be used to deduce which party was at fault, but this adds complexity to the scheme. Can proofs of proximity help? Yes. A proof of proximity is a short proof that can be added to a Merkle root that probabilistically, in the Fiat-Shamir sense, proves that at least some large percentage, e.g. 90%, of the data in the Merkle tree is on the same low-degree polynomial. https://bit.ly/general/2017/11/22/starks_part_2.html for a detailed description of how POPs work. One can create a proof of proximity that proves that some Merkle root with two n values is 90% close to a degree n polynomial, and this proves that there is some unique set of data, n values, that the data is close to. Users can verify this proof, and also randomly download a sample of branches of the tree to probabilistically verify that, for example, at least 80% of the data is available. In such a case, any two users that pass the same test will definitely have at least n*1.44 values, which they can use to recover the original data, perhaps canceling out errors with something like the Berlekamp-Welch algorithm, and there is an assurance that the data recovered by those two users will be the same. One difficulty that this approach introduces is that not every Merkle branch will point to the underlying data, as the proof of proximity can tolerate a small number of faults. Hence, proving membership of any specific piece of data would require a proof of proximity augmented with a proof that the value presented by that Merkle branch is on the same low-degree polynomial. So this is ultimately inferior to the further solution described below. Can SNARKs or Starks help? Yes. SNARKs and Starks can be used to create succinct 1. Sized proofs that the Merkle root of the data was constructed correctly, and at the same time prove that the state transitions executed in the block are valid. This allows us to make the process of verifying a block very conceptually simple. Suppose that a header is of the form previous_state_root, tx_root, post_state_root, proof, sig, where proof is a star. The proof would prove that the tx_root is the Merkle tree root of some data, where one part of the data is a set of transactions, and the other parts of the data are correctly formed erasure code for that data. It would also prove that executing those transactions on top of previous_state_root would result in post_state_root as the final state root hat. Note that to create the Stark, the creator would need to provide all of the Merkle tree nodes accessed as a witness, but this data does not need to go into the Stark itself. To verify a block, a client would only need to download the header, verify the Stark, and then randomly sample some Merkle branches of the erasure-coded data. A more advanced mechanism can be created using recursive Starks, i.e. Starks proving the validity of other Starks, allowing the erasure-coded data to be created collaboratively, solving the second problem mentioned above. Theoretically, the only upper limit to the scalability of such a scheme is the amount of data that nodes around the network are willing to reliably store voluntarily. Can an attacker not circumvent this scheme by releasing a full unavailable block, but then only releasing individual bits of data as clients query for? Kind of, but with limitations. Suppose that a block has 4 megabytes data, and each light client is making 20 queries for 256 bytes each. If, in the entire network, there are less than 820 light clients, then it is indeed the case that the attacker can do such an attack, and trick every light client into believing the block is available when in reality not enough data was published to reconstruct the whole thing. In reality, you need 1140 light clients to make up for overlap, and more if the erasure code is two-dimensional. Also, if the erasure code is fraudulent, then the fraud may never be discovered. Hence, the scheme depends on two honest minority assumptions. There exist enough honest-like clients that the intersection of their data availability proof requests is overwhelmingly likely to be equal to enough of the erasure-coded data to recover the whole thing. There exist enough honest nodes that will generate and forward fraud proofs if they discover that any part of the erasure code is fraudulent. Now, even if there are more than 1140 honest-like clients, an attacker could decide to answer the requests of the first 1,000 of them, and then stop responding to requests, thereby tricking a few nodes. This can be overcome by sending each request separately through an anonymizing onion routing network, so that an attacker cannot tell which requests came from the same node. Nodes that partially trust each other, i.e. trust each other to probably not be Sibyls, could also gossip to each other if they get a failure on any of their requests, allowing other nodes to try to make that request themselves. This way, if a block is rejected by a large portion of nodes, it would come to be rejected by all nodes. That feels a bit more rickety than just having everyone download and verify everything. It is imperfect, but do note that if the design is constructed correctly, many things have to go wrong at once for the scheme to. A well-designed scalable data availability verification scheme would have a randomly selected committee of validators sign off on each piece of data, so both the honest majority model and the honest client minority assumption would need to fail for unavailable data to get through. That said, making sure that the data does not spread so thin that the honest client minority assumption becomes an actual concern is perhaps the main scalability limitation that the scheme does have. Even if it works well for gigabyte blocks, it would not work well for petabyte blocks. Start proving low degreeness of a data availability route, some analysis. This post assumes familiarity with data availability sampling as in https://ar14.org/abs/1809009044156. The holy grail of data availability sampling is that we could remove the need for fraud proofs to check correctness of an encoded Merkle route. This can be done with polynomial commitments, including Friday, but at a high cost, to prove the value of any specific coordinate di/d. di/d. You would need a proof that \frac d xx I \frac d xx I, where x is the claimed value of di. di is a polynomial, and this proof takes linear time to generate and is either much larger, as in Friday, or relies on much heavier assumptions, as in any other scheme, than the status quo, which is a single Merkle branch. So what if we just bite the bullet and directly use a Stark, or others EKP, to prove that a Merkle root of encoded data d0, d2 and 1, d0, d2 and 1, with degree. That is, we prove that Merkle root actually is the Merkle root. The holy grail of data availability sampling is that we could remove the need for fraud proofs to check correctness of an encoded Merkle root. This can be done with polynomial commitments, including Friday, but at a high cost, to prove the value of any specific coordinate di/d. di/d. You would need a proof that \frac d xx I \frac d xx I, where x is the claimed value of di. di is a polynomial, and this proof takes linear time to generate and is either much larger, as in Friday, or relies on much heavier assumptions, as in any other scheme, than the status quo, which is a single Merkle branch. So what if we just bite the bullet and directly use a Stark, or others EKP, to prove that a Merkle root of encoded data d0, d2 and 1, d0, d2 and 1, with degree. That is, we prove that Merkle root actually is the Merkle root of data encoded in such a way, with zero mistakes. Then, data availability sampling would become much easier, a more trivial matter of randomly checking Merkle branches, knowing that if more than 50% of them are available then the rest of d can be reconstructed and it would be valid. There would be no fraud proofs and hence no network latency assumptions. Here is a concrete construction for the arithmetic representation of the Stark that would be needed to prove that. Let us use the MIMC hash function with a sponge construction for our hash. P equals modulus. R equals quadratic non-residual mod P. K equals 127 constants. Def mimc underscore hash, x, y, l, r equals x, 0. For I in range, 127. L, R equals, L3 plus 3 QLR2 plus KI, percent P, 3L2B plus QR3, percent P. L equals Y. For I in range, 127. L, R equals, L3 plus 3 QLR2 plus KI, percent P, 3L2B plus QR3, percent P. Return L. The repeated loops are cubing in a quadratic field. If desired, we can prevent analysis over FP2 by negating the x coordinate, i.e. L, after every round. This is a permutation that is a non-arithmetic operation over FP2, so the function could only be analyzed as a function over FP of two values. Now here is how we will set up the constraints. We position the values in d, dd, at 1. Now here is how we will set up the constraints. We position the values in d, dd, at 128 asterisk k, 128 k 128 asterisk k, for 2n \lek. Now here is how we will set up the constraints. We position the values in d, dd, at 128 asterisk k, 128 k 128 asterisk k, for 2n \lek. We want to set up the constraint, x100, however, because h is a very high degree function, we cannot just set up that constraint directly. So here's what we do instead. We have two program state values, x and y, to fit the two-item MIMC hash function. For all I, 2, where I \% 128 \ne0, I %128 is not equal to 0 I \% 128 \ne0. We want xi equals xi plus 1, caret 3 plus 3q asterisk xi plus 1, y, I plus 1, caret 2 plus k, I. xi equals xi plus 1, 3 plus 3qx, I plus 1, y, I plus 1, 2 plus k, I. xi equals xi plus 1, caret 3 plus 3q asterisk xi plus 1, y, I plus 1, caret, for all, where, we want, if I edit October 9th, 2019, some have argued that for technical reasons the xi equals x2i127, xi equals x2i127, xi equals x2i127. Constraint cannot be soundly enforced. If this is the case, we can replace it with a Plunk-style 13 coordinate accumulator-based copy constraint argument. Extended underscore data, 3, 1062 times 224 5.97 kb. We can satisfy all of these constraints by defining some piecewise functions, c underscore I, xi, y, I, xi plus 1, y, I plus 1, x2i, k, I. ci, xi, y, I, xi plus 1, y, I plus 1, x2i, k, I, c underscore I, xi, y, I, xi plus 1, y, I plus 1, x2i, k, I. Where c underscore 0, we add indicator polynomials I underscore 0, I0 I underscore 0, I underscore 4, I4 I underscore 4. For when each constraint applies, these are public parameters that can be verified once in linear time, and then make the constraints I underscore I, x, asterisk c underscore I, xi, y, I, xi plus 1, y, I plus 1, x2i, equals 0. 2, x, ci, xi, y, I, xi plus 1, y, I plus 1, x2i, equals 0 I underscore I, x, asterisk c underscore I, xi. We can also add a constraint x2n plus 128 asterisk I, equals z, I. x2n plus 128 I, equals z, I. x2n plus 128 asterisk I, equals z, I. And verify with another polynomial commitment. The only difference between this and a traditional Stark is that it has high distance constraints. The xi equals x2i127. xi equals x2i127. xi equals x2i127. This does double the degree of that term of the extension polynomial, though the term itself is degree 1, so its degree should not even dominate. Performance analysis. The RAM requirements for proving n bytes of original data can be computed as follows. Size of extended data, 2n bytes. Total hashes in trace per chunk, 2. Total size in trace, 512 n bytes. Total size in extended trace, 4096 n bytes. Hence proving 2 megabytes of data would require 8 GB of RAM, and proving 512 megabytes would require 2 TB. The total number of hashes required for n bytes of data is n/32 *2 extension *2 Merkle tree overhead equals n/8. So proving 2 megabytes would require proving 2*18 2182*18 hashes, and proving 512. An alternative way to think about it is a Stark would be 512 times more expensive than raw Friday. This does show that if we expect a Merkle root to be accessed more than 512 times, which seems overwhelmingly likely, then starking the Merkle root and then using Merkle proofs for witnesses is more efficient than using Friday for witnesses. Current Stark provers seem to be able to prove 600 hashes per second on a laptop, which implies a 7-minute runtime for 2 megabytes and a day-long runtime for. However, this can easily be sped up with a GPU and can be parallelized further. Links. Very nice. So the plan is to agree on any data for which the encoding is correct. Then you couldn't use Friday, since if even one erasure-coded piece in the Merkle tree was not from the low-degree polynomial, it would be possible to convince a like client that we agreed on different. In this case, one of the two sets of data would probably be nonsense, but it would be possible to make everyone agree on nonsense just to attack one like client. Friday only guarantees that the commitment agrees with a low-degree polynomial for all except a few values. Unlike Friday, Kate, or other polynomial commitments don't give you the Merkle tree, so if you wanted to have a smaller proof with an updatable trusted setup, you'd probably still want to use a similar construction with a snark that shows both that the polynomial is low-degree and that the Merkle tree hashes are correct. The construction would need a relatively large field which would make decoding the Reed-Solomon code slow. I wonder if it would be possible to do the erasure coding in a subfield and the Stark in an extension. Dark mode toggle. Starks, part 2. Thank goodness it's Friday day. 2017 November 22nd. See all posts. Special thanks to Eli Ben-Sasson for ongoing help and explanations, and Justin Drake for review. In the last part of this series, we talked about how you can make some pretty interesting succinct proofs of computation, such as proving that you have computed the millionth Fibonacci number, using a technique involving polynomial composition and division. However, it rested on one critical ingredient, the ability to prove that at least the great majority of a given large set of points are on the same low-degree polynomial. This problem, called low-degree testing, is perhaps the single most complex part of the protocol. We'll start off by once again restating the problem. Suppose that you have a set of points, and you claim that they are all on the same polynomial, with degree less than d, i.e. deg. You want to create a succinct probabilistic proof that this is actually true. Left, points all on the same deg. Right, points not on the same deg. If you want to verify that the points are all on the same degree. If you want to verify that the points are all on the same degree. But what you can do is probabilistically check that at least some fraction, e.g. 90%, of all the points are on the same polynomial. Top left, possibly close enough to a polynomial. Top right, not close enough to a polynomial. Bottom left, somewhat close to two polynomials, but not close enough to either one. Bottom right, definitely not close enough to a polynomial. If you have the ability to look at every point on the polynomial, then the problem is easy. But what if you can only look at a few points? That is, you can ask for whatever specific point you want, and the prover is obligated to give you the data for that point as part of the protocol, but the total number of queries is limited. Then the question becomes, how many points do you need to check to be able to tell with some given degree of certainty? Clearly, d points is not enough. D points are exactly what you need to uniquely define a degree. As we see in the figure above, however, d plus 1 points or more do give some indication. The algorithm to check if a given set of values is on the same degree. First, select a random subset of d points, and use something like Lagrange interpolation. Search for Lagrange interpolation here for a more detailed description, to recover the unique degree. Then, randomly sample one more point, and check that it is on the same polynomial. Note that this is only a proximity test, because there's always the possibility that most points are on the same low-degree polynomial, but a few are not, and the d plus 1 sample missed those points entirely. However, we can derive the result that if less than 90% of the points are on the same degree. Specifically, if you make d plus k queries, and if at least some portion p of the points are not on the same polynomial as the rest of the points, then the test will only pass with probability, 1p. But what if, as in the examples from the previous article, d is very high, and you want to verify a polynomial's degree with less than d queries? This is, of course, impossible to do directly, because of the simple argument made above, namely, that any k less than or equal to d points are all on at least one degree. However, it's quite possible to do this indirectly by providing auxiliary data, and achieve massive efficiency gains by doing so. And this is exactly what new protocols like Friday, FastR's IOPP, Rs equals Reed-Solomon, IOPP equals Interactive Oracle Proofs of Proximity, and similar earlier designs called Probabilistically Checkable Proofs of Proximity, PCPPs, try to achieve. A first look at sublinearity. To prove that this is at all possible, we'll start off with a relatively simple protocol, with fairly poor trade-offs, but that still achieves the goal of sublinear verification complexity, that is, you can prove proximity to a degree. The idea is as follows. Suppose there are n points, we'll say n equals 1 billion, and they are all on a degree. We find a bivariate polynomial, i.e. an expression like 1 plus x plus xy plus x5y3 plus x12 plus xy11, which we will denote g, xy, such that g, xx1000, equals f, x. This can be done as follows. For the kth degree term in f, x, e.g. 1744x185423, we decompose it into xk%1000 floor, k/1000, in this case, 1744x423y185. You can see that if y equals x1000, then 1744x423y185 equals 1. In the first stage of the proof, the prover commits to, i.e. makes a Merkle tree of, the evaluation of g, xy, over the entire square 1, and xx1000 colon 1 less than or equal to x less than or equal to n, that is, all 1 billion x coordinates for the columns, and all 1 billion corresponding thousandth powers for the y coordinates of the row. The diagonal of the square represents the values of g, xy, that are of the form g, xx1000, and thus correspond to values of f, x. The verifier then randomly picks perhaps a few dozen rows and columns, possibly using the Merkle root of the square as a source of pseudo-randomness if we want a non-interactive proof, and for each row or column that it picks the verifier asks for a sample of, say, 10 points on the row and column, making sure in each case that one of the points demanded is on the diagonal. The prover must reply back with those points, along with Merkle branches proving that they are part of the original data committed to by the prover. The verifier checks that the Merkle branches match up, and that the points that the prover provides actually do correspond to a degree 1000 polynomial. This gives the verifier a statistical proof that most rows are populated mostly by points on degree. This thus convinces the verifier that most points on the diagonal actually do correspond to a degree. If we pick 30 rows and 30 columns, the verifier needs to access a total of 1010.60 rows plus calls equals 60,600 points, less than the original 1 million, but not by that much. As far as computation time goes, interpolating the degree. The prover complexity is higher. The prover needs to calculate and commit to the entire n rectangle, which is a total of 1018 computational effort, actually a bit more because polynomial evaluation is still superlinear. In all of these algorithms, it will be the case that proving a computation is substantially more complex than just running it, but as we will see, the overhead does not have to be that high. A modular math interlude. Before we go into our more complex protocols, we will need to take a bit of a digression into the world of modular arithmetic. Usually, when we work with algebraic expressions and polynomials, we are working with regular numbers, and the arithmetic, using the operators plus, dash, slash, and exponentiation, which is just repeated multiplication, is done in the usual way that we have all been taught since school. 2 plus 2 equals 4, 72/5 equals 14.4, 1001 equals 10020. However, what mathematicians have realized is that these ways of defining addition, multiplication, subtraction, and division are not the only self-consistent ways of defining those operators. The simplest example of an alternate way to define these operators is modular arithmetic, defined as follows. The percent operator means, take the remainder of 15, 53, etc. Note that the answer is always non-negative, so for example 1. For any specific prime number p, we can redefine x plus y, percent pxy, xy, percent pxy, xy, percent pxy, xy, percent px/y, xy p2, percent p. The above rules are all self-consistent. For example, if p equals 7, then 5 plus 3 equals 1, as 8% 7 equals 1. 1 3 equals 5, as 2% 7 equals 5. 2 5 equals 3. 3/5 equals 2, as 3 7 equals 93 75% 7 equals 2. More complex identities such as the distributive law also hold. 2 plus 4, 3 and 2 3 plus 4 3 both evaluate to 4. Even formulas like a 2b2 equals a b, a plus b, are still true in this new kind of arithmetic. Division is the hardest part. We can't use regular division because we want the values to always remain integers, and regular division often gives non-integer results, as in the case of 3/5. The funny p2 exponent in the division formula above is a consequence of getting around this problem using Fermat's-Little theorem, which states that for any non-zero x, this implies that xp2 gives a number which, if multiplied by x one more time, gives 1, and so we can say that xp2, which is an integer, equals 1x. A somewhat more complicated but faster way to evaluate this modular division operator is the extended Euclidean algorithm, implemented in Python here. Because of how the numbers wrap around, modular arithmetic is sometimes called clock math. With modular math, we've created an entirely new system of arithmetic, and because it's self-consistent in all the same ways traditional arithmetic is self-consistent, we can talk about all of the same kinds of structures over this field, including polynomials, that we talk about in regular math. Cryptographers love working in modular math, or, more generally, finite fields, because there is a bound on the size of a number that can arise as a result of any modular math calculation. No matter what you do, the values will not escape the set 0, 1, 2, p1. Fermat's-Little theorem also has another interesting consequence. If p1 is a multiple of some number k, then the function x rightward arrow xk has a small image. That is, the function can only give p1k plus one possible result. For example, x rightward arrow x2 with p equals 17 has only 9 possible results. With higher exponents, the results are more striking. For example, x right word arrow x8 with p equals 17 has only 3 possible results. And of course, x right word arrow x16 with p equals 17 has only 2 possible results. For 0 it returns 0, and for everything else it returns 1. Now a bit more efficiency. Let us now move on to a slightly more complicated version of the protocol, which has the modest goal of reducing the prover complexity from 1018 to 1015, and then 109. First, instead of operating over regular numbers, we are going to be checking proximity to polynomials as evaluated with modular math. As we saw in the previous article, we need to do this to prevent numbers in our starks from growing to 200,000 digits anyway. Here, however, we are going to use the small image property of certain modular exponentiations as a side effect to make our protocols far more efficient. Specifically, we will work with p equals 1,005,001. We pick this modulus because I, it's greater than 1 billion, and we need it to be at least 1 billion so we can check 1 billion points 2, its prime, and 3, p1 is an even multiple of 1000. The exponentiation x 1000 will have an image of size 1,000,006, that is, the exponentiation can only give 1,000,006 possible results. This means that the diagonal, x 1000, now becomes a diagonal with a wraparound, as x 1000 can only take on 1,000,006 possible values, we only need 1,000,006 rows, and so, the full evaluation of g, x 1000, now has only 1015 elements. As it turns out, we can go further, we can have the proof. Only commit to the evaluation of g on a single call. The key trick is that the original data itself already contains 1000 points that are on any given row, so we can simply sample those, derive the degree. We then check that the column itself is A. The verifier complexity is still sublinear, but the prover complexity has now decreased to 109, making it linear in the number of queries, though it's still superlinear in practice because of polynomial evaluation overhead. And even more efficiency. The prover complexity is now basically as low as it can be. But we can still knock the verifier complexity down further, from quadratic to logarithmic, and the way we do that is by making the algorithm recursive. We start off with the last protocol above, but instead of trying to embed a polynomial into a 2D polynomial where the degrees in x and y are equal, we embed the polynomial into a 2D polynomial where the degree bound in x is a small constant value. For simplicity, we can even say this must be that is, we express f, x, equals g, xx2, so that the row check always requires only checking 3 points on each row that we sample, 2 from the diagonal plus 1 from the column. If the original polynomial has degree, the rows are straight lines, and the column has degree. Hence, what we now have is a linear time process for converting a problem of proving proximity to a polynomial of degree. Furthermore, the number of points that need to be committed to, and thus the prover's computational complexity, goes down by a factor of 2 each time. Eli Ben Sasson likes to compare this aspect of Friday to fast Fourier transforms, with the key difference that unlike with FFTs, each step of recursion only introduces one new subproblem instead of branching out into 2. Hence, we can simply keep using the protocol on the column created in the previous round of the protocol, until the column becomes so small that we can simply check it directly. The total complexity is something like n plus n2 plus n4 plus 2. In reality, the protocol will need to be repeated several times, because there is still a significant probability that an attacker will cheat one round of the protocol. However, even still the proofs are not too large. The verification complexity is logarithmic in the degree, though it goes up to log 2n if you count the size of the Merkle proof. The real Friday protocol also has some other modifications. For example, it uses a binary Galois field, another weird kind of finite field, basically, the same thing as the 12th degree extension fields I talk about here, but with the prime modulus being 2. The exponent used for the row is also typically 4 and not 2. These modifications increase efficiency and make the system friendlier to building starks on top of it. However, these modifications are not essential to understanding how the algorithm works, and if you really wanted to, you could definitely make starks with the simple modular math-based Friday described here. Soundness. I will warn that calculating soundness, that is, determining just how low the probability is that an optimally generated fake proof will pass the test for a given number of checks, is still somewhat of a here be dragons area in this space. For the simple test where you take 1 million plus k points, there is a simple lower bound. If a given dataset has the property that, for any polynomial, at least portion p of the dataset is not on the polynomial, then a test on that dataset will pass with at most 1p k probability. However, even that is a very pessimistic lower bound. For example, it's not possible to be much more than 50% close to 2 low-degree polynomials at the same time, and the probability that the first points you select will be the one with the most points on it is quite low. For a full-blown Friday, there are also complexities involving various specific kinds of attacks. Here is a recent article by Ben Sasson et al. Describing soundness properties of Friday in the context of the entire Stark scheme. In general, the good news is that it seems likely that in order to pass the d, x, z, x, equals c, p, x, check on the Stark, the d, x, values for an invalid solution would need to be worst case in a certain sense. They would need to be maximally far from any valid polynomial. This implies that we don't need to check for that much proximity. There are proven lower bounds, but these bounds would imply that an actual Stark need to be 1-3 megabytes in size. Conjectured but not proven stronger bounds reduce the required number of checks by a factor of. The third part of the series will deal with the last major part of the challenge in building Starks, how we actually construct constraint checking polynomials so that we can prove statements about arbitrary computation, and not just a few Fibonacci numbers. Fermat's little theorem. Fermat's-Little theorem states that if p is a prime number, then for any integer a, the number is an integer multiple of p. In the notation of modular arithmetic, this is expressed as, for example, if a equals 2 and p equals 7, then 27 equals 128, and 128 2 equals 126 equals 7 times 18 is an integer multiple of 7. If a is not divisible by p, that is if a is co-prime to p, Fermat's-Little theorem is equivalent to the statement that a p11 is an integer multiple of p, or in symbols 1 2. For example, if a equals 2 and p equals 7, then 26 equals 64, and 64 1 equals 63 equals 7 times 9 is thus a multiple of 7. Fermat's-Little theorem is the basis for the Fermat primality test and is one of the fundamental results of elementary number theory. The theorem is named after Pierre de Fermat, who stated it in 1640. It is called the Little theorem to distinguish it from Fermat's last theorem 3. History edit. Pierre de Fermat first stated the theorem in a letter dated October 18, 1640, to his friend and confidant Frenicle de Bessy. His formulation is equivalent to the following 3. If p is a prime and a is any integer not divisible by p, then a p11 is divisible by p. Fermat's original statement was, tout nombre premier misure infalliblement unde puissances. 1. De qualque progression kce soi, etl exposant de la die puissance su multiple du nombre premier done. 1. Et. Operation. This may be translated, with explanations and formulas added in brackets for easier understanding, as every prime number p divides necessarily one of the powers -1 of any geometric progression a 2, a 3, that is, there exists t such that p divides it, 1, and the exponent of this power t divides the given prime -1 divides p, 1. After one has found the first power t that satisfies the question, all those whose exponents are multiples of the exponent of the first one satisfy similarly the question, that is, all multiples of the first t have the same property. Fermat did not consider the case where a is a multiple of p nor prove his assertion, only stating for et set proposition, and this proposition is generally true for all series sic and for all prime numbers. I would send you a demonstration of it, if I did not fear going on for Euler provided the first published proof in 1736, in a paper titled Theorematum Corundam ad numeros primos spectantium demonstratio, in the proceedings of the St. Petersburg Academy 6, but Leibniz had given virtually the same proof in an unpublished manuscript from some The term, Fermat's-Little theorem, was probably first used in print in 1913 in Furjet and like Grupp. There is a fundamental theorem holding in every finite group, usually called Fermat's-Little theorem because Fermat was the first to have proved a very an early use in English occurs in Albert's modern. Some mathematicians independently made the related hypothesis. Several proofs of Fermat's-Little theorem are known. It is frequently proved as a corollary of Euler's theorem. Generalizations edit. Euler's theorem is a generalization of Fermat's-Little theorem. For any modulus n and any integer a coprime to n, one has, where phi, n, denotes Euler's totient function, which counts the integers from 1 to n that are coprime to n. Fermat's-Little theorem is indeed a special case, because if n is a prime number, then phi, n, equals n. A corollary of Euler's theorem is, for every positive integer n, if the integer a is coprime with n then, for any integers x and y. This follows from Euler's theorem, since, if mod, then x equals y plus k phi, n, for some integer k, and one has, if n is prime. This is also a corollary of Fermat's-Little theorem. This is widely used in modular arithmetic, because this allows reducing modular exponentiation with large exponents to exponents smaller than n. Euler's theorem is used with n not prime in public key cryptography, specifically in the RSA crypto system, typically in the following way: 8 if retrieving x from the values of y, e, and n is easy if one knows phi, n. 9 In fact, the extended Euclidean algorithm allows computing the modular inverse of e modulo phi, n, that is the integer f such that 1 mod. It follows that, on the other hand, if n equals pq is the product of two distinct prime numbers, then phi, n, equals p1, q1. In this case, finding f from n and e is as difficult as computing phi, n. This has not been proven, but no algorithm is known for computing f without knowing phi, n. Knowing only n, the computation of phi, n, has essentially the same difficulty as the factorization of n, since phi, n, equals p1, q1, and conversely, the factors p and q are the integer solutions of the equation x2, n phi, n, plus 1, x plus n equals 0. The Fermat's-Little theorem is also related to the Carmichael function and Carmichael's theorem, as well as to Lagrange's theorem in group theory. Converse edit. The converse of Fermat's-Little theorem is not generally true, as it fails for Carmichael numbers. However, a slightly stronger form of the theorem is true, and it is known as Lemmer's theorem. The theorem is as follows. If there exists an integer as such that, and for all primes q dividing p1 one has, then p is prime. This theorem forms the base. Euler's theorem. In number theory, Euler's theorem, also known as the Fermat-Euler theorem or Euler's totient theorem, states that, if n and n are coprime positive integers, and is Euler's totient function, then a raised to the power, is congruent to 1 modulo n, that is, in 1736, Leonard Euler published a proof of Fermat's-Little theorem 1, stated by Fermat without proof, which is the restriction of Euler's theorem to the case where n is a prime number. Subsequently, Euler presented other proofs of the theorem, culminating with his paper of 1763, in which he proved a generalization to the case where n is not prime 2. The converse of Euler's theorem is also true. If the above congruence is true, then and must be coprime. The theorem may be used to easily reduce large powers modulo. For example, consider finding the ones place decimal digit of 7, 222, i.e. 7, 222, mod 10. The integers 7 and 10 are coprime, and 10 equals 4. So Euler's theorem yields 7, 4, 1, mod 10, and we get 7, 222, 7, 4 times 55 plus 2, 7. In general, when reducing a power of modulo, where and are coprime, one needs to work modulo in the exponent of. Euler's theorem underlies the RSA crypto system, which is widely used in internet communications. In this crypto system, Euler's theorem is used with n being a product of two large prime numbers, and the security of the system is based on the difficulty of factoring such an proof said it. 1. Euler's theorem can be proven using concepts from the theory of groups. 3. The residue classes modulo n that are coprime to n form a group under multiplication. See the article multiplicative group of integers modulo n for details. The order of that group is phi, n. Lagrange's theorem states that the order of any subgroup of a finite group divides the order of the entire group, in this case phi, n. If a is any number coprime to n, then a is in one of these residue classes, and its powers a 2, ak modulo n form a subgroup of the group of residue classes, with ak1, mod n. Lagrange's theorem says k must divide phi, n, i.e. there is an integer m such that km equals phi, n. This then implies 2. There is also a direct proof for 5. Let r equals x1, x2, x phi, n, be a reduced residue system, mod n, and let a be any integer coprime to n. The proof hinges on the fundamental fact that multiplication by a permits the 11. In other words, if x j x mod n, then j equals. This law of cancellation is proved in the article multiplicative group of integers modulo n6. That is, the sets R and A are equals x1, x2, x, n, considered as sets of congruence classes, mod n, are identical. As sets they may be listed in different orders, so the product of all the numbers in R is congruent, mod n, to the product of all the numbers in A R. See also edit. Carmichael function. Euler's criterion. Fermat's-Little theorem. Wilson's theorem. Notes edit. C. Leonard Euler. Extended Euclidean algorithm. In arithmetic and computer programming, the extended Euclidean algorithm is an extension to the Euclidean algorithm and computes, in addition to the greatest common divisor, GCD, of integers a and b, also the coefficients of Bezout's identity, which are integers x and y such that this is a certifying algorithm, because the GCD is the only number that can simultaneously satisfy this equation and divide the inputs. It allows one to compute also, with almost no extra cost, the quotients of a and b by their greatest common divisor. Extended Euclidean algorithm also refers to a very similar algorithm for computing the polynomial greatest common divisor and the coefficients of Bezout's identity of two univariate polynomials. The extended Euclidean algorithm is particularly useful when a and b are coprime. With that provision, x is the modular multiplicative inverse of a modulo b, and y is the modular multiplicative inverse of b modulo a. Similarly, the polynomial extended Euclidean algorithm allows one to compute the multiplicative inverse in algebraic field extensions and, in particular in finite fields of non-prime. It follows that both extended Euclidean algorithms are widely used in cryptography. In particular, the computation of the modular multiplicative inverse is an essential step in the derivation of key pairs in the RSA public key encryption method. Description edit. The standard Euclidean algorithm proceeds by a succession of Euclidean divisions whose quotients are not used. Only the remainders are kept. For the extended algorithm, the successive quotients are used. More precisely, the standard Euclidean algorithm with a and b as input consists of computing a sequence 1 of quotients and a sequence 0 plus 1 of remainders such that it is the main property of Euclidean division that the inequalities on the right define uniquely and plus 1 from 1 and the computation stops when 1 reaches a remainder plus 1, which is 0. The greatest common divisor is then the last non-zero remainder. The extended Euclidean algorithm proceeds similarly, but adds two other sequences as follows. The computation also stops when plus 1 equals 0 and give is the Bezout coefficients are and that is the quotients of a and b by their greatest common divisor are given by plus. Moreover, if a and b are both positive and g 4 0 less than or equal to. This implies that the pair of Bezout's coefficients provided by the extended Euclidean algorithm is the minimal pair of Bezout coefficients, as being the unique pair satisfying both above inequalities. Also, it means that the algorithm can be done without integer overflow by a computer program using integers of a fixed size that is larger than that of a and b. The following table shows how the extended Euclidean algorithm proceeds with input 240 and 46. The greatest common divisor is the last non-zero entry, 2 in the column remainder. The computation stops at row 6, because the remainder in it is 0. Bezout. In fact, it is easy to verify that 9 Bezout coefficients appear in the last two entries of the second to last row. In fact, it is easy to verify that 9 times 240 plus 47 times 46 equals 2. Finally, the last two entries 23 and 120 of the last row are, up to the sign, the quotients of the input 46 and 240 by the greatest common divisor 2 as 0 less than or equal to plus 1. Thus it must stop with sum plus 1 equals 0. This proves that the algorithm stops eventually as plus 1 equals 1. The greatest common divisor is the same for 1 and plus 1. This shows that the greatest common divisor of the input equals 0 equals 1 is the same as that of plus 1 equals 0. This proves that is the greatest common divisor of a and b. Until this point, the proof is the same as that of the classical Euclidean algorithm as equals 0 and equals 1. We have plus equals for I equals 0 and 1. The relation follows by induction for all 1. Thus, and are Bezout coefficients. Consider the matrix. The recurrence relation may be rewritten in matrix form. The matrix 1 is the identity matrix and its determinant is 1. The determinant of the rightmost matrix in the preceding formula is 1. It follows that the determinant of is 1, 1. In particular, for equals plus 1, we have plus 1 equals 1. Viewing this as a Bezout's identity, this shows that plus 1 and plus 1 are coprime. The relation plus 1 equals 0. That has been proved above in Euclid's lemma show that plus 1 divides b, that is that equals plus 1 for some integer d, dividing by plus 1. The relation plus 1 equals 0 gives equals plus 1. So, plus 1 and plus 1 are coprime integers that are the quotients of a and b by a common factor, which is thus their greatest common divisor or its opposite. To prove the last assertion, assume that a and b are both positive and GCD is not equal to min, then is not equal to, and if quadratic arithmetic programs from 0 to hero. There has been a lot of interest lately in the technology behind ZK snarks, and people are increasingly trying to demystify something that many have come to call moon math due to its perceived sheer indecipherable complexity. ZK snarks are indeed quite challenging to grasp, especially due to the sheer number of moving parts that need to come together for the whole thing to work. But if we break the technology down piece by piece, then comprehending it becomes simple. The purpose of this post is not to serve as a full introduction to ZK snarks. It assumes as background knowledge that you know what ZK snarks are and what they do, and 2. Know enough math to be able to reason about things like polynomials. If the statement p x plus q x equals p plus q x, where p and q are polynomials, seems natural and obvious to you, then you're at the right level. Rather, the post digs deeper into the machinery behind the technology, and tries to explain as well as possible the first half of the pipeline, as drawn by ZK snark researcher Aaron Trimmer here. The steps here can be broken up into two halves. First, ZK snarks cannot be applied to any computational problem directly. Rather, you have to convert the problem into the right form for the problem to operate. The form is called a quadratic arithmetic program, QAP, and transforming the code of a function into one of these is itself highly non-trivial. Along with the process for converting the code of a function into a QAP is another process that can be run alongside so that if you have an input to the code you can create a corresponding solution, sometimes called witness to the QAP. After this, there is another fairly intricate process for creating the actual zero-knowledge proof for this witness, and a separate process for verifying a proof that someone else passes along to you, but these are details that are out of scope for this post. The example that we will choose is a simple one, proving that you know the solution to a cubic equation, x3 plus x plus 5 equals 35. Hint, the answer is 3. This problem is simple enough that the resulting QAP will not be so large as to be intimidating, but non-trivial enough that you can see all of the machinery come into play. Let us write out our function as follows. Def keval, xy equals x3 return x plus y plus 5. The simple special-purpose programming language that we are using here supports basic arithmetic, plus, dash, slash, constant power exponentiation, x7 but not xy, and variable assignment, which is powerful enough that you can theoretically do any computation inside of it, as long as the number of computational steps is bounded. No loops allowed. Note that modulo, percent, and comparison operators, less than or equal to, greater than or equal to, are not supported, as there is no efficient way to do modulo or comparison directly in finite cyclic group arithmetic. Be thankful for this. If there was a way to do either one, then elliptic curve cryptography would be broken faster than you can say binary search and Chinese remainder theorem. You can extend the language to modulo and comparisons by providing bit decompositions, e.g. 13 equals 2 3 plus 2 2 plus 1, as auxiliary inputs, proving correctness of those decompositions and doing the math in binary circuits. In finite field arithmetic, doing equality, equals checks is also doable and in fact a bit easier, but these are both details we won't get into right now. We can extend the language to support conditionals, e.g. if x. Let us now go through this process step by step. If you want to do this yourself for any piece of code, I implemented a compiler here, for educational purposes only, not ready for making QAPs for real-world ZK snarks quite yet. The first step is a flattening procedure, where we convert the original code, which may contain arbitrarily complex statements and expressions, into a sequence of statements that are of two forms x equals y, where y can be a variable or a number, and x equals y, op, z, where op can be plus, dash, asterisk, slash, and y and z can be variables, numbers or themselves sub-expressions. You can think of each of these statements as being kind of like logic gates in a circuit. The result of the flattening process for the above code is as follows. Sim underscore 1 equals x asterisk xy equals sim underscore 1 asterisk x sym underscore 2 equals y plus x out equals sim underscore 2 plus 5. If you read gates to R1CS. Now, we convert this gates to R1CS. If you read the original code and the code here, you can fairly easily see that the two are equivalent. Gates to R1CS. Now, we convert this into something called a rank 1 constraint system, R1CS. An R1CS is a sequence of groups of three vectors, A, B, C, and the solution to an R1CS is a vector S, where S must satisfy the equation S. A asterisk S, B, S. C equals 0, where represents the dot product. In simpler terms, if we zip together A and S, multiplying the two values in the same positions, and then take the sum of these products, then do the same to B and S and then C and S, then the third result equals the product of the first two result. For example, this is a satisfied R1CS. But instead of having just one constraint, we are going to have many constraints, one for each logic gate. There is a standard way of converting a logic gate into A, B, C, triple depending on what the operation is, plus, dash, asterisk, or slash, and whether the arguments are variables or numbers. The length of each vector is equal to the total number of variables in the system, including a dummy variable 1 at the first index representing the number 1, the input variables, a dummy variable out representing the output, and then all of the intermediate variables, sim1 and sim2 above. The vectors are generally going to be very sparse, only filling in the slots corresponding to the variables that are affected by some particular logic gate. First, we'll provide the variable mapping that we'll use. 1, x, out, sim underscore 1, y. The solution vector will consist of assignments for all of these variables, in that order. Now, we'll give the A, B, C, triple for the first gate. A equals 0, 1, 0, 0, 0. You can see that if the solution vector contains 3 in the second position, and 9 in the fourth position, then regardless of the rest of the contents of the solution vector, the dot product check will boil down to 3 asterisk 3 equals 9, and so it will pass. If the solution vector has -3 in the second position and 9 in the fourth position, the check will also pass. In fact, if the solution vector has 7 in the second position and 49 in the fourth position, then that check will still pass. The purpose of this first check is to verify the consistency of the inputs and outputs of the first gate only. Now, let's go on to the second gate. A equals 0, 0, 0, 1, 0. In a similar style to the first dot product check, here we're checking that sim underscore 1 asterisk x equals y equals 0, 1, 0, 0, 1, 0. Here, the pattern is somewhat different. It's multiplying the first element in the solution vector by the second element, then by the fifth element, adding the two results, and checking if the sum equals the sixth element. Because the first element in the solution vector is always 1, this is just an addition check, checking that the output equals the sum of the two input. Finally, the fourth gate. A equals 5, 0, 0, 0. Here, we're evaluating the last check, out equals sim underscore 2 plus 5. The dot product check works by taking the sixth element in the solution vector, adding 5 times the first element. Reminder, the first element is 1, so this effectively means adding 5, and checking it against the third element, which is where we store the output variable. And there we have our R1CS with 4 constraints. The witness is simply the assignment to all the variables, including input, output, and internal variables. 1, 3, 35. You can compute this for yourself by simply executing the flattened code above, starting off with the input variable assignment x equals 3, and putting in the values of all the intermediate variables in the output as you compute them. The complete R1CS put together is 0, 1, 0, 0, 0, 0, 0, 0. The next step is taking this R1CS and converting it into QAP form, which implements the exact same logic except using polynomials instead of dot product. We do this as follows. We go from 4 groups of 3 vectors of length 6 to 6 groups of 3 degree 3 polynomials, where evaluating the polynomials at each x coordinate represents one of the constraints. That is, if we evaluate the polynomials at x equals 1, then we get our first set of vectors. If we evaluate the polynomials at x equals 2, then we get our second set of vectors, and so on. We can make this transformation using something called a Lagrange interpolation. The problem that a Lagrange interpolation solves is this: if you have a set of points, I, x, y, coordinate pairs, then doing a Lagrange interpolation on those points gives you a polynomial that passes through all of those points. We do this by decomposing the problem. For each x coordinate, we create a polynomial that has the desired y coordinate at that x coordinate and a y coordinate of 0 at all the other x coordinates we are interested in, and then to get the final result we add all of the polynomials together. Let's do an example. Suppose that we want a polynomial that passes through 1, 3, 2, 2, and 3, 4. We start off by making a polynomial that passes through 1, 3, 2, 0, and 3, 0. As it turns out, making a polynomial that sticks out at x equals 1 and is 0 at the other points of interest is easy. We simply do x, 2, asterisk, x, 3, which looks like this. Now, we just need to rescale it so that the height at x equals 1 is right. x, 2, asterisk, x, 3, asterisk 3 slash, 1 to 2, asterisk, 1 to 3. This gives us 1.5 asterisk x2, 7.5 asterisk x plus 9. We then do the same with the other 2 points, and get 2 other similar looking polynomials, except that they stick out at x equals 2 and x equals 3 instead of x equals 1. We add all 3 together and get 1.5 asterisk x2, 5.5 asterisk x plus 7, with exactly the coordinates that we want. The algorithm as described above takes O, n3, time, as there are endpoints and each point requires O, n2, time to multiply the polynomials together. With a little thinking, this can be reduced to O, n2, time, and with a lot more thinking, using fast Fourier transform algorithms and the like, it can be reduced even further. A crucial optimization when functions that get used in zk snarks in practice often have many thousands of gates. Now, let's use Lagrange interpolation to transform our R1CS. What we are going to do is take the first value out of every vector, use Lagrange interpolation to make a polynomial out of that, where evaluating the polynomial at I gets you the first value of the ith vector, repeat the process for the first value of every b and c vector, and then repeat that process for the second values, the third, values, and so on. For convenience I'll provide the answers right now. A polynomial is -5.0, 9.166. Coefficients are in ascending order, so the first polynomial above is actually 0.833 asterisk x35 x2 plus 9.166 x, 5. This set of polynomials, plus a z polynomial that I will explain later, makes up the parameters for this particular QAP instant. Note that all of the work up until this point needs to be done only once for every function that you are trying to use zk snarks to verify. Once the QAP parameters are generated, they can be reused. Let's try evaluating all of these polynomials at x equals 1. Evaluating a polynomial at x equals 1 simply means adding up all the coefficients, as 1k equals 1 for all k, so it's not difficult. We get a result at x equals 1, 0, 1, and lo and behold, what we have here is exactly the same as the set of 3 vectors for the first logic gate that we created above. Now what's the point of this crazy transformation? The answer is that instead of checking the constraints in the R1CS individually, we can now check all of the constraints at the same time by doing the dot product check on the polynomial, because in this case the dot product check is a series of additions and multiplications of polynomials. The result is itself going to be a polynomial. If the resulting polynomial, evaluated at every x coordinate that we used above to represent a logic gate, is equal to 0, then that means that all of the checks pass. If the resulting polynomial evaluated at least one of the x coordinate representing a logic gate gives a non-zero value, then that means that the values going into and out of that logic gate are inconsistent. The gate is y equals x asterisk sim underscore 1, but the provided values might be x equals 2 sim underscore 1 equals 2 and y equals 5. Note that the resulting polynomial does not itself have to be 0, and in fact in most cases won't be. It could have any behavior at the points that don't correspond to any logic gates, as long as the result is 0 at all the points that do correspond to some gate. To check correctness, we don't actually evaluate the polynomial t equals a, s asterisk b, s, c. S at every point correspond. Z is defined as x, s at every point corresponding to a gate. Instead, we divide t by another polynomial, z, and check that z evenly divides t. That is, the division t slash z leaves no remain. Z is defined as x, 1, asterisk, x, 2, asterisk, x, 3. The simplest polynomial that is equal to 0 at all points that correspond to logic gates. It is an elementary fact of algebra that any polynomial that is equal to 0 at all of these points has to be a multiple of this minimal polynomial, and if a polynomial is a multiple of z then its evaluation at any of those points will be 0. This equivalence makes our job much easier. Now, let's actually do the dot product check with the polynomials above. First, the intermediate polynomials. A. S equals -3.0, 10.33, s equals -41 points. Now, a. S asterisk b. SC, S. T equals -88.0, 592.666, minus 1063.777, 805.833, minus 294.777. Now, the minimal polynomial z equals x, 1, asterisk, x, 2, asterisk, x, z equals 24, minus 50. And if we divide the result above by z, we get h equals t slash z equals -3.660, and so we have the solution for the QAP. If we try to falsify any of the variables in the R1CS solution that we are deriving this QAP solution from, say, set the last one to 31 instead of 30, then we get a t polynomial that fails one of the checks. In that particular case, the result at x equals 3 would equal -1 instead of 0, and furthermore t would not be a multiple of z. Rather, dividing t slash z would give a remainder of -5.0, 8.8. Note that the above is a simplification. In the real world, the addition, multiplication, subtraction, and division will happen not with regular numbers, but rather with finite field elements, a spooky kind of arithmetic which is self-consistent. So all the algebraic laws we know and love still hold true, but where all answers are elements of some finite-sized set, usually integers within the range from 0 to n1 for some. For example, if n equals 13, then 1 slash 2 equals 7, and 7 asterisk 2 equals 1, 3 asterisk 5 equals 2, and so forth. Using finite field arithmetic removes the need to worry about rounding errors and allows the system to work nicely with elliptic curves, which end up being necessary for the rest of the zk snark machinery that makes the zk snark protocol actually secure. Special thanks to Aaron Trimmer for helping to explain many details about the inner workings of zk snarks to me. Proto-Danks Harding FAQ. Proto-Danks Harding FAQ. What is Danks Harding? What is Proto-Danks Harding, aka EIP4844? Why is it okay to add 1 megabyte data to blocks that everyone has to download, but not to just make call data 10x? How does Proto-Danks Harding, EIP4844, compare to EIP4488? What parts of full Danks Harding does Proto-Danks Harding implement? What is Danks Harding? Danks Harding is the new sharding design proposed for Ethereum, which introduces some significant simplifications compared to previous design. The main difference between all recent Ethereum sharding proposals since 2020, both Danks Harding and pre-Danks Harding, and most non-Ethereum sharding proposals is Ethereum's roll-up-centric roadmap. See also, 1, 2, 3. Instead of providing more space for transactions, Ethereum sharding provides more space for blobs of data, which the Ethereum protocol itself does not attempt to interpret. Verifying a blob simply requires checking that the blob is available, that it can be downloaded from the network. The data space in these blobs is expected to be used by layer 2 rollup protocols that support high-throughput transaction. The main innovation introduced by Danks Harding, see also, 1, 2, 3, is the merged fee market. Instead of there being a fixed number of shards that each have distinct blocks and distinct block proposers, in Danks Harding there is only one proposer that chooses all transactions and all data that go into that slot. To avoid this design forcing high system requirements on validators, we introduced proposer/builder separation, PBS. See also, 1, 2. A specialized class of actors called block builders bid on the right to choose the contents of the slot, and the proposer need only select the valid header with the highest bid. Only the block builder needs to process the entire block, and even there, it's possible to use third-party decentralized Oracle protocols to implement a distributed block builder. All other validators and users can verify the blocks very efficiently through data availability sampling. Remember, the big part of the block is just data. What is Proto-Danks Harding, aka EIP4844? Proto-Danks Harding, aka EIP4844, is a proposal to implement most of the logic and scaffolding, e.g. transaction formats, verification rules, that make up a full Danks Harding spec, but not yet actually implementing any shard. In a Proto-Danks Harding implementation, all validators and users still have to directly validate the availability of the full data. The main feature introduced by Proto-Danks Harding is new transaction type, which we call a blob carrying transaction. A blob carrying transaction is like a regular transaction, except it also carries an extra piece of data called a blob. Blobs are extremely large, 125 KB, and can be much cheaper than similar amounts of call data. However, blob data is not accessible to EVM execution. The EVM can only view a commitment to the blob. Because validators and clients still have to download full blob contents, data bandwidth in Proto-Danks Harding is targeted to 1 megabyte per slot instead of the full 6. However, there are nevertheless large scalability gains because this data is not competing with the gas usage of existing Ethereum transactions. Why is it okay to add 1 megabyte data to blocks that everyone has to download, but not to just make call data 10x? This has to do with the difference between average load and worst case load. Today, we already have a situation where the average block size is about 90 KB, but the theoretical maximum possible block size, if all 30 M gas in a block went to call data, is 1.8 M. The Ethereum network has handled blocks approaching the maximum in the past. However, if we simply reduce the call data gas cost by 10x, then although the average block size would increase to still acceptable levels, the worst case would become 18 megabytes, which is far too much for the Ethereum network to handle. The current gas pricing scheme makes it impossible to separate these two factors. The ratio between average load and worst case load is determined by users' choices of how much gas they spend on call data vs other resources, which means that gas prices have to be set based on worst case possibilities, leading to an average load needlessly lower than what the system can handle. But if we change gas pricing to more explicitly create a multidimensional fee market, we can avoid the average case/worst case load mismatch and include in each block close to the maximum amount of data that we can safely handle. Proto-Danks Harding and EIP4488 are two proposals that do exactly that. Average case block size. How does Proto-Danks Harding, EIP4844, compare to EIP4488? EIP4488 is an earlier and simpler attempt to solve the same average case/worst case load mismatch problem. EIP4488 did this with two simple rules. Call data gas cost reduced from 16 gas per byte to 3 gas per byte. A limit of 1 megabyte per block plus an extra 300 bytes per transaction. Theoretical max, 1.4 MB. The hard limit is the simplest possible way to ensure that the larger increase in average caseload would not also lead to an increase in worst case load. The reduction in gas cost would greatly increase rollup use, likely increasing average block size to hundreds of kilobytes, but the worst case possibility of single blocks containing 10 megabytes would be directly prevented by the hard limit. In fact, the worst case block size would be lower than it is today, 1.4 megabytes vs 1.8 megabytes. Proto-Danks Harding instead creates a separate transaction type that can hold cheaper data in large fixed-size blobs, with a limit on how many blobs can be included per blob. These blobs are not accessible from the EVM, only commitments to the blobs are, and the blobs are stored by the consensus layer, beacon chain, instead of the execution. The main practical difference between EIP4488 and Proto-Danks Harding is that EIP4488 attempts to minimize the changes needed today, whereas Proto-Danks Harding makes a larger number of changes today so that few changes are required in the future to upgrade to full shard. Although implementing full sharding, with data availability sampling, etc., is a complex task and remains a complex task after Proto-Danks Harding, this complexity is contained to the consensus layer. Once Proto-Danks Harding is rolled out, execution layer client teams, roll-up developers, and users need to do no further work to finish the transition to full shard. Proto-Danks Harding also separates blob data from call data, making it easier for clients to store blob data for a shorter period of time. Note that the choice between the two is not an either-or. We could implement EIP4488 soon and then follow it up with Proto-Danks Harding half a year later. What parts of full Danks Harding does Proto-Danks Harding implement, and what remains to be implemented? Quoting EIP4844. The work that is already done in this EIP includes a new transaction type, of the exact same format that will need to exist in full sharding. All of the execution layer logic required for full shard. All of the execution/consensus cross-verification logic required for full sharding. Layer separation between beacon block verification and data availability sampling blob. Most of the beacon block logic required for full sharding. A self-adjusting independent gas price for blobs. The work that remains to be done to get to full sharding includes a low-degree extension of the blob_KZGS in the consensus layer to allow 2D sampling. An actual implementation of data availability sampling. PBS, proposer/builder separation, to avoid requiring individual validators to process 32 megabytes of data in one slot. Proof of custody or similar in protocol requirement for each validator to verify a particular part of the sharded data in each block. Notice that all of the remaining work is consensus layer changes, and does not require any additional work from execution client teams, users, or roll-up developer. What about disk space requirements blowing up from all these really big blocks? Both EIP4488 and Proto-Danks Harding lead to a long-run maximum usage of 1 MB per slot, 12s. This works out to about 2.5 TB per year, a far higher growth rate than Ethereum requires today. In the case of EIP4488, solving this requires history expiry, EIP4444, where clients are no longer required to store history older than some duration of time. Durations from 1 month to 1 year have been proposed. In the case of Proto-Danks Harding, the consensus layer can implement separate logic to auto-delete the blob data after some time, e.g. 30 days, regardless of whether or not EIP4444 is implemented. However, implementing EIP4444 as soon as possible is highly recommended regardless of what short-term data scaling solution is adopted. In the long run, adopting some both strategies limit the extra disk load of a consensus client to at most a few hundred gigabytes. In the long run, adopting some history expiry mechanism is essentially mandatory. Full sharding would add about 40 TB of historical blob data per year, so users could only realistically store a small portion of it for some time. Hence, it's worth setting the expectations about this sooner. If data is deleted after 30 days, how would users access older blobs? The purpose of the Ethereum consensus protocol is not to guarantee storage of all historical data for it. Rather, the purpose is to provide a highly secure real-time bulletin board and leave room for other decentralized protocols to do longer-term storage. The bulletin board is there to make sure that the data being published on the board is available long enough that any user who wants that data, or any longer-term protocol backing up the data, has plenty of time to grab the data and import it into their other application or protocol. In general, long-term historical storage is easy. While 2.5 TB per year is too much to demand of regular nodes, it's very manageable for dedicated users. You can buy very big hard drives for about $20 per terabyte, well within reach of a hobbyist. Unlike consensus, which has a n/2 of ntrust model, historical storage has a 1 of ntrust model. You only need one of the storers of the data to be on it. Hence, each piece of historical data only needs to be stored hundreds of times, and not the full set of many thousands of nodes that are doing real-time consensus verification. Some practical ways in which the full history will be stored and made easily accessible include application-specific protocols, e.g. rollups, can require their nodes to store the portion of history that is relevant to their application. Historical data being lost is not a risk to the protocol, only to individual applications, so it makes sense for applications to take on the burden of storing data relevant to themselves. Storing historical data in BitTorrent, e.g. auto-generating and distributing a 7 GB file containing the blob data from the blocks in each day. The Ethereum portal network, currently under development, can easily be extended to store history. Block explorers, API providers, and other data services will likely store the full history. Individual hobbyists and academics doing data analysis will likely store the full history. In the latter case, storing history locally provides them significant value as it makes it much easier to directly do calculations on it. Third-party indexing protocols like the Graph will likely store the full history at much higher levels of history storage, e.g. 500 TB per year. The risk that some data will be forgotten becomes higher, and additionally, the data availability verification system becomes more strained. This is likely the true limit of sharded blockchain scalability. However, all current proposed parameters are very far from reaching this point. What format is blob data and how is it committed to? A blob is a vector of 4096 field elements, numbers within the range 0. The blob is mathematically treated as representing a degree. Omega is a constant that satisfies omega 4096 equals 1 omega 4096 equals 1 omega 4096 equals 1. A commitment to a blob is a hash of the KZG commitment to the polynomial. From the point of view of implementation, however, it is not important to be concerned with the mathematical details of the polynomial. Instead, there will simply be a vector of elliptic curve points, the Lagrange basis trusted setup, and the KZG commitment to a blob will simply be a linear combination. Quoting code from EIP 4844. Def blob _to _KZG, blob, vector BLS field element, 4096, KZG commitment. Computed _KZG equals BLS.Z1. For value, point _KZG in zip, tx.blob, KZG setup Lagrange. Assert value. BLS _modulus is the above modulus, and KZG setup Lagrange is the vector of elliptic curve points that is the Lagrange basis trusted setup. For implementers, it's reasonable to simply think of this for now as a black box special purpose hash function. Why use the hash of the KZG instead of the KZG directly? Instead of using the KZG to represent the blob directly, EIP 4844 uses the version hash, a single 0x01 byte, representing the version, followed by the last 31 bytes of the SHA-256 hash of the KZG. This is done for EVM compatibility and future compatibility. KZG commitments are 48 bytes whereas the EVM works more naturally with 32 byte values, and if we ever switch from KZG to something else, for quantum resistance reasons, the commitments can continue to be 32 bytes. What are the two precompiles introduced in Proto-Danks Harding? Proto-Danks Harding introduces two precompiles, the blob verification precompile and the point evaluation precompile. The blob verification precompile is self-explanatory. It takes as input a version hash in a blob, and verifies that the provided version hash actually is a valid version hash for the blob. This precompile is intended to be used by optimistic rollups. Quoting EIP 4844. Optimistic rollups only need to actually provide the underlying data when fraud proofs are being submitted. The fraud proof submission function would require the full contents of the fraudulent blob to be submitted as part of call data. It would use the blob verification function to verify the data against the version hash that was submitted before, and then perform the fraud proof verification on that data as is done to. The point evaluation precompile takes as input a version hash, an x coordinate, a y coordinate in a proof, the KZG commitment of the blob and a KZG proof of evaluation. It verifies the proof to check that p, x, equals y, where p is the polynomial represented by the blob that has the given version hash. This precompile is intended to be used by ZK rollup. Quoting EIP 4844. ZK rollups would provide two commitments to their transaction or state delta data, the KZG and the blob, and some commitment using whatever proof system the ZK rollup uses internally. They would use a commitment proof of equivalence protocol, using the point evaluation precompile, to prove that the KZG, which the protocol ensures points to available data, and the ZK rollup's own commitment refer to the same data. Note that most major optimistic rollup designs use a multi-round fraud proof scheme, where the final round takes only a small amount of data. Hence, optimistic rollups could conceivably also use the point evaluation precompile instead of the blob verification precompile, and it would be cheaper for them to do so. How exactly do ZK rollups work with the KZG commitment efficiently? The naive way check a blob in a ZK rollup is to pass the blob data as a private input into the KZG, and do a elliptic curve linear combination, or a pairing, inside the snark to verify it. This is wrong and needlessly inefficient. Instead, there is a much easier approach in the case where the ZK rollup is BLS 12-381 based, and a moderately easier approach for arbitrary ZK snark. Easy approach requires rollup to use the BLS 12-381 modulus. Suppose KKK is the KZG commitment, and BBB is the blob that it is committing to. All ZK snark protocols have some way to import large amounts of data into a proof, and contain some kind of commitment to that data. For example, in Plunk, this is the QCQCQ_C commitment. All we have to do is prove that KKK and QCQCQ_C are committing to the same data. This can be done with a proof of equivalence, which is very simple, copying from the post. Suppose you have multiple polynomial commitments C1C1C_1, CKCKC_K, under KKK different commitment schemes, e.g. K, Friday, something bulletproof based, dark, and you want to prove that they all commit to the same polynomial PPP. We can prove this easily. Let Z equals hash, C1, CK, Z equals hash, C1, CK, Z equals hash, C_1, C_K, where we interpret ZZZ as an evaluation point at which PPP can be evaluated. Publish openings O1, OKO1, OKO_1, O_K, where OIO_I is a proof that CI, Z, equals ACI, Z, equals AC_I, Z, equals A under the ITH commitment scheme. Verify that AAA is the same number in all cases. A ZK rollup transaction would simply have to have a regular snark, as well as a proof of equivalence of this kind to prove that its public data equals the version hash. Note that they should not implement the KZG check directly. Instead, they should just use the point evaluation precompile to verify the opening. This ensures future proofness. If later KZG is replaced with something else, the ZK rollup would be able to continue working with no further issues. Moderate approach works with any ZK snark. If the destination ZK snark uses some other modulus, or even is not polynomial based at all, e.g. it uses R1CS, there is a slightly more complicated approach that can prove equivalent. The proof works as follows. Let P, X, P, X, P, X be the polynomial encoded by the blob. Make a commitment QQQ in the ZK snark scheme that encodes the values V1 VN V1 VN V_1. v underscore n, where 6 equals p, omega. Choose triple x by hashing the commitment of PPP and QQQ. Prove p, x, p, x, p, x, with the point evaluation precompile. Use the barycentric equation p, x, equals xn1 and sigma ivii xip, x, equals xn1 and sigma ivii xip, x, equals backslash frac x caret n, 1 n asterisk backslash sum underscore I backslash frac v underscore I asterisk backslash omega caret I x, backslash omega caret I to perform the same evaluation inside the zk. Verify that the answer is the same as the value proven in 3. 4 will need to be done with mismatched field arithmetic, but lookup-style techniques can do this with fewer constraints than even an arithmetically friendly hash function. Note that xn1 and xn1 and backslash frac x caret n, 1 n and omega I backslash omega caret I can be precomputed and saved to make the calculation simpler. For a longer description of this protocol, see what does the KZG trusted setup look like? https://bit.ly.ca/general/2022/033/14/trustedzetop.html for a general description of how powers of tau trusted setups work. https://github.com/e3um/research/blob/master/trusted_setup/trusted_setup.py for an example implementation of all of the important trusted setup related computation. In our case in particular, the current plan is to run in parallel 4 ceremonies with different secrets, with sizes, n1 equals 4096 and 2 equals 16, n1 equals 4096 and 2 equals 16, n underscore 1 equals 4096, n underscore 2 equals 16, n1 equals 8192 and 2 equals 16, n1 equals 8192 and 2 equals 16, n underscore 1 equals 8192, n underscore 2 equals 16, n1 equals 16384 and 2 equals 16, n1 equals 16384 and 2 equals 16, n underscore 1 equals 16384, n underscore 2 equals 16, and n1 equals 32768 and 2 equals 16, n1 equals 32768 and 2 equals 16, n underscore 1 equals 30. Theoretically, only the first is needed, but running more with larger sizes improves future-proofness by allowing us to increase blob size. We can't just have a larger setup, because we want to be able to have a hard limit on the degree of polynomials that can be validly committed to, and this limit is equal to the blob size. The likely practical way to do this would be to start with the Filecoin setup, and then run a ceremony to extend it. Multiple implementations, including a browser implementation, would allow many people to participate. Couldn't we use some other commitment scheme without a trusted setup? Unfortunately, using anything other than KZG, e.g., IPA or SHA-256, would make the sharding roadmap much more difficult. This is for a few reasons. Non-arithmetic commitments, e.g. hash functions, are not compatible with data availability sampling, so if we use such a scheme we would have to change to KZG anyway when we move to full shard. IPAs may be compatible with data availability sampling, but it leads to a much more complex scheme with much weaker properties, e.g. self-healing and distributed block building become much harder. Neither hashes nor IPAs are compatible with the cheap implementation of the point evaluation precompile. Hence, a hash or IPA-based implementation would not be able to effectively benefit ZK rollups or support cheap fraud proofs in multi-round optimistic rollup. One way to keep data availability sampling and point evaluation but introduce another commitment is to store multiple commitments, e.g. KZG and SHA-256 per block, but this has the problem that either we need to add a complicated ZKP proof of equivalence, or 2, all consensus nodes would need to verify the second commitment, which would require them to download the full data of all blobs, tens of megabytes per slot. Hence, the functionality losses and complexity increases of using anything but KZG are unfortunately much greater than the risks of KZG itself. Additionally, any KZG-related risks are contained. A KZG failure would only affect rollups and other applications depending on blob data, and leave the rest of the system untouched. How complicated and new is KZG? KZG commitments were introduced in a paper in 2010, and have been used extensively since 2019 in Plunk-style ZK SNARK protocol. However, the underlying math of KZG commitments is a relatively simple piece of arithmetic on top of the underlying math of elliptic curve operations and pairing. The specific curve used is BLS 12-381, which was generated from the Barreto-Linscott family invented in 2002. Elliptic curve pairings, necessary for verifying KZG commitments, are very complex math, but they were invented in the 1940s and applied to cryptography since then. By 2001, there were many proposed cryptographic algorithms that used pairings. From an implementation complexity point of view, KZG is not significantly harder to implement than IPA. The function for computing the commitment, see above, is exactly the same as in the IPA case, just with a different set of elliptic curve point constant. The point verification precompile is more complex, as it involves a pairing evaluation, but the math is identical to a part of what is already done in implementations of EIP 2537, BLS 12-381 precompiles, and very similar to the BN128 pairing precompile. See also, optimized Python implementation. Hence, there is no complicated new work that is required to implement KZG verification. What are the different software parts of a proto-Danks Harding implementation? There are 4 major components. The execution layer consensus changes. See the EIP. For details. New transaction type that contains blobs. A code that outputs the ITH blob version hash in the current transaction. Blob verification precompile. Point evaluation precompile. The consensus layer consensus changes. See this folder in the repo. List of blob KZGs in the beacon block. The sidecar mechanism, where full blob contents are passed along with a separate object from the beacon block. Cross-checking between blob version hashes in the execution layer and blob KZGs in the consensus layer. The mempool. Blob transaction network wrapper. See networking section of the EIP. More robust anti-DOS protections to compensate for large blob sizes. Block building logic. Accept transaction wrappers from the mempool. Put transactions into the execution payload. KZGs into the beacon block and bodies in the sidecar. Deal with the two-dimensional fee mark. Note that for a minimal implementation, we do not need the mempool at all. We can rely on second-layer transaction bundling marketplaces instead, and we only need one client to implement the block building logic. Extensive consensus testing is only required for the execution layer and consensus layer consensus changes, which are relatively lightweight. Anything in between such a minimal implementation and a full rollout where all clients support block production and the mempool is possible. What does the proto-Danks Harding multidimensional fee market look like? Proto-Danks Harding introduces a multidimensional EIP 1559 fee market, where there are 2 resources, gas and blobs, with separate floating gas prices and separate limit. That is, there are 2 variables and 4 constants. Target per block, max per block, base fee, gas, 15 million, 30 million, variable, blob. The blob fee is charged in gas, but it is a variable amount of gas, which adjusts so that in the long run the average number of blobs per block actually equals the target. The two-dimensional nature means that block builders are going to face a harder problem. Instead of simply accepting transactions with the highest priority fee until they either run out of transactions or hit the block gas limit, they would have to simultaneously avoid hitting 2 different limits. Here's an example. Suppose that the gas limit is 70 and the blob limit is 40. The mempool has many transactions, enough to fill the block, of 2 types. TX gas includes the per blob gas. Priority fee 5 per gas, 4 blobs, 4 total gas. Priority fee 3 per gas, 1 blob, 2 total gas. A miner that follows the naive, walk down the priority fee algorithm would fill the entire block with 10 transactions, 40 gas, of the first type, and get a revenue of 5 * 40 equals 200. Because these 10 transactions fill up the blob limit completely, they would not be able to include any more transactions. But the optimal strategy is to take 3 transactions of the first type and 28 of the second type. This gives you a block with 40 blobs and 68 gas, and 5 * 12 plus 3 * 56 equals 228 revenue. Are execution clients going to have to implement complex multidimensional knapsack problem algorithms to optimize their block production? No, for a few reasons. EIP 1559 ensures that most blocks will not hit either limit, so only a few blocks are actually faced with the multidimensional optimization problem. In the usual case where the mempool does not have enough sufficient fee-paying transactions to hit either limit, any miner could just get the optimal revenue by including every transaction that they. Fairly simple heuristics can come close to optimal in practice. See Ansgar's EIP 4488 analysis for some data around this in a similar context. Multidimensional pricing is not even the largest source of revenue gains from specialization. MEV is specialized MEV revenue extractable through specialized algorithms from on-chain DEX arbitrage, liquidations, front-running NFT sales, etc. is a significant fraction of total, naively extractable revenue. Priority fees specialized MEV revenue seems to average around 0.025 ETH per block, and total priority fees are usually around 0.1 ETH per block. Proposer/builder separation is designed around block production being highly specialized. PBS turns the block building process into an auction, where specialized actors can bid for the privilege of creating a block. Regular validators merely need to accept the highest. This was intended to prevent MEV-driven economies of scale from creeping into validator centralization, but it deals with all issues that might make optimal block building hard. For these reasons, the more complicated fee market dynamics do not greatly increase centralization or risks. Indeed, the principle applied more broadly could actually reduce denial of service risk. How does the exponential EIP 1559 blob fee adjustment mechanism work? Today's EIP 1559 adjusts the base fee BBB to achieve a particular target gas use level TTT as follows. Bn plus 1 equals Bn, 1 plus UT8T, where BNB underscore N is the current block space fee, Bn plus 1 B underscore N plus 1 is the next block space fee, TTT is the target and UU is the gas used. The goal is that when U2 2T, so, usage is above the target, the base fee increases, and when U. The fee adjustment mechanism in Proto-Danks Harding accomplishes the exact same goal of targeting a long-run average usage of TTT, and it works in a very similar way, but it fixes a subtle bug in the EIP 1559 approach. Suppose, in EIP 1559, we get two blocks, the first with U equals 0, U equals 0, U equals 0, and the next with U equals 2, 2 equals 2, 2 equals 2T. We get block, despite average use being equal to TTT, the base fee drops by a factor of 6364 /frac 6364. So when block space usage varies block by block, the base fee only stabilizes when usage is a little higher than TTT, in practice apparently about 3% higher, though the exact number depends on the variant. Proto-Danks Harding instead uses a formula based on exponential adjustment. Bn plus 1 equals Bn exp, UT8T, Bn plus 1 equals Bn, exp, x, exp, x, exp, x, is the expo, at small triple x values, exp, x, 1 plus x, x. In fact, the graphs for Proto-Danks Harding adjustment and EIP 1559 adjustment look almost exactly the same. However, the exponential formula has the convenient property that it is transaction displacement independent. The same total usage has the same effect on the base fee, regardless of how it is distributed between different blocks. Copying over the example above, we can see that the exponential formula does in fact fix the issue. Block number. Gas in block. Base fee using EIP 1559 rule. Base fee using Proto-Danks Harding rule. KKK. Triple X. Triple X. K plus 1K. We can see why this is true in the general case as follows. The new base fee BNB underscore N after a multi-step adjustment can be computed as follows. BN EXP, U1T8T. EXP, UNT8T, EXP, UNT8T. But we can re-express this formula a different way. BN EXP, U1T8T, EXP, UNT, EXP, plus UNT8T, plus UNT8T, plus UNT8T, plus UNT8T. And from here we can see that BNB underscore N depends only on the total usage, U1 plus UNU 1 plus UNU underscore 1 plus U underscore N, and not how that usage is distributed. The term, U1 plus on NT, U1 plus on NT, U underscore 1 /+++ U underscore N, NT, can be viewed as the excess, the difference between the total gas actually used and the total gas intended to be used. The fact that the current base fee equals B0 EXP, XS8T, B0 EXP, XS8T, B underscore 0 asterisk EXP, /frac XS8T, makes it really clear that the excess can't go out of a very narrow range. If the excess goes above AT60 asterisk 60, then the base fee becomes E60 E caret 60, which is so absurdly high that no one can pay it, and if it goes below 0 then the resource is basically free and the chain will get spammed until the excess goes back above 0. The adjustment mechanism in Proto-Danks Harding works in exactly these terms. It tracks actual underscore total, U1 plus UNU 1 plus UNU underscore 1 /++ U underscore N, and computes targeted underscore total, NT, and computes the price as an exponential of the difference. To make the computation simpler, instead of using x caret x we use 2x caret x. In fact, we use an approximation of 2x caret x, the fake underscore exponential function in the EIP. The fake exponential is almost always within 0.3% of the actual value. To prevent long periods of underuse from leading to long periods of 2x full blocks, we add an extra feature. We don't let excess go below 0. If actual underscore total ever goes below targeted underscore total, we just set actual underscore total to equal targeted underscore total instead. This does break transaction order invariance in extreme cases, where the blob gas goes all the way down to 0, but this is an acceptable trade-off for the added save. Note also one interesting consequence of this multidimensional market. When Proto-Danks Harding is first introduced, it's likely to have few users initially, and so for some period of time the cost of a blob will almost certainly be extremely cheap, even if regular Ethereum blockchain activity remains expensive. It is the author's opinion that this fee adjustment mechanism is better than the current approach, and so eventually all parts of the EIP 1559 fee market should switch to using it. For a longer and more detailed explanation, see Dankrad's post. Here's the code of fake underscore exponential for convenience. Def fake underscore exponential, numerator, int, denominator, int, dash int. Cofactor equals 2, numerator / denominator. Fractional equals numerator % denominator. Return cofactor plus. Fractional asterisk cofactor asterisk 2 plus. Fractional 2 asterisk cofactor / denominator. / denominator asterisk 3. Here at the core mechanism re-expressed in math, with rounding removed. Fake exp, x, equals 2xq, xx. Fake exp, x, equals 2xq, xx. Q, x, equals 1 plus 2 3x plus 1 3x 2q. The goal is to splice together many instances of q, x, q, x, q, x. 1 shifted and scaled up appropriately for each 2k plus 1 2k 2k plus 1 2 caret k. 2 caret k plus 1 range. Q, x, q, x, q, x. Itself is an approximation of 2x 2x 2 caret x for 0 less than or equal to x less than or equal to 10 less than or equal to x less than or equal to 10 \lex \le1, chosen for the following properties. Simplicity, it's a quadratic equation. Correctness on the left edge, q0 equals 20 equals 1. Correctness on the right edge, q1 equals smooth slope. We ensure q1 equals 2q0, q1 equals 2q0, q1 equals 2 asterisk q0, so that each shifted plus scaled copy of qqq has the same slope on its right edge as the next copy has on its left edge. The last three requirements give three linear equations and three unknown coefficients, and the above given q, x, q, x, q, x gives the only solution. The fake underscore exponential. The approximation works surprisingly well. For all but the smallest inputs, fake underscore exponential gives answers within 0.3% of the actual value of 2x caret x. Fake underscore exponential. Blue. vs actual value of 2x. Fake underscore exponential divided by actual value of 2x caret x for 5 less than or equal. What are some questions in proto-Danks Harding that are still being debated? Note, this section can very easily become out of date. Do not trust it to give the latest thought on any particular issue. All major optimistic rollups use multi-round proofs, and so they can work with the much cheaper point evaluation precompile instead of the blob verification precompile. Anyone who really needs blob verification could implement it themselves. Take as input the blob DDD and the version #HHH. Choose x equals hash DH, x equals hash DH, x equals hash DH. Use barycentric evaluation to compute y equals D, x, y equals D, x, y equals D, x, and use the point evaluation precompile to verify h, x equals yeah, x equals yeah, x equals. Hence, do we really need the blob verification precompile or could we just remove it and only use point evaluation? How well can the chain handle persistent long-term 1 MB plus block? If it's too risky, should the target blob count be reduced at the beginning? Should blobs be priced in gas or in eth that gets burned? Are there other adjustments to the fee market that should be made? Should the new transaction type be treated as a blob or an SSC object? In the latter case, changing execution payload to a union type. This is a more work now vs more work later trade-off. Exact details of the trusted setup implementation, technically outside the scope of the EIP itself, is for implementers. The setup is just a constant, but it still needs to be done.
Casper the friendly finality gadget, Vitalik Buterin and Virgil.
Never used this one for reading PDFs. So. I'm going to go eat something and then I'm gonna read these documents while I eat. I think I'm gonna put them on a file. Because there's a bunch of stuff about arbitrage DAX here. I don't remember which one is this, but I guess I'm gonna read it as well. I'm going to have to study the math a lot more to understand, but I think I get it. At least some parts of it. The new arithmetic that they do is just another system to do calculations. So it's just another way to do mathematics, but it limits the space of possibilities to only allow integers because you are working only with remainders. But then on the downside is that you lose some operations because of that. And then they use this arithmetic system to do all the computation of the elliptic curves and the pairings, which I don't understand really well yet. And the whole KZG commitments or data availability sampling thing that uses the polynomial technique, the Lagrangian interpolation polynomial, which I think I've seen before. Like you can represent a polynomial based on those multiplications, and then the point is to get the polynomial that crosses all the points. But I don't understand really well yet. Especially the code, like, and it's pretty crazy that Vitalik did a bunch of stuff. He made the compiler, it's like insane. I think this is the, don't remember which one is the compiler. There's so much stuff to look at. I think I'm gonna leave this stuff for the side. Like, it's good to read so I understand the general gist of it, but I'm not gonna spend time studying the code because I think it's worth it more now to study the code about the Casper and the proof of stake mechanism. And then just leave this ZK snark and data availability sampling for later, I think. But I'm gonna read these papers. Now. I think that's all of them. Don't know which one I'm gonna read first though. I guess it's gonna be this one.
Combining Ghost and Casper. Vitalik Buterin Ethereum Foundation.
And I think
Via
they don't have a
buterin.com.
way to
Diego Hernandez.
zoom in, so
Stsu.
I'm gonna have to
Diego.Hernandez at
zoom in the
stsu.edu.
page.
Thorkamp Hefner. Stsu. Thor.Camp-Hefner at stsu.edu. Keemfam Vene iResearch v.chi.empd1 at vina.io. Jichiao stsu 9092 at gmail.com. Danny Ryan Ethereum Foundation Danny at ethereum.org. Jui Yoxin. Stsu Homie N203 at gmail.com. Ying Wang. Stsu. Yingwang1001 at gmail.com. Yan X John. Stsu Yan.x.
I also think it's not working with this headset.
Combining Ghost and
Now
Casper.
it works.
Vitalik Buterin Ethereum Foundation.
Yeah, but I'm gonna use the other headset anyways. And I think I'm gonna go very slow now because both to understand better and because I'm gonna eat, so it's gonna be harder to pay attention as I eat. So I think it's a good idea to go slower. It's kind of crazy how after some time, like it seems really fast at first, but then after some time you kind of get used to it and start understanding. Obviously, like there's the trade-off where you understand less, but still feel like I understand a decent amount by going that speed. And a lot of times is better because some of these articles here, these ones that I'm gonna read as well, I already read them, and I wanna like get more exposure, so read in different times. So it's kind of like spaced repetition kind of thing. And then for those articles, I think it's better than to just go a lot faster, because then obviously I'm already familiar with most of the stuff. So if I go slow, then I get distracted, I think, and going fast forces me to pay attention. I'm gonna grab something to eat and then I'm gonna read this stuff.
This paper is motivated. Our goal is to create a consensus protocol for a proof-of-stake blockchain. This paper.
Damn, this sounds so slow. Let's do this one.
Blockchain. This paper is motivated by the need to construct Ethereum's beacon chain in its sharding design. This paper is motivated by the need to construct Ethereum's beacon chain in its sharding design. However, the construction can also be used for a solo blockchain with no sharding. We present Casper, a combination of Casper FFG.
I'm gonna grab something to eat, then I'll... Let me see first if I can make this better to put it like this, because I'm not sure. There's stuff that I can't show. But I'm gonna see if I can put it on dark mode and increase the size there. And I think it's not gonna be possible. Yeah, I don't see any options here.
Vitalik Buterin and Virgil Griffith. Ethereum Foundation. Abstract. We introduce Casper, a proof-of-stake-based finality system.
Yeah, I'm gonna go, and I'm not gonna put the camera. I'm gonna go grab something to eat, and I'll be right back.
We introduce Casper, a proof-of-stake-based finality system which overlays an existing proof-of-work blockchain. Casper is a partial consensus mechanism combining proof-of-stake algorithm research and Byzantine fault-tolerant consensus theory. We introduce our system, prove some desirable features, and show defenses against long-range revisions and catastrophic crashes. The Casper overlay provides almost any proof-of-work chain with additional protections against block reversions. 1. Introduction. Over the past few years there has been considerable research into proof-of-stake, POS, based blockchain consensus algorithms. In a POS system, a blockchain appends and agrees on new blocks through a process where anyone who holds coins inside of the system can participate, and the influence an agent has is proportional to the number of coins, or stake, it holds. This is a vastly more efficient alternative to proof-of-work, POW, mining and enables blockchains to operate without mining's high hardware and electricity costs. There are two major schools of thought in POS design. The first, chain-based proof-of-stake 1, 2, mimics proof-of-work mechanics and features a chain of blocks and simulates mining by pseudo-randomly assigning the right to create new blocks to stakeholders. This includes Peercoin 3, Blackcoin 4, and Ido Bentoff's work 5. The other school, Byzantine fault-tolerant, BFT, based proof-of-stake, is based on a 30-year-old body of research into BFT consensus algorithms such as PBFT6. BFT algorithms typically have proven mathematical properties. For example, one can usually mathematically prove that as long as 23 of protocol participants are following the protocol honestly, then, regardless of network latency, the algorithm cannot finalize conflicting blocks. Repurposing BFT algorithms for proof-of-stake was first introduced by Tendermint 7, and has modern inspirations such as 8. Casper follows this BFT tradition, though with some modifications. 1.1 Our work. Casper the friendly finality gadget is an overlay atop a proposal mechanism, a mechanism which proposes blocks 1. Casper is responsible for finalizing these blocks, essentially selecting a unique chain which represents the canonical transactions of the ledger. Casper provides safety, but liveness depends on the chosen proposal mechanism. That is, if attackers wholly control the proposal mechanism, Casper protects against finalizing two conflicting checkpoints, but the attackers could prevent Casper from finalizing any future checkpoints. Casper introduces several new features that BFT algorithms do not necessarily support. Accountability. If a validator violates a rule, we can detect the violation and know which validator violated the rule. Accountability allows us to penalize malfeasant validators, solving the nothing at stake problem that plagues chain-based POS. The penalty for violating a rule is a validator's entire deposit. This maximal penalty is the defense against violating the protocol. Because proof-of-stake security is based on the size of the penalty, which can be set to greatly exceed the gains from the mining reward, proof-of-stake provides strictly stronger security incentives than proof-of-work. 1. This functionality serves a similar role to the common abstraction of leader election used in traditional BFT algorithms, but is adapted to accommodate Casper's construction of being a finality overlay atop an existing blockchain. AR 141710.09437v4cs.cr January 22, 2019. Dynamic validators. We introduce a safe way for the validator set to change over time. Section 3. Defenses. We introduce defenses against long-range revision attacks as well as attacks where more than 1/3 of validators drop offline, at the cost of a very weak trade-off synchronicity assumption. Section 4. Modular overlay. Casper's design as an overlay makes it easier to implement as an upgrade to an existing proof-of-work chain. We describe Casper in stages, starting with a simple version, Section 2, and then progressively adding validator set changes, Section 3, and finally defenses against attacks, Section 4. 2. The Casper protocol. Within Ethereum, the proposal mechanism will initially be the existing proof-of-work chain, making the first version of Casper a hybrid POW/POS system. In future versions the POW proposal mechanism will be replaced with something more efficient. For example, we can imagine converting the block proposal into some kind of POS round-robin block signing scheme. In this simple version of Casper, we assume there is a fixed set of validators in a proposal mechanism, example the familiar proof-of-work proposal mechanism, which produces child blocks of existing blocks, forming an ever-growing block tree. From 9 the root of the tree is typically called the genesis block. Under normal circumstances, we expect that the proposal mechanism will typically propose blocks one after the other in a linked list, i.e., each parent block having exactly one child block. But in the case of network latency or deliberate attacks, the proposal mechanism will inevitably occasionally produce multiple children of the same parent. Casper's job is to choose a single child from each parent, thus choosing one canonical chain from the block tree. Rather than deal with the full block tree, for efficiency purposes 2 Casper only considers the subtree of checkpoints. Forming the checkpoint tree, figure 1a. The genesis block is a checkpoint, and every block whose height in the block tree, or block number, is an exact multiple of 100 is also a checkpoint. The checkpoint height of a block with block height 100k is simply k. Equivalently, the height h, c, of a checkpoint c is the number of elements in the checkpoint chain stretching from c, non-inclusive, to the root along the parent links, figure 1b, point 3. Each validator has a deposit. When a validator joins, its deposit is the number of deposited coins. After joining, each validator's deposit rises and falls with rewards and penalties. Proof-of-stake security derives from the size of the deposits, not the number of validators, so for the rest of this paper, when we say 23 of validators, we are referring to the deposit-weighted fraction, that is, a set of validators whose sum deposit size equals to 23 of the total deposit size of the entire set of validators. Validators can broadcast a vote message containing 4 pieces of information, table 1 2 checkpoints S and T together with their heights H, S, and H, T. We require that S be an ancestor of T in the checkpoint tree, otherwise the vote is considered invalid. If the public key of the validator new is not in the validator set, the vote is considered invalid. Together with the signature of the validator, we will write these votes in the form new, S, T, H, S, H, T. Notation description. S the hash of any justified checkpoint, the source, T any checkpoint hash that is a descendant of S, the target, H, S, the height of checkpoint S in the checkpoint tree H, T, the height of checkpoint T in the checkpoint tree S signature of S, T, H, S, H, T, from the validator new S private key. Table 1, the schematic of a single vote message denoted new, S, T, H, S, H, T. We define the following terms. 2. A long distance between checkpoints reduces the overhead of the algorithm, but also increases the time it takes to come to consensus. We choose a spacing of 99 blocks between checkpoints as a middle ground. 3. Specifically, the height of a checkpoint is not the same as the number of ancestors in the checkpoint tree all the way back to root along the supermajority links, defined in the next section. B1, B2, B3, R, A, the checkpoint tree. The dashed line represents 99 blocks between the checkpoints, which are represented by rounded rectangles. The root of the tree is denoted R. B1, B2, B3, RH, R, equals 0. H, B1, equals 1. H, B2, equals 3. H, B3, equals 6. B, the height function. B1, B2, B3, R. C, the justified chain R rightward arrow B1 rightward arrow B2 rightward arrow B3. Figure 1, illustrating a checkpoint tree, the height function, and a justified chain within the checkpoint tree. A supermajority link is an ordered pair of checkpoints, A, B, also written A rightward arrow B, such that at least 23 of validators, by deposit, have published votes with source A and target B. Supermajority links can skip checkpoints, i.e., it's perfectly okay for H, B, H, A, plus 1. Figure 1c shows 3 distinct supermajority links in red, R rightward arrow B1, B1 rightward arrow B2, and B2 rightward arrow B3. 2 checkpoints A and B are called conflicting if and only if they are nodes in distinct branches, i.e., neither is an ancestor or descendant of the other. A checkpoint C is called justified if, 1, it is the root, or, 2, there exists a supermajority link C rightward arrow C where checkpoint C is justified. Figure 1c shows a chain of 4 justified blocks. A checkpoint C is called finalized if, 1, it is the root or, 2, it is justified and there is a supermajority link. C rightward arrow C where C is a direct child of C. Equivalently, checkpoint C is finalized if and only if, checkpoint. An individual validator new must not publish 2 distinct votes. New, S1, T1, H, S1, H, T1, and new, S2, T2, H, S2, H, T2. Such that either IH, T1, equals H, T2. Equivalently, a validator must not publish 2 distinct votes for the same target height. Or 2H, S1. Equivalently, a validator must not vote within the span of its other votes. Figure 2, the 2 Casper commandments. Any validator who violates either of these commandments gets its deposit slashed. C is justified, there exists a supermajority link C rightward arrow C, checkpoints C and C are not conflicting, and H, C, equals H, C, plus 1. The most notable property of Casper is that it is impossible for any 2 conflicting checkpoints to be finalized unless greater than or equal to 13 of the validators violate one of the 2 4 Casper commandments slashing conditions, figure 2. If a validator violates either slashing condition, the evidence of the violation can be included into the blockchain as a transaction, at which point the validator's entire deposit is taken away with a small finder's fee given to the submitter of the evidence transaction. In current Ethereum, stopping the enforcement of a slashing condition requires a successful 51% attack on Ethereum's proof of work block proposer. 2.1. Proving safety and plausible liveness. We prove Casper's 2 fundamental properties, accountable safety and plausible liveness. Accountable safety, proving safety and plausible liveness.
I'm going to watch the videos instead because I'm not being able to pay too much attention while I eat. So I think it's better to watch the videos and then after I'm done eating, I'm gonna finish reading this papers here. I'll be right back.
and they both have MEV, one unit of MEV and another unit of MEV. And if you're the proposer in slot 2 and you're an attacker, you can go DDoS the proposer at slot 1 if that proposer's IP address is public, which it currently is on the beacon chain, which is that. And then basically the attacker can get twice as much MEV. So I'm expecting roughly $1,000 worth of MEV at every single block post merge. And so if you can do like a $1 denial of service attack on the proposer before you, you make 1,000 times your money. And I expect some people to some extractors to try and do that. And you can try and even do that with several slots in advance and make you basically steal even more MEV. So that's DOS-based MEV. And then another component of single lead secret, single lead election is the single. And I just want to explain why this is important in the context of MEV, because imagine that you have two proposers, proposer 1 and proposer 2, that kind of have this precedence list. So proposer 1 has precedence of proposer 2, etc. So proposer 1 doesn't propose blocks and proposer 2 can come in. Well, this is problematic because let's assume that the same person, an attacker, controls both proposer 1 and proposer 2, and this is how the attack goes. Proposer 2 publishes a block at the expected time, well enough in advance for all the attesters to be able to see the block. But then a few seconds later, proposer 1 publishes another block, this time with more MEV. But because it was published kind of late, it's possible that the attesters won't see it on time, and therefore it might not make it on chain. But in the case where it does make it on chain, then basically the attacker has these few seconds of edge to extract more MEV. Because the more time you have, then the more transactions come in, and you can have blocks with more MEV. So that's called a time buying attack, where you buy a few seconds worth. So chains like Definity and kind of got it wrong, at least in hindsight, in my opinion. Okay, so secret leader election. How does it work? Because I did have the word cryptography in the title. So very briefly, we have these trackers, which are basically ways for validators to have a commitment on chain, and this commitment to get shuffled around in such a way that they can track the commitment, but no one else can track the commitment. And then we use these commitments to select the next proposer. So we have this stirring function where we can every proposer can kind of stir and add some entropy. Then we do a bunch of stirs, and if one of the stirs is kind of honest, then we have plenty of entropy. And you see the blue block here is basically the commitment of the validator. And you have the validator 1 can track his commitment over time. And the way that this is implemented concretely is you have basically a pair of points. This is an curve point, the generator, and basically you have the secret which is embedded, and then you just multiply the tracker with a random scalar, and that's how you add in the entropy. Okay, that's most of the cryptography for this talk. Okay, so what about randomness? How does MEV come into play with randomness? So the way that we do randomness today is with randall. The way it works is that we have an epoch which is made of 32 slots, slot 0 to slot 31, and at each slot the proposer is invited to reveal a secret they've committed to at the time of registration. So this kind of secret 0 all the way to secret 31, and because they have the option to, basically they can not reveal, so it could be kind of the empty reveal, the empty set there. So every proposer either reveals or does not reveal a secret, you hash everything, and then you get the randomness for the next epochs. To sample the next proposers. So the problem here is that the very last proposer can either basically can choose between two random outputs. It can either reveal and get the green output, or not reveal and get the blue output. And this is bad because it means that they could choose which random number they want, which gives them the most MEV. Now, how can changing the randomness give you more MEV? Well, one reason is that you just might have more validator slots. If you choose green as opposed to blue, it's possible that you have the knowledge, for example, that there's going to be an NFT airdrop at a specific slot, which is going to be extremely valuable from an MEV standpoint. And it might be that the blue randomness will give you access to this really valuable slot. Or it could be, for example, that one of the randomness will give you access to these later slots in an epoch. Because basically the later slots are more valuable than the prior slots because they give you more control over the randomness. So you can use control over randomness to get even more control over randomness. And the way that we solve this, one thing to mention here is that it's not necessarily the last proposer who just voluntarily chooses to not reveal because he's malicious, but it could be that the last proposer is honest and intends to reveal, but is being DDoSed by someone else who likes the randomness at this point in time. So basically by an attacker who likes the blue randomness. And so here, this is kind of a good example where MEV, the systemic issue, is not very well contained. You have different MEV leaks which interact with each other in very subtle ways, and it's kind of compound on each other in some cases. Okay, so we have this delay function, and the idea of the delay function is that it's a function which takes time to compute, and we're actually going to use the output of the delay function as the source of randomness, not the input. And the reason is that by the time the output is made public, is known to the world, it was too late for these validators, these proposers, to reveal or not reveal. Okay, another problem with layer 1 MEV is chain reorgs. So this is very simple. We have some MEV as slot 1, represented by the cache icon here. And the proposer at slot 2 says, I want this MEV for myself. What I'm going to try and do is build on the parent, kind of rewriting history. And this is called a time-banded attack, right? Now, one of the things that we want to do on the beacon chain is completely remove time-banded attacks from the equation. And here's kind of how we'll get there. So the idea is to use BLS aggregation. So what we have today is per epoch finality. So we have hundreds of thousands of validators. We have so many validators that we kind of split them up into across a whole epoch from slot 0 to 31. So we have roughly right now 11,000 validators per slot. And each validator will make an attestation, will make a vote, for the block in the slot. The question that we can ask ourselves, and basically once we reach the end of the epoch, everyone had an opportunity to vote, and everyone having the opportunity to vote is what allows finality. So we need at least 2/3 of the validators to be doing these attestations to get finality. Now the question we can ask ourselves is, can we get a per slot finality, also known as single slot finality? And what we need to do that is basically have all validators sign at the same time and kind of aggregate them all at the same time. And the power of aggregatable BLS signatures is that you can take hundreds of thousands of signatures, you can aggregate them all very, very quickly, and the cost of verifying them on chain is very small. And we actually believe that we can get to this single slot finality point where we just completely remove time-banded attacks. Like small detail here, there's actually 2 slots, right? So in order to get finality, there's these 2 steps. Step number 1 is justification, second step is finality. So kind of under the hood, there's 2 kind of beacon slots, but these would correspond to only 1 EVM slot, so only 1 state transition change at the EVM level. okay, what is another source of MEV that comes from layer 1? And basically, it's the fact that the layer 1 is not scaling. And so there's a lot of overflow, which means that there's kind of this demand for these other layer 1s, and then you need to build bridges, and these bridges kind of inherently bring a lot of friction and MEV. So what are some of the kind of the constraints, fundamental limit of bridging between layer 1 and layer 1 is you don't have this nice synchrony. So you don't have the same slot durations, the same slot boundaries, the same settlement times, like this nice atomicity. But the other problem is that you don't have shared security. And so you have different social governance, you have independent 51% attack vectors, and there's some things that you fundamentally can't do, like data availability sampling. You can't have one layer 1 do data availability sampling on another layer 1. And all of these inefficiencies kind of lead to cross layer 1 MEV. And so the question is, can we remove cross layer 1 MEV? And my thesis is that yes, we can remove it. And the way that we remove it is with rollups and shared security. So the idea of shared security is that you have this very large layer 1 data availability, and then on top of it, you just put a bunch of rollups. And in order to achieve this, this dream of shared security, you have to do quite a bit of work cryptographically. You have to look at polynomial commitments, snarks, and all. So here, the way that what we want is not just shared security, but we want this really scalable shared security. And here again, this is kind of my belief that we're basically going to go from the current TPS the current situation of 10 TPS to 10 million TPS. And the way that we get there is that we have three 100x opportunities to scale, largely with, to a large extent with fancy cryptography. So we have rollups, which give us 100x, sharding gives us another 100x, and Nielsen's law, which is basically just Moore's law for bandwidth, which gives us another 100x. Okay, I only have 4 minutes left, and I really want to talk about this second part, because it might be more relevant for those who are not so much interested in layer 1. So here my thesis is that to a very large degree we can mitigate application layer MEV with encryption. And in the history of cryptography, it kind of started with encryption. And for a long time, blockchains have ignored encryption. Now, we've been using hashing, we've been using signatures, we've been using zero-knowledge proofs and all sorts of stuff, but we have kind of ignored encryption. And I think it's going to be the big return of encryption. So the thesis that I have is that in the medium-term future, most transactions are going to go through this life cycle. So transactions will be encrypted off-chain, and then on-chain, they will be included, decrypted, and executed. And by having these transactions be encrypted prior to inclusion on-chain will make it basically very hard or impossible to front-run, because the front-runner doesn't have the information that they need to do the front-running. But one of the key problems here is the decryption set. That is the most complicated one. And specifically what we need is some form of guaranteed decryption. We somehow need the decryption to automatically decrypt itself once it's been included on-chain. And you can't have commit reveal because that gives you like a free option. And so what are the forms of guaranteed decryption that exist in cryptography? So one is threshold decryption, where you're basically trusting a committee to do the decryption of the transactions. There's this other thing called delay decryption, where fancy cryptography allows you to automatically decrypt transactions after, let's say, 10 seconds or a minute. And then there's the most powerful tool of all, which is called witness decryption, where you provide some sort of cryptographic proof. It can be any proof, any snark, and that will allow you to decrypt a transaction. And one of the exciting things here is that from a user experience standpoint, all of this encryption stuff won't change. At least in theory, it could not change the user experience. Everything could be done in a single EVM slot. And so this is how I kind of see the end game at the consensus layer in terms of infrastructure that could be provided. So there's this single EVM slot, which is kind of what we're used to today, and then kind of behind the scenes, there's stuff happening with multiple beacon slots. And basically, we can shove a lot of ideas that help with MEV. We can shove proposer builder separation, so that there's these two stages where we have proposer blocks and builder blocks, and we also have here the two stages of finality. So first we finalize proposer blocks, then we finalize builder blocks. All of that takes 4 slots. And then in this final beacon slot, we have automatic decryption, for example, with witness decryption triggered by the finality of the builder block, and we execute. And from a UX standpoint, you don't realize that there's multiple blocks or additional latency. Now, there's a lot of devil into the details to actually point that off. One of the complications is that you need to encrypt the metadata. You also need to potentially do other things, and here you need to bring in the big guns like homomorphic encryption or fully homomorphic encryption. I don't have time today, but there is a 1 hour and a half talk where I go into the details on YouTube. That's it. Thank you.
So thank you everyone for coming. I think the purpose of this conversation is to talk about MEV and the interactions, how there's and interactions of it with the consensus layer and the design. But before we start, it might be worth going around the room doing intros. So Chris, you want to start?
Thanks all. I'm Casper. I previously designed the IBC protocol for the Cosmos project, which has some interesting relevance to cross-domain MEV, and now I work on the node protocols.
Answer?
And I'm with Quilt, which is a small Ethereum development team with Consensus and Ethereum Foundation, and I'm basically just help design kind of some of the iterations for Ethereum, mostly on the execution side actually, but of course MEVs kind of permeate everything, so yeah, I'll have to take into account that as well.
I'm Metallica. You guys I hang out and give presentations from time to time.
I'm Justin from the Foundation Research.
Nice. So the way that we can structure this conversation, and feel free to rearrange as you wish, is that we can talk about first the effects of MEV and the design space around consensus for how MEV is created, and then we can talk about mitigations and consensus layer, and then about where things are going. So maybe to start, it would be worth hearing, how does MEV affect your day-to-day when working on consensus-related research or client design or implementation? Maybe starting with Chris.
One of the questions for me as someone working on, say, a protocol that is not Ethereum, is are there interesting points in the design space that we can explore that are different, that would provide useful experimental data for future protocol designers? The honest answer after in the morning of talks and last 2 days for me is that I'm not sure if there are. Your presentation, Justin, on combining different steps of slots to prevent certain kinds of attacks seems to me to be very similar to discussions we're having around pipelining, threshold decryption, and tendermint. And I'm starting to wonder if some of these constraints are really information theoretic. But even so, there might be some cryptographic choices or choices on the mechanisms of implementation, especially if they're cryptonomic or cryptoeconomic instead of cryptographic, which change equilibria of how these systems would work in practice and how centralized or decentralized they might be. So one question for me is just, are there interesting different points in the design space? Can we predict equilibria just by looking at those points without actually building the systems, or do we have to build the systems and run them in production for a while in order to see what happens?
And maybe as a meta point, because we have a lot of questions to go through, and then maybe we'll have also questions from the audience. Let's try to keep answers 1-2 minutes.
Sure. So for me, I think day-to-day, it's probably a little bit less than most other people here. It's just whenever there are topics, for example, right now we're looking into a resource pricing on Ethereum, multi-dimensional 259 mechanisms, and it's just every time you give anything that's even remotely touches the incentive layer on Ethereum, you always have these detections, and so you just always have to make sure that at the end of the day, whatever systems you design basically stay incentive compatible. So I think that's primarily where it touches what I'm doing.
Yeah, and I think I definitely agree with all that. Like MEV does just touch many parts of the core of Ethereum protocol design, and even other layers of the Ethereum ecosystem. Right, so like it affects how you think about resource pricing is one example, and I guess kind of both positively and negatively. Right, so like one example there is the possibility of proposer builder separation and specialized builders like makes it easier to justify including and getting the benefits of multidimensional pricing, for example. So that and then thinking about things like the structure of when proposals happen, like how the cycle of one slot to the next slot works. Like you have to think about like is that incentive compatible and how do those incentives interact with the incentives to like get transactions included or get MEV for yourself.
I guess for me on the day-to-day, it's just very intellectually stimulating because it's an evolving story and it forces you to rethink the fundamentals and the end game. I guess it's also a forcing function to kind of prioritize things. So, for example, this MEV is incentivizing people to attack Ethereum post-merge, because proposers are public. And so one of the things that I've been trying to prioritize is the secret leader election to at least have ready in our back pocket if indeed the beacon chain does get unstable.
Maybe just very briefly say, I think because you said intellectually stimulating, I think it's really interesting that I think before MEV, we usually, whenever we kind of made design choices on Ethereum, they were purely kind of limited by whatever is technically possible, and then we just try to make the optimal choice within that scope. And now for the first time, we basically have this economic constraint, right? And basically the design space is very much narrowed now. Where basically we have to also take into account all the kind of incentive compatibility. And I think it's actually, it really is very healthy for the first basically be forced into this, because now, like, as we're talking about also other things like liquid staking and whatnot, like there are more of these more economic incentive kind of forcing functions that narrow our design space. And so it's really kind of less and less that it's really bound by just what's technically possible. But yeah, so this is really interesting.
So if MEV acts as a feedback loop, like a force back into the consensus layer design, how should somebody designing consensus protocols be thinking about where MEV can manifest and what should they do about that? I'm curious to hear maybe a summary from Justin's previous talk, because some people were not here, on how you're thinking about it, and then I'm also curious to hear for non-Ethereum chains.
Right. So I guess MEV is a bit like flash loans, right? They help exhibit vulnerabilities, leaks in your system. And I guess it's just a muscle you need to train when you look at the design. Like try and think MEV. And I guess the TLDR of my talk is like for all the known MEV leaks, there is cryptography that can solve it. So the heuristic is we're going to make it with cryptography because every time we find a leak, we can patch it. So yeah, that's the TLDR.
How does that change outside of Ethereum?
I think maybe one way it changes is more practical or engineering-wise rather than theoretical. I'm not actually sure if it changes in like the theoretical information way. In a practical way, it's maybe easier to use certain primitives because you can change more of the system. So for example, in using threshold decryption, where we also want guaranteed decryption as you're talking about, we can like have threshold decryption shares allocated exactly proportional to stake among 10 different validators, and we can inline basically or pipeline the threshold decryption into the stages of voting so that you're always, if you have the usual liveness assumptions that you're making already, you are guaranteed to be able to decrypt transactions. So I'm not sure that that's like different in the asymmetric time goes to infinity way. I think maybe it's different in the practical way, and maybe it's easier to try some of these systems out and provide data on just like what other economic layers form in practice above them, and if that impacts the consensus design constraints.
So we've heard of the term conservation of MEV, that no matter what you do, the MEV kind of moves around the stack. So I wonder, just to play devil's advocate, is it possible that while in process of patching the system, introducing new mechanisms to combat MEV form A, you introduce MEV in form B, and that is harder to mitigate? I have some ideas around it, but I don't think it's good.
I don't think that's necessarily true. Like there definitely are cases where you have different mechanisms to do the same thing, and some of them like actually do just like have as much MEV or have much more MEV than others. Auctions are definitely one good example of this. I mean, even just like one very trivial example is like how large is the liquidation bounty on like some collateralized thing, right? Like if you set it to 20% instead of 10%, you create twice as much MEV. So there's definitely some choices where like you're basically deciding, are you giving MEV to the miners or are you capturing MEV to some other mechanism, which is still sometimes a really important thing to do. But then there's also some cases where you actually can have more of it or less of it.
All right, this covers, I think, a bit like on the design space, so maybe let's switch over to mitigations. So again, we can use multiple techniques at various levels of the stack, either at the application layer like CowSwap, or the RPC layer like Flashbots, or the protocol layer, all the stuff that Justin has said. So the question is, how do we design mechanisms that are friendly to MEV mitigation, and how should we be thinking about that? Are there some desired properties that we're looking for here?
I mean, for me, one of the changes to the design philosophy that seems to emerge when we consider MEV is that we have to think a lot about returns to sophistication, and if sophisticated actors can like make more from the system, especially if they can make non-linearly more, then we're faced with this kind of centralizing force. And I think that's a different model than we've been using previously. Like often the sort of rational actor models treat computation as this like thing that just happens and you can do infinite amounts of it, and that is fine when the amount of computation is like kind of small or fixed size, so it's a reasonable first order approximation. But in MEV land, where we're dealing with like very complex spaces of computation or computational search space, I think that assumption no longer holds, and we have to like rethink some of our protocol design on those grounds. Maybe that's too abstract an answer. But.
I mean, I can put MEV into two buckets. There's the fundamental stuff and then the non-fundamental stuff. And basically, the non-fundamental stuff is everything that can be encrypted to prevent front running. And I think what will happen is that as soon as I think 95% of transactions will end up being encrypted and non-confrontable, and that will make up the bulk of the block. And then at the very top, the 5% of the transactions are going to be like highly specialized and doing all the arbitrage and cleaning up all the fundamental MEV, and it won't be encrypted, and it will just be produced basically by the supply chain that was mentioned. And the MEV will be split, to whoever does the actual work or is in a position of power to extract the MEV.
I'm going to disagree with the 95% figure. I think very plausibly under 50. Basically, I just think that we often forget that the majority of stuff that people do on chains isn't like fancy hyper time sensitive DeFi stuff. It's like I want to send you some money, or I want to make a CDP, like I want to update an ENS name, and just all sorts of just tiny random stuff. And for those things, like you don't really care if you get front run, and you actually want to broadcast your transactions to as many people as possible. Like even if your wallet starts doing exclusive order flows, you want to get a better wallet because you want to maximize the chance that your transaction will get included within the next wallet because that's most convenient for you. Now there are also other types of transactions that don't have that property, but I think both categories exist and both are large.
Right. But I guess this category of transactions don't have MEV to start with. So,
okay, yeah.
And the other thing is that it's kind of good practice maybe if they were to opt into this encryption scheme, because then it provides more, maybe more privacy for the other side of transactions.
I don't know. Like on the other hand, it also risks entrenching particular second layer things that you just have to be part of if you want to be a builder or whatever.
Yeah, but I'm optimistic that all this other infrastructure will be eventually public good stuff.
Mm-hmm.
Is there any interesting design space to your point of the talk earlier in between like no smart contracts Bitcoin land and full programmability Ethereum land, where you have something like protocol enshrined AMM or other kinds of certain MEV relevant economic infrastructure, but don't allow full programmability? Would that change the distribution here or no?
I mean, I guess like in principle, you totally can create. Like, you don't even need to forget other stuff. It's like for every category of stuff that people end up doing, you just make a protocol enshrined version and slightly subsidize it, right? And everyone uses it then. But I'm not sure that approach is the right approach. Like, I feel like the approach of layer separation is probably the better approach for sort of stuff. Like, make it possible that in some way that somehow one step insulated from the sensitive parts of the ecosystem.
Okay, then maybe like a related question. Of course, we have this vision now with basically the Ethereum-based layer becomes more just like a layer 2 settlement layer. And so is there any case to be made to say like maybe in the long run we want our kind of execution environment to be more of like a specialized virtual machine that maybe is in a sense more restricted and more controllable for us in that way?
I mean, I guess the main challenge there is like the politics of breaking backwards compatibility, right? Because like I've been yelling about banning self-destruct for like 2 years, and it's still it's going to happen, but it's it's a battle. And
Sure, but we could turn the current chain at some point into like a rollup or something.
yeah, I guess, yeah.
I mean, my position on this is that we want to go with full programmability, but the application layer won't be able to provide everything fully trustless. And so maybe there's going to be a little delta where we want to enshrine with additional consensus layer infrastructure. Like, I mean, this may be a bad example because it's very contentious, but potentially if we can't do like fully trustless oracles at layer 2, maybe we should consider doing them at layer 1.
So there are a lot of shiny things that we're talking about, and this can mean frequently lack of focus. So I'm curious to hear from each one of you, what do you think is the single most important thing that needs to be done yesterday on Ethereum or Anoa to achieve?
SSLE for me.
Why?
Well, as I
And
mentioned,
if you can break out the acronym.
yeah, so it's basically the secret lead election. The most important word is secret. So what we have on the beacon chain today is that proposers are known in advance, and post-merge there will be a small period of time, or maybe not so small period of time, where proposers will still be known ahead of time. And what you can do is that you can fairly easily map proposer pub key identities to IP addresses. So if you want, if you know how to DDoS IP addresses, and that's something a script kiddie can do, then there's kind of two things that could potentially happen. One is like some sort of malicious attacker who wants to spend, I don't know, $1,000 a day just disrupting Ethereum could potentially disrupt maybe the home validators or things like that. But maybe more worryingly is that there's going to be quite a lot of MEV on a block by block basis, on the order of $1,000. And there's this attack whereby if you're a proposer at slot n and you DDoS the proposer at slot n-1, you get to get the MEV of slot n-1. So basically you're now doubling your MEV at the cost of attacking your fellow validators. I don't expect most people to do that, but I am expecting like some kind of extractors to be doing it.
Just pushing back a bit on the DOS point. In general, infrastructure providers not getting the DOS, you'd say, or a reasonable person would say it's a solved problem with Sentry nodes like improper like load balancing infrastructures. I wonder why specifically the fixation of the DOS part.
Well, yes, you can have fancy networking setups, and like the exchanges will have it, the pool operators will have it. The bad thing here is that it's more difficult to do from home. And I think the clients are starting to build out this infrastructure, but it's possible that you need 2 internet connections as opposed to 1. It's possible that you need to get VPNs, and that's going to kind of add friction for home users. And it's possible that if there are going to be attacks, and this might be kind of a centralization vector where home validators kind of throw the towel and say, I'm being attacked, I'm just going to move to some exchange. So that I think one of the reasons why I'm prioritizing SSLE is partly for the health of the network, but also partly for kind of the long-term centralization.
Makes sense. Vitalik, what is the most important thing?
I don't know. I think there's a lot of important things. And I think the big, well, probably just to go back to the kind of way that I described my own goal when I was making a presentation earlier today, which is basically just like protects the really important parts of layer 1 and make sure that they don't centralize as a result of any economies of scale that do exist at other layers of the stack.
So how is that solved? What's the solution for that? Or the action item?
I mean, action items are, one is continue research on the stuff that we have already, and the other is just I guess continue the sort of more open-ended brainstorm. Like I feel like there's probably things other than our current ideas around like layer 2s and separating out builders that should be explored as well.
Can you unpack a bit the argument around why proposer-builder separation is important, and maybe talk a bit about CR lists?
Yeah, I mean, basically proposer-builder separation, it separates out the proposer market from the builder market, and so it makes sure that the economies of scale in the builder market don't end up spilling over onto the proposer market. So proposers can still like continue to be relatively dumb nodes, just people installing a piece of software onto a fairly simple computer and running it, even while builders become this kind of crazy game where everyone keeps optimizing lots of things. One of the challenges of that is like the risk that there is a monopoly builder, and monopoly builders could easily start censoring. I think there is some protection against that censoring already, because if you censor even one transaction, then the builder will basically have to like pay or either pay or kind of lose an opportunity cost sense, an amount of ETH equal to the gas cost of that transaction for pretty much every block, which is a pretty high price, but something that's not enough. And so there's this idea of like adding explicit kind of further infrastructure to create like more channels in parallel through which a chain can force inclusion of transactions. So a CR list, a censorship resistance list, are one example of this. Like basically proposers could just like create a list where they flag all the transactions that they see that seem to be worthy of being included, and then the next block by builder just like has to actually include the transaction, or else that block is not like accepted by Fortress.
Yeah, I think I would largely agree, like going in a similar direction to what just I've been saying. I think the way I think about it is like, as I was saying earlier, we have like now more incentive-based kind of design space constraints, and I think it's really important to figure out exactly what types of centralizations basically will be inevitable, and then separately figure out what types of like centralization are unacceptable for us, or like what types of decentralization we really care about and want to retain, and like make sure that how can we make sure that those two kind of things overlap and keep overlapping, right? And like, I think right now, for example, we seem to all try and be okay with something like PBS, and still that I think there's also quite a few things to be worked out to be sure that this would be actually defined for the network, and then also on the validator side, we really want to keep decentralization. It's also not yet clear that this is within the possible design space, right? But there also like then other things, right? I think, for example, less sexy maybe because it's not like a current topic, but like there's like I think right up from like even 4 years ago, already 3 years ago, they're talking about how right now basically fork choice on Ethereum is like we have like automatic rules and we have social consensus that can override this, and then we have Circle that basically chooses which fork actually honors USDC, right? And that would in practice override social consensus on Ethereum like in many scenarios, just because on the other side DeFi would collapse and the entire chain would crumble, right? And that's also like that's a completely separate example, but it's another one where basically like are we okay with this? What other like how can we influence this as a base chain? Is that something that's inevitable? Just in general, right? This whole topic of like how can we make sure that what will need to happen and what we really want to happen, how can we keep those overlapping, basically?
And like which technological solution do you think is the one that you're the most excited to spend all your productive time on?
I mean, I really don't think there's like a silver bullet. Like I think like every one of those problems has like a separate kind of design space, a separate solution. So it's really important that we just make sure we keep track of all of them and try to have solve all of them.
I guess it gets back to my point around prioritization and focus, but I'll take that. Chris?
Yeah, I mean, to me, MEV seems like a sort of iterated game between the protocol designers and the people trying to exploit MEV, and I think it's good that we are playing this game and that both sides can iterate and that both sides, like, are not fighting each other tooth and nail, but also understand that there is a game going on, and that only through like some progression there, I think, if there are rational actors with sophistication, they will exploit the easiest opportunity. And there's this information flow topology all the way from like some users, submitting things to those transactions being settled, and if we, push things L2s, then sophisticated actors will go after L2s. I have not thought enough about that problem to know whether it's like easier or harder, or will have higher or lower returns to sophistication. It does push it to somebody else, like it's not us, so that's good, but it's also perhaps concerning. I think it's like another case where this is clear, this iterated game thing is, I completely agree that like proposer DOS is a concerning problem in principle, especially if you want home operated validators. In practice, in tenement networks, it's not a priority because like it's just not worth the cost of building up sophisticated systems to do it yet. Probably we can reason somewhat about when that might become a priority and like try to fix it then. And that kind of iterated game modeling the actors maybe determines prioritization until we either converge to some like final thing where there's an architecture that seems to be a stable equilibrium, or we just like keep going forever. I don't know if it ends or not.
Yeah, that makes sense. And one aspect of this iterative game is the deterrence game. And so you kind of want to have kind of in your back pocket all these cards that you can play if you do have an attack. So you're basically disincentivizing the upfront investment. And as you said, in the case of proposer DDoS, you probably have to invest at least a month's worth of dev time.
Because the fact that we live in a multi-chain world at this point, and I wonder how you guys are thinking about cross-chain MEV and how it affects the consensus layer decisions or solutions. For example, we're already seeing Cosmos meta extractors who run validators on 2 chains, and they are among the 2 chains atomically when they're elected as the proposer for both chains. So how are you thinking about that? And does that concern Ethereum, if at all?
One like very specific way that it might affect things is like in PBS there's this discussion of are we auctioning off hashes or are we auctioning off like the builder identity, right? Like basically when you make a bid you have to commit to what you're going to be including in your block, and that basically forces the builder to make bids based on like what they can include at that particular moment when the auction happens. Versus if you just leave it free, then it's like the builder's bid based on their expectations of how much MEV they'll be able to see in the next lot. I think historically we've been generally more in favor of the approach that requires builders to include hashes because it's like that way builders can guarantee what their revenue is going to be, and that makes it easier to be a builder. But in a cross-chain world there are arguments for kind of leaving that open as well, right? Basically because in a cross-chain world, like if you want it to be possible to kind of get these gains from being the proposer in multiple domains at the same time, then like that only becomes possible to do like inside the game if you actually do have like that free opportunity on both domains.
Is a world with multi-chain bundles a good world?
I mean, in general, I feel like a more complicated world is a less good world, but the question is like, what's the counterfactual? And if the counterfactual is like even more incentive for people to join the biggest staking pool, then like I'd rather have multi-chain bundles,
So I'm sitting on the wrong couch. I should be on the light mode couch to answer this question. I'm mildly optimistic about maybe not like the full cross-domain, but at least cross-chain MEV for the reason that I don't think it requires like agreement on too many components of the architecture. I think it mostly requires agreement on clocks. So if we're using like threshold decryption systems, it matters a lot in a cross-domain context whether or not those like periods of threshold decryption are synchronized across the domains. If they're happening at like lots of different times across the domains, then there's going to be a lot of asymmetric information among block proposers. But if they're happening in a more synchronized time, then everyone kind of has to make decisions about ordering, and then everything gets decrypted. Maybe there's still a 5%, 10%, but it seems like you can synchronize some things without necessarily agreeing on consensus or agreeing on other more fundamental architectural decisions.
So my opinion is that cross-layer 1 MEV is bad, but ironically this is a great thing. And the reason it's a great thing is that it pushes the shared security model. And so the question is, the real question is, can we scale shared security? And it's my belief that we can. And if we can, then we wouldn't take most, and therefore there wouldn't be so much cross-layer 1 MEV.
Interesting.
So we have 9 minutes, so let's spend 4 minutes on the next question and then something about the future, and then let's open up to the audience for any questions. So MEV traditionally has been painted as a curse in a way, but I wonder if there's a galaxy brain where you can invert it and use it for good. The obvious examples are arbitrage and liquidations, but maybe in chains without a block reward, you can use MEV as a security budget or something in that neighborhood.
Interesting, yeah. Like I guess if you like auction the builder's block very far ahead of time, then like you can do the like transaction fees for security thing and like basically avoid having the big spikes in like what the reward is. But then I guess the counter argument is like you could do that the other way as well, right? Like if you have EIP 1559 burns, you can just like release them retroactively, like basically put the burn into a pot and then every block release like 1 over 100,000 of the pot. I think the direction that where like if you kind of surrender to a block building specialization where you get like a lot of gains is the question of like can you have more sophisticated resource limits multi-dimensional EIP 1559 is one good example. Another good example is if you start having like multi-threaded and parallel EVMs, then like that also will require the concept of gas to kind of become more complex to reflect the actual constraints that nodes have. If you just say like we have this other way to just deal with optimal block production being really complicated, then like all of those like there's just a lot of other hard decisions that you just totally don't have to make and things that become easier.
Yeah, so MEV can be kind of good for several things. One is that it can increase security because there's more rewards validators, but it can also be used to increase scarcity if you can find a way to burn it. And there are some designs where we have MEV burn. And basically, you can be in a situation where you just rely on the proof of stake issuance for security, and everything else just leads to more scarcity. I think kind of another reason why MEV is good is that it's kind of a tandem magnet and has this accelerationist aspect to it. And, this room is proof of it.
You always find ways to add more ultrasound to the ultrasound.
Ultra.
All right, now I'm on the right couch because I'm going to take the contrarian position. I feel like there might be some conservation of demand here, where like ultimately users want to use blockchains because some like semantics of state transition of sending someone money or trading some asset is the thing they want to do. And if they're like doing that slightly less efficiently because they're not getting as much of the assets as they could have gotten because there's some MEV, that changes maybe who gets like specific parts of whatever that demand translates to in terms of transaction fees or MEV, but I'm not sure it changes how much of it there is. Which isn't to say that MEV isn't like an interesting like tool in the protocol designer's toolkit, but I'm not sure it like can be used to add security that wouldn't have already been somehow provided by the fundamental demand.
Just one kind of protocol security, I would definitely, I would definitely say, like Justin said, that I think it's very important to never directly couple protocol income and security spending, just because conceptually those really like should be really floating against each other, right? You just set a security budget and then you have an income, and that can be more or less, and that determines the soundness of your money, maybe. But like, if you basically artificially cost, right, as Bitcoin is today, and I hope they'll move to some 50 mechanism. But like right now, right, they just artificially couple their security to their to the fees, and that just doesn't make sense, right? Because then you're floating security guarantees. That's never worked.
What did we not talk about?
What should we change the Ethereum logo to?
All right. Do we have any questions from the crowd?
To your point, Vitalik, at the beginning, you said users mostly want to do just transfers, right? So I wonder if there are some possibilities out there for MEV mitigation that are more sort of not on-chain design and in protocol, but actually if there's, for example, if we're able to enable intents at the end user level, where the intent is not just I want to transfer assets from A to B, but where I can say, for example, I would like this transfer to happen, but I also would like it to not, I would like to not be run, and I would like to pay this much as long as that is guaranteed. So I wonder if there are some, like, there's more some potential in the space by just enable end user intents to just be more expressive. To avoid,
I mean, that is what like some of these like fancier exchange protocols are trying to do, right? Like basically allowing users to kind of set more conditions and like basically making AMMs have like some of the properties of order books and kind of like pushing like exploring the design space in the middle by starting from the AMM side and then making it look more orderly. Like that's that feels like it's already doing some of that, right? And like a stronger MEV ecosystem, I think it can even help there, right? Because users can create conditions that are very strict, like you can even set slippage to 0 if they want or whatever, and things like that can be handled more effectively.
Flashbox is adding that to the RPC, where you can opt in on certain kinds of method to be extracted from your transaction, and only go to certain searchers that look for that. I think we have one more question, and we'll go wrap.
Yeah, so I'm going to start a little off, and then I'm sure you'll understand why. So,
sorry, we got really tight, like you can get.
Okay, I got to the point then. Okay, good. So, other industries, let's say airplane, mining, oil and gas, etc., spend inordinate time, money, and effort on trying to figure out why accidents happen. And it turns out that, of course, accidents happen because people are stupid and technological issues and whatnot. But a good chunk of it actually happens because they try to put more and more safeguards into place, and these safeguards tend to eventually interact in complex and complicated and unknown ways. And then it blows up into the face of the people who built it. And I feel like there's been a lot of work being put forward here that says, okay, well, this is the system the way we understand it, and this is the way we're going to try to put these even more and more complex ways to try to fix it. And I'm wondering, are you afraid of these complex systems that are meant to safeguard the system from current issues that you see right now will eventually interact in ways that will blow up into our face? And whether it's best to sort of accept the risk that we have already and live with it rather than try to fix it and then create potentially way more risk than what you're thinking you're fixing.
Maybe a TLDR would be complexity solves things, but is complexity okay?
I mean, I think the answer here is just modularity. You want to try and encapsulate as much as possible. And so, for example, within the beacon chain, there's like all these different modules. So, for example, we have randomness generation, and this can be a very well encapsulated thing and can have like an ideal functionality. Just provides unbiased randomness. We could have, and if you just do this for every single module, and then you're kind of limiting complexity in a big way. And this is kind of going against the flow of MEV. MEV is this kind of force towards being like systemically seeping through every single crack. And so, it's a good counterbalance to try and modularize as much as possible.
Great. Thank you all for coming. Thank you to the group.
We prove Casper's two fundamental properties, accountable safety and plausible liveness. Accountable safety means that two conflicting checkpoints cannot both be finalized unless greater than or equal to 13 of validators violate a slashing condition, meaning at least 1/3 of the total deposit is lost. Plausible liveness means that, regardless of any previous events, example slashing events, delayed blocks, censorship attacks, etc., if greater than or equal to 23 of validators follow the protocol, then it's always possible to finalize a new checkpoint without any validator violating a slashing condition. Under the assumption that properties I. If S1 rightward arrow T1 and S2 rightward arrow T2 are distinct supermajority links, then H, T1, 6 equals H, T2. 2. If S1 rightward arrow T1 and S2 rightward arrow T2 are distinct supermajority links, then the inequality H, S1. 4. There exists at most one justified checkpoint with height n. With these four properties in hand, we move to the main theorems. Theorem 1, accountable safety. Two conflicting checkpoints M and Bn cannot both be finalized. Proof. Let M, with justified direct child M plus 1, meaning H, M. Let M, with justified direct child M plus 1, meaning H, M, plus 1 equals H, M plus 1, and Bn, with justified direct child Bn plus 1, meaning H, Bn, plus 1 equals H, Bn plus 1, be distinct finalized checkpoints as in figure 3. Now suppose M and Bn conflict, and without loss of generality H, M. Let our rightward arrow be 1, rightward arrow be 2, rightward arrow bn be a chain of checkpoints, such that there. 4 earlier versions of Casper had 2 types of messages and 4 slashing conditions 10, but we have reduced this to 1 message type and 2 slashing conditions. We removed the conditions, I, committed hashes must already be justified, and, 2, prepare messages must point to an already justified ancestor. This is a design choice. We made this choice so that slashing violations are independent of the state of the chain. Exists a supermajority link R rightward arrow b1, by rightward arrow by +1, bn rightward arrow bn +1. We know that no h, by, equals either h, am, or h, am +1, because that violates property, 4. Let j be the lowest integer such that h, bj, h, am +1, then h, bj1. This implies the existence of a supermajority link from a checkpoint with an epoch number less than h, am, to a checkpoint with an epoch number greater than h, am +1, which is incompatible with the supermajority link from am to am +1. Theorem 2, plausible liveness. Supermajority links can always be added to produce new finalized checkpoints, provided there exist children extending the finalized chain. Point 5. Proof. Let A be the justified checkpoint with the greatest height, and B be the target checkpoint with the greatest height for which any validator has made a vote. Any checkpoint A, which is a descendant of A with height h, A, equals h, B, +1 can be justified without violating either commandments I or 2, and then A can be finalized by adding a supermajority link from A to a direct child of A, also without violating either I or 2. A1 equals B1. A2. B3. B2. Violates 2. A3. B4. R. Figure 3. Figure for Theorem 1. Accountable safety. 2.2 Casper's fork choice rule. Casper is more complicated than standard POW designs. As such, the fork choice must be adjusted. Our modified fork choice rule should be followed by all users, validators, and even the underlying block proposal mechanism. If the users, validators, or block proposers instead follow the standard POW fork choice rule of always build atop the longest chain, there are pathological scenarios where Casper gets stuck and any blocks built atop the longest chain cannot be finalized, or even justified, without some validators altruistically sacrificing their deposit. To avoid this, we introduce a novel, correct by construction, fork choice rule, follow the chain containing the justified checkpoint of the greatest height. This fork choice rule is correct by construction because it follows from the plausible liveness proof, Theorem 2, which precisely states that it's always possible to finalize a new checkpoint on top of the justified checkpoint with the greatest height. This fork choice rule will be tweaked in sections 3 and 4. 5. The finalized chain always exists because the root is enabling dynamic validator sets. The set of validators needs to be able to change. New validators must be able to join, and existing validators must be able to leave. To accomplish this, we define the dynasty of a block. The dynasty of block B is the number of finalized checkpoints in the chain from root to the parent of block B. When a would-be validator's deposit message is included in a block with dynasty D, then the validator new will join the validator set at first block with dynasty D +2. We call D +2 this validator's start dynasty, DS, new. To leave the validator set, a validator must send a withdraw message. If validator new S withdraw message is included in a block with dynasty D, it similarly leaves the validator set at the first block with dynasty D +2. We call D +2 the validator's end dynasty, new. If a withdraw message has not yet been included, then new equals infinity. Once validator new leaves the validator set, the validator's public key is forever forbidden from rejoining the validator set. This removes the need to handle multiple start/end dynasties for a single identifier. At the start of the end dynasty, the validator's deposit is locked for a long period of time, called the withdrawal delay, approximately 4 months worth of blocks, before the deposit is withdrawn. If, during the withdrawal delay, the validator violates any commandment, the deposit is slashed. We define 2 functions that generate 2 subsets of validators for any given dynasty D, the forward validator set and the rear validator set. They are defined as VF, D. Note this means that the forward validator set of dynasty D is the rear validator set of dynasty D +1, i.e., VF, D, equals VR, D +1. To support these dynamic validator sets, we redefine a supermajority link in a finalized checkpoint as follows. An ordered pair of checkpoints, S, T, where T is in dynasty D, has a supermajority link if both at least 23 of the forward validator set of dynasty D have published votes S rightward arrow T and at least 23 of the rear validator set of dynasty D have published votes S rightward arrow T previously. A checkpoint C was called finalized if C is justified and there is a supermajority link from C rightward arrow C where C is a child of C. We now add the condition that C is finalized if only if the votes for the supermajority link C rightward arrow C, as well as the supermajority link justifying C, are included in CS blockchain and before the child of C, i.e., before block number H, C, 100 + 1. The forward and rear validator sets will usually greatly overlap, but if the 2 validator sets substantially differ, this stitching mechanism prevents safety failure in the case when 2 grandchildren of a finalized checkpoint have different dynasties because the evidence was included in one chain but not the other. For an example of this, see figure 4. For stopping attacks. There are 2 well-known attacks against proof-of-stake systems, long-range revisions and catastrophic crashes. We discuss each in turn. 4.1 Long-range revisions. The withdrawal delay after a validator's end dynasty introduces a synchronicity assumption between validators and clients. Once a coalition of validators has withdrawn their deposits, if that coalition had more than 23 of deposits long ago in the past, they can use their historical supermajority to finalize conflicting checkpoints without fear of getting slashed, because they have already withdrawn their money. This is called the long-range revision attack, see in figure 5. In simple terms, long-range attacks are prevented by a fork choice rule to never revert a finalized block, as well as an expectation that each client will log on and gain a complete up-to-date view of the chain at some regular frequency, example once per 1 to 2 months. A long-range revision fork that finalizes blocks older than that will 2B votes finalizing block S are included in these intermediate blocks, so simply be ignored, because all clients will have already seen a finalized block at that height and will refuse to revert it. We make an informal proof of the mechanism. Figure 4, attack from dynamic validator sets. Without the validator set stitching mechanism, it's possible for two conflicting checkpoints C and C to both be finalized without any validator getting slashed. In this case C and C are the same height, thus violating commandment I, but because the validator sets finalizing C and C are disjoint, no one gets slashed. Simply be ignored, because all clients will have already seen a finalized block at that height and will refuse to revert it. We make an informal proof of the mechanism as follows. Suppose that there is a maximum communication delay delta between two clients, so if one client hears some message at time t, all other clients are guaranteed to have heard it by time t plus delta. This means that we can talk about the time window tmin, tmax during which a block was received by the network. With width tmax tmin at most delta, we assume that all clients have local clocks that are perfectly synchronized. Any discrepancy can be treated as being part of the communication delay delta. Blocks are required to have timestamps. If a client has local time TL, then it will reject blocks whose timestamp TB satisfies TBTL, i.e., in the future, and they will refuse to accept as finalized, but may still accept as part of the chain, blocks where TB. If a validator sees a slashing violation at time t, that's the time they hear the later of the two votes required for a slashing violation, then they reject blocks with timestamps t plus 2 delta that are part of chains that have not yet included this slashing evidence. Suppose that a large set of slashing violations results in two conflicting finalized checkpoints, C1 and C2. If the two time windows do not intersect, then all validators agree which checkpoint came first and everyone follows the rule to not revert finalized checkpoints, then there is no issue. If the two time windows do intersect, then we can handle the case as follows. Let C1 S time window be 0, delta, and C2 S time window be delta, 2 delta. Then the timestamps of both are at least 0. By time 2 delta, it is guaranteed that all clients have seen the slashing violation, so they reject blocks with timestamp 4 delta whose chains have not yet included the evidence transaction. Hence, as long as omega 4 delta, it's guaranteed that malfeasant validators will lose their deposits in all chains that any client accepts, where omega is the withdraw delay, figure 5, the delay between the end epoch and when validators actually receive their deposits back. Due to network delays, it's possible that clients will disagree whether a given piece of slashing evidence was submitted into a given chain on time or as having accepted it too late. However, this is only a liveness failure, not a safety failure, and this possibility does not weaken our security claims because it is already known that a corrupted proposal mechanism, which would be required to prevent evidence inclusion, can prevent finality. After withdrawal, attack fabricates a conflicting chain. Withdraw delay. Attacker submits withdraw request. Attacker withdraws here. CC. Figure 5, the long-range attack. As long as a client gains complete knowledge of the justified chain at a regular interval, it will not be susceptible to a long-range attack. We can also sidestep the issue of evidence inclusion timeouts by informally arguing that attacks will be short-lived, because the validators will perceive a long-running chain without including slashing evidence as an attack and switch to another branch supported by an honest minority of validators that are not part of the attack. See section 4.2, thus stopping the attack and slashing the attacker. 4.2 Catastrophic crashes. Suppose that 13 of validators crash fail at the same time, i.e., they are no longer connected to the network due to a network partition, computer failure, or the validators themselves are malicious. Intuitively, from this point on, no supermajority links can be created, and thus no future checkpoints can be finalized. We can recover from this by instituting an inactivity leak, which slowly drains the deposit of any validator that does not vote for checkpoints, until eventually its deposit sizes decrease low enough that the validators who are voting are a supermajority. The simplest formula is something like in every epoch a validator with deposit size D fails to vote, it loses DP, for 0. This drained ether can be burned or returned to the validator after omega days. Whether leaked assets should be burned or returned as well as the exact formula for the inactivity leak is outside the scope of this paper, as these are questions of economic incentives, not Byzantine fault tolerance. The inactivity leak introduces the possibility of two conflicting checkpoints being finalized without any validator getting slashed, as in figure 6, with validators only losing money on only one of the two checkpoints. Assume the validators are split. Whether leaked assets should be burned or returned as well as the exact formula for the inactivity leak is outside the scope of this paper, as these are questions of economic incentives, not Byzantine fault tolerance. The inactivity leak introduces the possibility of two conflicting checkpoints being finalized without any validator getting slashed, as in figure 6, with validators only losing money on only one of the two checkpoints. Assume the validators are split into two subsets, with subset VA voting on chain A and subset VB voting on chain B. On chain A, VB's deposits will leak, and vice versa, leading to each subset having a supermajority on its respective chain, allowing two conflicting checkpoints to be finalized without any validators being explicitly slashed, but each subset will lose a large portion of their deposit on one of the two chains due to leaks. If this situation happens, then each validator should simply favor whatever finalized checkpoint it saw first. The exact algorithm for recovering from these various attacks remains an open problem. For now, we assume validators can detect obviously malfeasant behavior, example not including evidence, and manually create a minority soft fork. This minority fork can be viewed as a blockchain in its own right that competes with the majority chain in the market, and if the majority chain truly is operated by colluding malicious attackers, then we can assume that the market will favor the minority fork. Validator A goes offline and slowly leaks. Validator B strikes once it is a supermajority. Justified and finalized by A. Justified by A. Justified and finalized by B. Justified by B. Figure 6, inactivity leak. The checkpoint on the left can be finalized immediately. The checkpoint on the right can be finalized after some time, once offline validator deposits sufficiently deplete. 5 conclusions. We presented Casper, a novel proof-of-stake system derived from the Byzantine fault tolerance literature. Casper includes 2 slashing conditions, a correct by construction fork choice rule inspired by 11, and dynamic validator sets. Finally, we introduced extensions to Casper, not reverting finalized checkpoints and the inactivity leak, to defend against two common attacks. Casper remains imperfect. For example, a wholly compromised block proposal mechanism will prevent Casper from finalizing new blocks. Casper is a POS-based strict security improvement to almost any POW chain. The problems that Casper does not wholly solve, particularly related to 51% attacks, can still be corrected using user-activated soft forks. Future developments will undoubtedly improve Casper's security and reduce the need for user-activated soft forks. Future work. The current Casper system builds upon a proof-of-work block proposal mechanism. We wish to convert the block proposal mechanism to proof of stake. We wish to prove accountable safety and plausible liveness even when the weights of the validator set change with rewards and penalties. Another problem for future work is a formal specification of a fork choice rule taking into account the common attacks on proof of stake. Future work papers will explain and analyze the financial incentives within Casper and their consequences. A particular economic problem related to such automated strategies to block attackers is proving upper bounds on the ratio between the degree of disagreement between different clients and the cost incurred by the attacker. Acknowledgements. We thank John Choi, Carl Floersk, Ozymandias Haynes, and Vlad Zamfir for frequent discussions. References. 1Pass, RNG, eFruit Chains, a fair blockchain. In Proceedings of the ACM Symposium on Principles of Distributed Computing, PODC 2017, 315-324, ACM, New York, USA, 2017. URL http://doi. acm.org/10.1145/3087801.3087809. 2 Introducing Definity Crypto Techniques, 2017. URL https://definity.org/pdf-viewer/pdfs/viewer. HTML, file =/library/intro-definity-crypto.pdf. 3 King, S. and Nadal, Coin, peer-to-peer cryptocurrency with proof of stake 19, 2012. URL https://decred.org/research/king2012.pdf. https://web.archive.org/save/https://decred.org/research/king2012.pdf. For Vazin, P. Blackcoin's proof of stake protocol v2, 2014. URL http://blackcoin.co. Blackcoin POS protocol v2 whitepaper.pdf. 5 Bentov, I, Gabizin, A. and Mizrahi, a cryptocurrencies without proof of work. In Zion, R. ed. International. Conference on Financial Cryptography and Data Security, 142-157, Springer, 2016. URL http://www. cs.technion.ac.il/tilde/iddd/coa.pdf. 6 Castro, M. Liskov, B. and E.T. AL Practical Byzantine Fault Tolerance. In Leach, P.J. and Seltzer, M. eds. Proceedings of the Third Symposium on Operating Systems Design and Implementation, Volume 99, 173-186, 1999. URL http://pmg.csale.mit.edu/papers/osdi99.pdf. Proving safety and plausible liveness. We prove Casper's two fundamental properties, accountable safety and plausible liveness. Accountable safety means that two conflicting checkpoints cannot both be finalized unless greater than or equal to 13 of validators violate a slashing condition, meaning at least 1/3 of the total deposit is lost. Plausible liveness means that, regardless of any previous events, example slashing events, delayed blocks, censorship attacks, etc., if greater than or equal to 23 of validators follow the protocol, then it's always possible to finalize a new checkpoint without any validator violating a slashing condition. Under the assumption that properties. I. If S1 rightward arrow T1 and S2 rightward arrow T2 are distinct supermajority links, then H, T1, 6 equals H, T2. 2. If S1 rightward arrow T1 and S2 rightward arrow T2 are distinct supermajority links, then the inequality H, S1. 4. There exists at most one justified checkpoint with height n. With these 4 properties in hand, we move to the main theorems. Theorem 1, accountable safety. Two conflicting checkpoints M and Bn cannot both be finalized. Proof. Let M, with justified direct child M plus 1, meaning H, M, plus 1 equals H, M plus 1, and Bn, with justified direct child Bn plus 1, meaning H, Bn, plus 1 equals H, Bn plus 1, be distinct finalized checkpoints as in figure 3. Now suppose M and Bn conflict, and without loss of generality H, M. Let our rightward arrow B1 rightward arrow B2 rightward arrow Bn be a chain of checkpoints, such that there. 4 earlier versions of Casper had 2 types of messages and 4 slashing conditions 10, but we have reduced this to 1 message type and 2 slashing conditions. We removed the conditions, I, committed hashes must already be justified, and, 2, prepare messages must point to an already justified ancestor. This is a design choice. We made this choice so that slashing violations are independent of the state of the chain. Exists a supermajority link R rightward arrow B1, by rightward arrow by plus 1, Bn rightward arrow Bn plus 1. We know that no H, by, equals either H, M, or H, M plus 1, because that violates property, 4. Let J be the lowest integer such that H, Bj. Casper FFG, the friendly finality gadget, and LMD Ghost, latest message-driven greediest heaviest observed subtree. Casper FFG7 is a finality gadget, which is an algorithm that marks certain blocks in a blockchain as finalized so that participants with partial information can still be fully confident that the blocks are part of the canonical chain of blocks. Casper is not a fully specified protocol and is designed to be a gadget that works on top of a provided blockchain protocol, agnostic to whether the provided chain were proof of work or proof of stake. LMD Ghost is a fork choice rule where validators, participants, attest to blocks to signal support for those blocks, like voting. Casper is a full proof of stake protocol that is an idealized abstraction of the proposed Ethereum implementation. In sections 2 and 3, we define our primitives, provide background knowledge, and state our goals. In section 4, we give our main protocol Casper. In sections 5, 6, and 7, we formally prove Casper's desired qualities. In section 8, we summarize some differences between Casper and the actual planned Ethereum implementation, such as delays in accepting attestations, delaying finalization, and dynamic validator sets. We conclude with some thoughts and ideas for future research in section 9. 2. Setup and goals. What is Byzantine fault tolerance, BFT? Byzantine fault tolerance, BFT, is one of the fundamental properties of reliable blockchain rules or protocols. Blockchain allows computers and people to agree on things without needing to trust each other. This network of people and computers simply need to trust that the rules they are all following are reliable. Byzantine fault tolerance, BFT, is one of the fundamental properties of creating reliable blockchain rules or protocols. But before we can understand what Byzantine fault tolerance is, we need to take a step back and work out what peers, nodes, and consensus means and what military tactics have to do with it all. What are peers and nodes? Most blockchain or cryptocurrencies operate as networks where all computers in the network have equal access and rights, and directly communicate with each other. Each single computer in this network is known as a peer or a node. In a truly decentralized system, no peer or node has more authority or power than the next. This means that there are no managers, coordinators, or directors to enforce the rules, determine what is true, or punish misbehavior. Instead, the system relies on the fact that all nodes must follow the same rules or protocol in order to come to an agreement. What is consensus? Consensus simply means a general agreement. In a decentralized system where there are no authorities, achieving consensus is one of the most important and most difficult things to do. For the system or network to function correctly, consensus simply means a general agreement. In a decentralized system where there are no authorities, achieving consensus is one of the most important and most difficult things to do. For the system or network to function correctly, the majority of nodes must agree on what is true, reaching consensus at regular intervals. The problem is that some nodes will inevitably fail, misbehave, or just disagree with the consensus of the other nodes, so the system must be designed in such a way that deals with this inevitability. What is a Byzantine fault tolerance? A system has Byzantine fault tolerance, BFT, when it can keep functioning correctly as long as 2/3 of the network agree or reaches consensus. BFT is a property or characteristic of a system that can resist up to 1/3 of the nodes failing or acting maliciously. All decentralized blockchains run on consensus protocols or rules that all the nodes in the blockchain must follow in order to participate. Consensus protocols such as proof of work and proof of stake are Byzantine fault tolerant and are thus able to resist up to 1/3 of the nodes disagree. Who invented Byzantine fault tolerance? The Byzantine generals problem was invented in 1982 by Leslie Lamport, Robert Shostak, and Marshall Pease and is the inspiration for the concept of Byzantine fault tolerance. Byzantine generals problem. The concept of BFT comes from the Byzantine generals problem, which is a logical thought experiment where there are several generals that need to attack a city. The generals are all in different locations and can only communicate by messenger, one message at a time. They must all coordinate the same action in order to successfully attack or retreat. If they all attack, they will be fine. If they all retreat, they will be fine. The problem occurs when some generals attack while others retreat, in which case it will be a bad result for everyone. The twist is that some generals are disloyal and will try to confuse the other generals. The problem to solve is, how will all the generals agree on the same action even in the face of treachery and deceit? What's so special about it? A consensus protocol that is Byzantine fault tolerant can still coordinate and come to consensus despite some amount of disagreement among the nodes. This is vital for decentralized blockchains such as Ethereum or Bitcoin. One of the essential innovations of Satoshi Nakamoto when they created Bitcoin was in solving the Byzantine generals problem by applying proof of work to the Bitcoin network. By having the property of BFT, the Bitcoin network is protected from up to 1/3 of the nodes being malicious. Did you know? Systems that require BFT are also used in industries beyond blockchain such as aviation, space, and nuclear. These industries all highly prioritize safety and security as well as work with a large number of interconnected sensors or computers, which act as nodes. These nodes need to communicate with each other reliably and BFT comes into play when a portion of these nodes become faulty yet the system is still able to continue functioning as intended. What can you do with BFT? The most common consensus protocols used in blockchain networks such as proof of work, proof of stake, and proof of authority all have some property of BFT. By applying BFT, systems can be designed that are not controlled by a single authority and do not rely on trusting certain parties. It is fundamental to building a decentralized network. The future. The principle of BFT will continue to play a major role in blockchain networks. As more people and organizations explore distributed and decentralized systems, more innovative ways to design BFT systems will be discovered and implemented. Stay on top of crypto news. Get daily updates in your inbox. Your email. Get it. Setup and goals. The main goal of this paper is to describe and prove properties of a proof-of-stake blockchain with certain safety and liveness claims. In this section, we give some general background on consensus protocols and blockchain. As the literature uses a diverse lexicon, the primary purpose of this section is to pick out a specific set of vocabulary for the rest of the paper. 2.1 Consensus protocols, validators, blockchain. Our goal is to create a consensus protocol, or protocol for short from this point on, which is an agreed suite of algorithms for a set of entities, nodes, people, etc., to follow in order to obtain a consensus history of their state, even if the network is unreliable and or if many validators are malicious. We call the entities, people, programs, etc., who participate in protocol validators, denoted by the set V. They are called validators because of their data validation role in the Ethereum 2.0 beacon chain, though the specifics of this role are not part of our abstract protocol. Other works use many different words for the same concept, e.g. replicas in classic PBFT literature, block producers in DeepOS and EOS, peers on Peercoin and NXT, or bakers on Tezos. The validators are connected to each other on a peer-to-peer network, which means they can broadcast messages, basically, packets of data, to each other. In the types of protocols we are interested in, the primary types of messages are blocks, which collect bundles of messages. The first block is called the genesis block and acts as the initial blank slate state. Other blocks are descriptions of state transitions with a pointer to a parent block 1. A blockchain is just an instantiation, i.e. with specific network conditions, validators, etc., of such a consensus protocol where we use blocks to build the overall state. We do not want all blocks seen on the network to be accepted as common history because blocks can conflict with each other. These conflicts can happen for honest reasons such as network latency, or for malicious reasons such as Byzantine validators wanting to double spend. Byzantine refers to a classic problem in distributed systems, the Byzantine generals problem, and is used in this instance to describe a validator who does not follow the protocol, either because they are malicious or experiencing network latency. Graph theoretically, one can think of a choice of history as a choice of a chain going from the genesis block to a particular block. Thus, a consensus history is 1. Our choice that each block has a unique parent is almost taken for granted in blockchains. One can imagine blockchains where blocks do not need to have parents, or can have more than one parent. See, for instance, hash graph 2. Even the very general structure of block itself may be limiting. A consensus of which chain of blocks to accept is correct. This is why we call such an instantiation of our protocol a blockchain. Example 2.1. Assume the goal of a protocol is to keep a ledger of every validator's account balances. Then their collective state is the ledger, and each block captures a state transition, such as a monetary transaction from one validator to another. Example, Eunice sends coin with ID 538 to BureauGuard. One type of conflict we may want to avoid is having both the aforementioned transaction and another transaction with content. Eunice sends coin with ID 538 to Carol, be accepted into consensus history, an act commonly called double spending. The current consensus state can be determined by starting from a genesis state and sequentially processing each message in the consensus history, hopefully one that all honest validators will agree with, starting from the genesis block. 2.2 Messages and views. In our model, a validator V interacts with the network by broadcasting messages, which are strings in some language. When an honest validator V broadcasts a message M, we assume M is sent to all validators on the network too. The main type of message proposes a block, which is a piece of data, to the network. Other messages can be bookkeeping notices such as voting for blocks, attestation, putting new validators on the blockchain, activation, proving bad actions of other validators, slashing, etc. Depending on the specific protocol, we assume that each message is digitally signed by a single validator, which means we can accurately trace the author of each message, and attacks such as impersonation of honest validators are not possible. Due to network latency and dishonest validators, delaying messages or relaying incorrect information, validators may have different states of knowledge of the full set of messages given to the network. We formalize this by saying that a validator either sees or does not see each message given to the network at any given time. Each message may have one or more dependencies, where each dependency is another message. At any time, we accept a message if and only if all of its dependencies, possibly none, are accepted, defined recursively. We now define the view of a validator V at a given time t, denoted as view, v, t, as the set of all the accepted messages the validator has seen so far. We also have a God's eye view that we call the network view, defined to be the set of accepted messages for a hypothetical validator that has seen, with no latency, all messages any validator has broadcast at any time. This includes messages sent by a malicious validator to only a subset of the network. We will treat the network as a virtual validator, so we use view, NW, t, to denote the network view at time t. For any validator V in any given time t, view, NW, t, includes all the messages in view, v, t, though the timestamps may be mismatched. Finally, since usually the context is that we are talking about a specific point in time, we will usually just suppress the time and use notation such as view, v, to talk about view, v, t, unless talking about the specific time is necessary. Example 2.2. At time t, suppose validator V sees the message M with content, Eunice sends coin number 5340 to Bob, but has not yet seen the message M containing Eunice obtains coin number 5340, which is on the network but has not yet made its way to V. Also suppose that in our protocol M depends on M, and no other message, which captures the semantic meaning that we need to obtain a coin before spending it, and that V cannot and should not act on M without seeing M. In this situation we say that V has seen but has not accepted M, so M/set membership symbol view, V, T. However, the network has seen both, so if the network accepts M, we have M set membership symbol view, NW, T. We now make some assumptions on the structure of views. Everyone, the validators and the network, starts with a single message, with no signature, corresponding to a single agreed upon genesis block, denoted genesis, with no dependencies, so it starts out automatically accepted into all views. 2. We model the validators as sending a single message to an abstract network, which handles the message. In practice, it may be part of the protocol that example every honest validator rebroadcasts all messages that they see. For robustness, we consider these implementation details not important to our paper. Each block besides genesis refers to, and depends on, a parent block as part of its data. Thus, we can visualize view, v, as a directed acyclic graph, in fact, a directed tree 3, rooted at genesis, with an edge b leftward arrow b if b is the parent of b, in which case we say b is a child of b. We call these parent-child edges to differentiate from other types of edges. We say that a block is a leaf block if it has no children. A chain in such a protocol would then be a sequence of pairwise parent-child edges b1 leftward arrow, b2 leftward arrow if there is a chain from b to b. We say b is a descendant of b. We say b is an ancestor of b if and only if b is a descendant of b. We say two blocks b and b conflict if they do not equal and neither is a descendant of the other. The above setup implies each block b uniquely defines a backwards chain starting from genesis to b, and this must be the same chain in any view that includes b, thus we do not need to include a view as part of its definition. We call this the chain of b, or chain, b. Genesis, a, b, c, d, e. Figure 1, a graph visualization of a view, only visualizing blocks and not other messages, that occurs in the types of protocols we care about. Example 2.3. See figure 1 for an example of a view, limited to blocks. Arrows portray parent-child edges. The blocks in a view form a tree rooted at a single genesis block genesis. Here blocks c and d conflict, as well as e and d. E has the longest chain, which is chain, e, equals, genesis, a, b, c, e. There are some technicalities to our wording in this section that motivates our definition of views but are not very important to the core of this paper. To not distract the reader, we defer these details to Appendix A 2.3 Proof of Stake. The first and most influential approach to blockchain protocols is Bitcoin 15, using a proof-of-work model. This approach makes it computationally difficult to propose blocks, using the simple and intuitive fork-choice rule. The block with the heaviest chain is the head of the chain. Miners, the analogy of validators, simply propose blocks to build on the heaviest chain, the chain with the most amount of computational work, which does not mathematically guarantee any non-genesis block is correct but offers a probabilistic guarantee since it becomes less and less likely to conflict with the block once other miners build on top of it. Then the consensus history is simply the chain. History is simply the chain with the heaviest amount of work, which ideally keeps growing. The elegance of proof of work is paid for by the expensive cost of computational work / electricity / etc. To propose a block, In this paper, we want to create a proof-of-stake blockchain where a validator's voting power is proportional to their bonded stake, or money, in the system. Instead of using computational power to propose blocks, proposing blocks is essentially free. In exchange, we need an additional layer of mathematical theory to prevent perverse incentives that arise when we make proposing blocks. 3. This statement already captures the primary reason we define both seeing and accepting. The blocks a validator accepts must be a single-rooted tree, though the blocks a validator sees can be some arbitrary subset of the tree, so limiting our attention to the tree allows cleaner analysis and avoids pathological cases. Beyond this reason, the distinction between the two words is unimportant for the rest of this paper. Easy. We now shift our paper's focus to a family of blockchain designs with proof-of-stake in mind. To start, we assume we have a set of n validators V equals V1, Vn, and that each validator V set membership symbol V has an amount of stake W, V, a positive real number describing an amount of collateral. We make the further assumption that the average amount of stake for each validator is 1 unit, so the sum of the total stake is n. All of our operations involving stake will be linear, so this scaling does not change the situation and makes the bookkeeping easier. We assume validator sets and stake sizes are fixed for the sake of focusing on the theoretical essentials of the protocol. We address issues that occur when we relax these conditions in practical use in later sections, especially section 8. The main ingredients we need are a fork choice rule, a function fork, that, when given a view G, identifies a single leaf. Block B. This choice produces a unique chain fork, G, equals chain, B, from Genesis to be called the canonical chain. The block B is called the head of the chain in view G intuitively. A fork choice rule gives a validator a law to follow to decide what the right block should be. For example, the longest chain rule is a fork choice rule that returns the leaf block which is farthest from the Genesis block. This rule is similar with the heaviest chain rule used by Bitcoin. A concept of finality, formally, a deterministic function f that, when given a view G, returns a set f, G, of finalized blocks. Intuitively, finalized blocks are blocks that everyone will eventually think of as part of the consensus history, or what the blockchain is sure of. Slashing conditions, these are conditions that honest validators would never violate and violating validators can be provably caught, with the idea that validators' stake would be slashed, or destroyed. Slashing conditions incentivize validators to follow the protocol. The protocol can reward honest validators for catching dishonest validators violating the conditions, for example. The key concept we use to define these ingredients are attestations, which are votes, embedded in messages, for which blocks should be the head of the chain. To prevent validators from double voting or voting in protocol-breaking ways, we enforce slashing conditions which can be used to destroy a validator's stake, incentivizing validators to follow the protocol. Genesis. A. B. C. Blocks. Attestations. B. A. B depends on A. Genesis ABC. The chain of C or chain, C. Figure 2, an ideal view with both blocks and attestations. One can see an idealized version of the protocol we will present in Figure 2. In each time period, a new block is created with the parent block being the last head of chain, which is ideally just the last block created, and validators in the corresponding committee all perfectly attest to the new block. In less idealized situations, the blocks may fork, we may have missing attestations, etc., and the attestations will come to play by helping validators decide the correct head of the chain. In Section 4 we will define all the details. In a protocol, we call a validator honest if he/she follows the protocol, and Byzantine otherwise. We typically assume strictly less than p equals 13 of validators are Byzantine. This constant can be traced to practical Byzantine fault tolerance, PBFT, from 8, a classic consensus protocol in Byzantine tolerance literature. PBFT ensures that the system runs correctly as long as less than 13 of the replicas. Synonymous with our validators are Byzantine, as proven in 3. This constant 13 tolerance appears frequently in many works based on PBFT. The main idea is that a pigeonhole principal argument needs the 1/3 to work, such as in our proof in Section 5, with Casper FFG7 being the most directly relevant to our work, which we review in Section 3.1. Concretely, we define a blockchain running the protocol to be p-slashable if validators with a total of p and stake can be provably slashed by a validator with the network view, and most of our results will take the form, at any time, our blockchain either has good property X or is 1/3 slashable, because we really cannot guarantee having any good properties when we have many Byzantine actors, so this is the strongest type of statement we can have. Also note that having 1/3 slashable is a stronger and much more desirable result than just having 1/3 of the stake belonging to Byzantine validators, because if we only had the latter guarantee, we may still incentivize otherwise honest validators to cheat in a way they do not get caught. One of the most important aspects of PBFT is that it works under asynchronous conditions, which means we have no bounds on how long it may take for messages to be received. Thus, it is robust to the demands of blockchains and cryptocurrencies, where we often worry about adversarial contexts. We will discuss synchrony assumptions further in Section 2.6. 2.5 Safety and liveness. The ultimate goal for the honest validators is to grow a finalized chain where all blocks form logically consistent state transitions with each other, despite having validators potentially go offline, suffer latency problems, or maliciously propose conflicting state changes. Formally, this translates to two desired properties. Definition 2.4. We say a consensus protocol has safety if the set of finalized blocks F, G, for any view G can never contain two conflicting blocks. A consequence of having safety is that any validator view G's finalized blocks F, G, can be completed into a unique subchain of F, view, and W, that starts at the Genesis block and ends at the last finalized block, which we call the finalized chain. Liveness, if the set of finalized blocks can actually grow. There are different ways to define liveness. For our paper, we say the protocol has plausible liveness, if regardless of any previous events, attacks, latency, etc., it is always possible for new blocks to be finalized. Alternatively, it is impossible to become deadlocked. This is to prevent situations where honest validators cannot continue unless someone forfeits their own stake. Probabilistic liveness, if regardless of any previous events, it is probable for new blocks to be finalized, once we make some probabilistic assumptions about the network latency, capabilities of attackers, etc. On first glance, the latter implies the former, but the situation is more subtle. The former is a purely non-probabilistic property about the logic of the protocol. The latter requires, potentially very strong, assumptions about the context of the implementation to guarantee that the protocol usually works as intended. We discuss this contrast further in Section 7.3. Our main goal in this paper is to prove these vital properties for our main protocol in Section 4. Remark, syntax versus semantics. It should not be immediately obvious that chains have anything to do with logical consistence of state transitions, and this requires more work on the part of the protocol designer to ensure. For example, one can dictate a protocol where a block that allows a user to spend a coin S forbids an ancestor block from using S in another transaction. In this situation, if Xander obtained a coin S from block BX and writes 2 blocks by NBZ, such that byte's data includes Xander paying S to Yeshus and BZ's data includes Xander paying S to Zachariah, then the logical idea that these actions are inconsistent corresponds to the graph theoretical property that by NBZ conflict as blocks. The language of chains and conflicting blocks is enough to serve any such logic, so we assume in our paper that the syntax of what blocks can be children of what other blocks has already been designed to embed the semantics of logical consistency, which allows us to ignore logic and only think in terms of chains and conflicting blocks. 2.6 Time, epochs, and synchrony. In our model, we measure time in slots, defined as some constant number of seconds, tentatively 12 seconds in 11. We then define an epoch to be some constant number C, tentatively 64 slots in 11, of slots. The epoch J of slot I is EP, I, equals J equals BICC. In other words, the blocks belonging to Epoch J have slot numbers JC plus K as K runs through 0, 1, C1. The Genesis block Genesis has slot number 0 and is the first block of epoch 0. The main purpose of epochs is to divide time into pieces, the boundaries between which can be thought of as checkpoints. This allows concepts from Casper FFG to be used, as we will see in section 3.1. We should not assume the network is guaranteed to have the validators see the same messages at any given time, or even that different validators have the same view of time. The study of consensus protocols address this issue by having different synchrony conditions, such as a synchronous system has explicit upper bounds for time needed to send messages between nodes. An asynchronous system has no guarantees. Recall that PBFT8 works under asynchrony. A partially synchronous system can mean one of two things depending on context. I. Explicit upper bounds for delays exist but are not known a priori. 2. Explicit upper bounds are known to exist after a certain unknown time t. The work 10 establishes bounds on fault tolerance in different fault and synchrony models, focusing on partial synchrony. For us, we make no synchrony assumptions when studying safety and plausible liveness. When studying probabilistic liveness, i.e. trying to quantify liveness under realistic conditions, we will use the notion, 2, of partial synchrony above. We say that the network is t-synchronous at time t, where t and t are both in units of slots, if all messages with timestamps at or before time, tt, are in the views of all validators at time t and afterwards. Example, if each slot is 12 seconds, then, 1/2, synchrony means that all messages are received up to 6 seconds later. Remark. It is possible to example receive messages from the future. Suppose Alexis sends a message timestamped at 1 minute and 30 seconds pt and Bob receives it 1 second later with a clock that is 3 seconds behind Alexis's. Bob sees this 1 minute and 30 seconds pt message on his own clock timestamped at 1 minute and 28 seconds pt because he is a net total of 2 seconds behind. To make analysis easier, we can assume that all honest validators always delay the receiving of a message, i.e., do not add it into their view until their own timestamps hit the message's timestamp. This allows us to assume no messages are read, again, by honest validators, in earlier slots than they should. 3 main ingredients. 3.1 Casper FFG. Buterin and Griffith introduced Casper the friendly finality gadget, FFG, in 7. This tool defines the concepts of justification and finalization inspired by practical Byzantine fault tolerance, PBFT, literature. Casper is designed to work with a wide class of blockchain protocols with tree-like structures. Every block has a height defined by their distance from the Genesis block, which has height 0. Equivalently, the height of B is the length of chain, B, 1. We define checkpoint blocks to be blocks whose height is a multiple of a constant h, in 7, h equals 100. We define the checkpoint height h, B, for a checkpoint block B as the height of B divided by h, which is always an integer. Thus, we can think of the subset of checkpoints in the view as a subtree, containing only blocks whose heights are multiples of h attestations are signed messages containing checkpoint edges, a rightward arrow B, where A and B are checkpoint blocks. We can think of each such attestation as a vote to move from block A to B. The choices of A and B depend on the underlying blockchain and is not a part of Casper. Each attestation has a weight, which is the stake of the validator writing the attestation. Ideally, h, B, equals h, A, plus 1, but this is not a requirement. For example, if h equals 100, it is possible for an honest validator to somehow miss block checkpoints in the view as a subtree, containing only block. Every block. Casper is designed to work with a wide class of blockchain protocols with tree-like structures. Every block has a height defined by their distance from the Genesis block, which has height 0. Equivalently, the height of B is the length of chain, B, 1. We define checkpoint blocks to be blocks whose height is a multiple of a constant h, in 7, h equals 100. We define the checkpoint height h, B, for a checkpoint block B as the height of B divided by h, which is always an integer. Thus, we can think of the subset of checkpoints in the view as a subtree, containing only blocks whose heights are multiples of h attestations are signed messages containing checkpoint edges, a rightward arrow B, where A and B are checkpoint blocks. We can think of each such attestation as a vote to move from block A to B. The choices of A and B depend on the underlying blockchain and is not a part of Casper. Each attestation has a weight, which is the stake of the validator writing the attestation. Ideally, h, B, equals h, A, plus 1, but this is not a requirement. For example, if h equals 100, it is possible for an honest validator to somehow miss block 200, in which case their underlying blockchain may want them to send an attestation from checkpoint block 100 to checkpoint block 300. Remark. Observe we set up time in units of slots, which are grouped into epochs. This is analogous to, but not exactly identical to, block heights and checkpoint blocks. We discuss this further in section 4.1. Casper FFG also introduces the concepts of justification and finalization, which are analogous to phase-based concepts in the PBFT literature such as prepare and commit, example C8. In each view G, there is a set of justified checkpoint blocks J, G, and a subset F, G, proper subset symbol, J, G, of finalized checkpoint blocks. The Genesis block is always both justified and finalized. In a view G, a checkpoint block B is justified by a justified checkpoint block A, if A is justified and there are attestations voting for a rightward arrow B with total weight at least 2/3 of total validator stake. Equivalently, we say there is a supermajority link AJ, rightward arrow B. This is a view-dependent condition, because the view in question may have or have not seen all the relevant attestations to break the 2/3 threshold, or even having seen the block B itself, which is why the set of justified blocks is parameterized by G. In a view G, if a set membership symbol J, G, equivalently, A is justified, and AJ, rightward arrow B is a supermajority link. With H, B, equals H, A, plus 1, then we say a set membership symbol F, G, equivalently, A is finalized. Finally, Casper introduces slashing conditions, which are assumptions about honest validators. When they are broken by a validator V, a different validator W can slash V, destroy V's stake and possibly getting some sort of slashing reward by offering proof V violated the conditions. Definition 3.1. The following slashing conditions, when broken, cause a validator violating them to have their stake slashed. S1. No validator makes two distinct attestations alpha 1 and alpha 2 corresponding to checkpoint. Edges S1 rightward arrow T1 and S2 rightward arrow T2 respectively with H, T1, equals H, T2. S2. No validator makes two distinct attestations alpha 1 and alpha 2 corresponding respectively to checkpoint edges S1 rightward arrow T1 and S2 rightward arrow T2, such that H, S1. It is assumed that honest validators following the underlying protocol will never be slashed. As Casper is a finality gadget and not a complete protocol, it assumes the underlying protocol has its own fork-choice rule, and at every epoch all the validators run the fork-choice rule at some point to make one, and only one, attestation. It is assumed that honest validators following the underlying protocol will never be slashed. For example, if the protocol asks to make exactly one attestation per epoch, then honest validators will never violate S1. The main theorems in Casper are, slightly paraphrased. Theorem 3.2, accountable safety. Two checkpoints on different branches cannot both be finalized, unless a set of validators owning stake above some total provably violated the protocol, and thus can be held accountable. Theorem 3.3, plausible liveness. It is always possible for new checkpoints to become finalized, provided that new blocks can be created by the underlying blockchain. Remark. POMSCO ETAL 17 provided a mechanical proof assistant for Casper FFG's accountable safety and plausible liveness in the Coke proof assistant. The authors modified the blockchain model in Coke, toy chain, to use for the Casper FFG with Ethereum's beacon chain specs in order to see how Casper FFG's proofs will work in practice. The greediest, heaviest observed subtree rule, Ghost, is a fork-choice rule introduced by Sompolinsky and Zohar 20. Intuitively, Ghost is a greedy algorithm that grows the blockchain on sub-branches with the most activity. Zamfir 22, in looking for a correct by-construction consensus protocol, introduces a natural adaptation of Ghost that happens to be well-suited for our setup for. We call this variant latest message-driven greediest, heaviest observed subtree, LMD. Ghost, which we can define after having a notion of weight. Definition 3.4. Given a view G, let M be the set of latest attestations, 1 per validator. The weight W, G, B, M, is defined to be the sum of the stake of the validators I whose last attestation in M is to B or descendants of B. Algorithm 3.1 LMD Ghost fork choice rule. 1. Procedure LMD Ghost, G, 2, B leftward arrow Genesis 3, M leftward arrow the most recent attestations of the validators, 1 per validator, 4, while B is not a leaf block in G do 5, B leftward arrow argmax. B child of B. W, G, B, M. 6. Ties are broken by hash of the block header. 7. Return B. Genesis. 8, 8, 5 3, 113, 1, 3, 1 2, 2, 1. Figure 3, an example of the LMD Ghost fork choice rule. The number in each block B is the weight, by stake, with all attestations, circles, having weight 1 in our example. A validator using this view will conclude the blue chain to be the canonical chain, and output the latest blue block on the left, with weight 3, to be the head of the chain. The idea of LMD Ghost is that at any fork, we use the weights of the subtrees created by the fork as a heuristic and assume the subtree with the heaviest weight is the right one, as evident from the name of the algorithm. We will always end up at a leaf block, which defines a canonical chain. See figure 3 for a graphical visualization. In 22, LMD Ghost was tied to a particular protocol. Our presentation of it in this paper treats the specifics of attestations as details to be filled in by the protocol, like how Casper does not specify details on how blocks are constructed. We merely need that the concepts of blocks and attestations exist, and then LMD Ghost defines an algorithm to find a block given a view. In section 4 we will modify the rule to satisfy our other purposes. For this part of the field can create phantasmal confusion. The name of 22 is Casper the Friendly Ghost, which introduces Casper CBC, also C5, a completely separate protocol from Casper FFG. Our paper is in some sense recombining these two ideas, but the Casper in 22 is very different from Casper FFG. We now define our main protocol Casper, which is a combination of the Ghost and Casper FFG ideas. The main concepts are epoch boundary, pairs of a chain, given a chain, certain blocks are picked out, ideally 1 per epoch, to play the role of Casper's checkpoints. However, a block may appear more than once as a checkpoint on the same chain. This is a nuance not found in Casper. We expound on this in section 4.1, so we use ordered pairs, B, J, where B is a block and J is an epoch, to disambiguate. These will be called epoch boundary pairs, or pairs for short. Committees. The validators are partitioned into committees in each epoch, with 1 committee per slot. In each slot, 1 validator from the designated committee proposes a block. Then, all the members of that committee will attest to what they see as the head of the chain, which is hopefully the block just proposed. In each slot, 1 validator from the designated committee proposes a block. Then, all the members of that committee will attest to what they see as the head of the chain, which is hopefully the block just proposed, with the fork choice rule HLMD Ghost, a slight variation of LMD Ghost. Justification and finalization. These concepts are virtually identical to that of Casper FFG. Except we justify and finalize pairs instead of justifying and finalizing checkpoint blocks, i.e., given a view G, J, G, and F, G, are sets of pairs. 4.1 Epoch boundary blocks and pairs. Recall any particular block B uniquely determines a chain, B. For a block B in an epoch J, define EB, B, J, the JTH epoch boundary block of B, to be the block with the highest slot less than or equal to JC in chain, B. Let the latest such block be LEB, B, or the last epoch boundary block of B. We make a few observations. For every block B, EB, B, 0, equals Genesis. More generally, if slot B equals JC for some epoch J, B will be an epoch boundary block in every chain that includes it. However, without such assumptions, a block could be an epoch boundary block in some chains but not others. To disambiguate situations like these, we add precision by introducing epoch boundary pairs, or pairs for short, B, J, where B is a block and J is an epoch. Our main concepts of justification and finalization will be done on these pairs. Given a pair P equals B, J, we say P has attestation epoch J, using the notation AEP, P equals J, which is not necessarily the same as EP, B. 63 64, 63, 65, 66. Epoch 0 epoch 1. LEBB, 65, equals 64. LEBB, 66, equals 60. Figure 4, example of epoch boundary blocks and pairs. Blocks are labeled with their slot numbers. 63 is not an actual block but illustrates the perspective of 66 needing an epoch boundary block at slot 64 and failing to find one. Example 4.1. Suppose blocks, labeled by slots, form a chain 63 leftward arrow 64 leftward arrow 65 and there is a fork 63 leftward arrow 66. Then EB, 65, 1, equals 64 since 64 is in chain, 65. When we try to find EB, 66, 1, we look for block 64 because we are in epoch 1 and realize it is not in chain, 66, so we have to look backwards and pull up block 63 from the previous epoch to serve as the epoch boundary block in 11. This chain. This is visualized by the dashed components in figure 4. Observe even though AEP, 63, 1, and EP, 63, equals 0, EP, is a local property that only depends on the block slot, and epoch boundary concepts like AEP, depend on the context of the chain. Remark. We further address why we use pairs instead of checkpoint blocks. Casper FFG is a finality gadget, meaning Remark. We further address why we use pairs instead of checkpoint blocks. Casper FFG is a finality gadget, meaning it is designed to place a layer of finality on top of a blockchain which has probabilistic liveness, which gives a steady new supply of checkpoint blocks. Probabilistic liveness assumes good synchrony conditions. For the safety part of the design, we would want to make fewer Probabilistic liveness assumes good synchrony conditions. For the safety part of the design, we would want to make fewer assumptions and take into account worst-case scenarios where we may be put into a state where we have not seen a new block for a while. For the safety part of the design, we would want to make fewer assumptions and take into account worst-case scenarios where we may be put into a state where we have not seen a new block for a while. As an example, block B may be the head of the chain from epoch 1, but be currently at epoch 3 with no new block built on top of B. In the original Casper FFG, we expect probabilistic liveness, so we would have a different checkpoint at every epoch. However, when we have no synchrony assumptions, in the analysis we would need to differentiate the idea of checkpoint in epoch 2 and checkpoint in epoch 3, even though the best candidate for both is B, which is itself still only in epoch 1. This naturally induces the concepts B2 and B3, which represents the best approximation to a checkpoint in a later epoch if the checkpoint block that should have been there is missing. Also, Casper FFG makes no assumptions about time in the underlying blockchain, only block heights are important, with no notion of slots or epochs. The use of block height is a natural choice in proof-of-work blockchains due to the Poisson process of mining new blocks serving somewhat as a system clock, with blocks coming at fairly irregular times. Casper, as a proof-of-stake protocol, can have blocks coming in at controlled regular intervals as part of the protocol, instead of depending on a random process, so instead the notion of time is explicitly desired in the protocol. To capture this notion of time, each object in our blockchain then naturally requires the knowledge of both the data, captured in a block, and the time, captured in the epoch count, which also leads naturally to the idea of pairs. 4.2 Committees. The point of committees is to split up the responsibilities among the validators. To start, assume the validators have access to a sequence of random length n permutations row 0, row 1. As functions 1, 2, and rightward arrow 1, 2, n. In the scope of this article, we assume we get these random permutations from a random oracle 5. Recall time is split into epochs, of C slots each. Each permutation row j will be used only during epoch j. Its role is to pseudo-randomly select validators into C committees, each of whom has responsibilities for one slot of the epoch. To be precise, during epoch j, we would like to split the set of validators V into C equal size committees. S0, S1, SC1, we assume Cn for easier notation, dealing with roughly equal size committees does not change the essence of our approach. Therefore, for each k set membership symbol 0, 1, C1, we define Sk to be the set of the n/C validators of the form V rho j, S, where Sk, mod C. Note, for an epoch j, the sets S0, S1, SC1. Partition the entire set of validators V1, Vn across all the slots of epoch j, as desired. To summarize, in each epoch j, rho j allows us to shuffle the validators into C committees. Our work does not assume more than this intuition. 4.3 Blocks and attestations. Now, in each slot, the protocol dictates two types of committee work for the committee assigned to their respective slot. One person in the committee needs to propose a new block, and everyone in the committee needs to attest to their head of the chain. Both proposing blocks and attesting mean immediately adding a corresponding message, a block and an attestation, respectively, to the validator's own view and then broadcasting the message to the network. Recall the messages proposing, non-genesis, blocks and publishing attestations have digital signatures. 5. Achieving non-exploitable randomness on the blockchain is itself an interesting problem, stimulating research such as verifiable delay functions. However, in this article we will take this randomness for granted. Both proposing and attesting requires the committee member to run the same fork choice rule HLMD on the validator's own view, which is a variation of the LMD ghost fork choice rule. HLMD's definition requires concepts that we have not introduced yet, so we delay its definition to section 4.6. For now, the only thing we need to know is, like LMD ghost, HLMD takes a view G and returns a leaf block B as the head of the chain, making chain B the canonical chain of G. We now present the responsibilities of the protocol during slot I equals JC plus K, where K set membership symbol 0, 1, C1. All mentions of time are computed from the point of view of the validator's local clock, which we assume to be synced within some delta. Definition 4.2. At the beginning of slot I equals JC plus K, designate validator V equals V rho J, K, i.e., the first member of the committee Sk of epoch J, as the proposer for that slot. The proposer computes the canonical head of the chain in his /her view, i.e., HLMD, view, V, I, equals B, then proposes a block B, which is a message containing 1 slot, B, equals I, the slot number, 2p, B, equals B, a pointer to the parent block. In other words, we always build a block on top of the head of the chain. 3. Nwatests, B, a set of pointers to all the attestations, to be defined next, V has accepted, but have not been included in any nwatests, B, for a block B, who is an ancestor of B. For some implementation-specific data, for example, Eunice paid 4.2 ETH to Brad if we are tracking coins, the semantics of which is irrelevant for us. For dependencies, B depends on P, B, and all attestations in nwatests, B. So for example, if we see a block on the network but do not see its parent, we ignore the block until we see its parent. In typical, honest, behavior, we can assume each slot number that has a block associated with it also has at most one such block in view, NW. By default, Genesis is the unique block with slot 0. A dishonest validator can theoretically create a block with a duplicate slot number as an existing block, but we can suppose the digital signatures and the pseudo-random generator for block proposal selection are set up so such behavior would be verifiably caught. For example, every time a digitally signed block enters the view of a validator, the validator can immediately check if the block proposer is the unique person allowed to propose a block for that respective slot. A validator can also prove the same person proposed 2 blocks in the same slot by just pointing to both blocks. Definition 4.3. At time, I plus 1/2, the middle of slot I equals JC plus K, each validator V in committee SK computes B equals HLMD, view, V, I plus 1/2, and publishes an attestation alpha, which is a message. Containing 1 slot, alpha, equals JC plus K, the slot in which the validator is making the attestation. We will also use EP, alpha, as shorthand for EP, slot, alpha, 2 block, alpha, equals B. For dependencies, alpha depends on block, alpha. So we ignore an attestation until the block it is attesting to is accepted into our view. This is one of the bigger differences between theory and implementation. We discuss this more in section 8. Intuitively, alpha is doing 2 things at once. It is simultaneously a ghost vote for its block and also a Casper FFG vote for the transition between the 2 epoch boundary pairs, akin to Casper's checkpoint blocks.
I don't know what's going on here, but it's lagging a lot. So I think I'm gonna read
Definition
the other
4.4.
stuff here.
Given a block B, we define 6 view
I think I'll
B,
read
the view of
the
B, to be the view consisting of
rest
B
of
and all
these
its ancestors in the
documentations
dependency
using
graph.
the other
We define
text to
view
speech
B,
thing,
the
and I'm
FFG
gonna
view of
do
B,
that
to be view
off stream
LEBB
probably.
B. The
'Cause I'm
definition of view
already
B is
tired
agnostic of the
now.
viewer, in which any view that accepted B can
And
compute an
after
identical
reading all
view
of
B,
this,
so
I'm
we do
gonna
not
get
need to supply a
even more
validator or
tired.
NW into the argument.
So
Intuitively,
it's probably
view
good
B
to
focuses
take
the
a
view to chain
break,
B, and view
and
B looks at a frozen snapshot of view B at the last checkpoint.
after
Casper FFG
only after
operates
the
only on
break,
epoch boundary
read
pairs, so the
the rest
FFG
of
view
the
of a block B extracts
limitation.
exactly the information in chain B that is relevant to Casper
So
FFG.
I read this
We
one,
now define the main
now
concepts
I'm
of
on this
justification.
one.
To start, recall an attestation alpha for Casper
I
contains
didn't
a
fully
checkpoint edge LJ,
understand
alpha, B,
the
rightward arrow LE, alpha, acting as a
algorithm
FFG
here. I
vote between
understood
2
the
epoch boundary
concept,
pairs.
obviously, but
After a couple of new definitions, we can finally explicitly
the
define
thing
these
that
notions.
was kind of
Definition
confusing to me
4.5.
was
We say
the
there is a super-majority link
link
from pair A,
thing.
J to pair
But I
B,
guess
J
it's
if the
because of the
attestations
number of
with checkpoint edge A,
attestations
J,
for each
B,
link.
rightward arrow B,
Because
J have total weight more than
This
23 of the total
this
validator
one that
stake.
I'm reading
In
now
this case, we write
made
A,
it
J,
more
J,
clear, I
rightward
think,
arrow B, J.
where
Definition 4.6.
it's
Given a view G,
determined
we define a set
that
J, G,
at some
of justified
points
pairs as follows.
they're gonna be
Genesis 0, set membership symbol J, G,
these checkpoints,
if A, J, set
and
membership symbol J, G, and
they are
A,
decided
J,
by
J.
this number,
Rightward arrow
which
B,
I think
J,
is H
then
or
B,
K or
J,
something
set
like
membership
that
symbol
in
J,
the
G as well.
document that they
If
talk
B,
about.
J, set membership symbol J,
And then
G. We say B is justified in G
From
during
each
epoch
of
J
these
definition
checkpoints,
4.7.
you're gonna
Given an attestation alpha,
deduce
let
the
B equals
history
LEBB, block, alpha. We define
based
1
on
LJ,
the number
alpha,
of
the last justified pair of
attestations,
alpha,
and
the
the one
highest
that has
attestation
the,
epoch, or last
the highest
justified pair
rate
in
of attestations
block,
is
alpha,
going to be the
equals view,
canonical chain.
2 LE, alpha, the last epoch boundary pair of alpha,
So
B,
you
EP, slot,
works like
alpha.
a
While we define
frequency
J,
of
G, for any view
checkpoints
G, we are typically only interested in J,
times
G,
the
for G
weight of
equals view,
attestation
B.
of all the checkpoints.
We can think of each chain as
So
having
it's
its own state of
very
justified
similar
blocks
to
slash
proof
pairs that
of
is
work,
updated only at the epoch boundaries.
in the
0, 1,
sense that
63,
you're getting
64,
the highest
64,
block, but
130,
it's
129,
fundamentally different because
131,
in proof of work is
180,
all about,
180,
about the mining
193.
power,
Alpha, epoch
and
0, epoch 1,
here
epoch 2,
is
epoch 3.
about the weight
Figure
of
5. A validator's view
attestation
G as she writes an attestation in
based
epoch
on
3.
the
During epoch 1,
checkpoints.
latency issues make her not see any
And
blocks.
then
So block
there
64 is
needs
both
to
ebb,
be
193, 1, and ebb, 193,
disincentive to
2.
cheat the
She ends up
system,
writing an
so
alpha with a
that's
ghost
why
vote
you
for block.
put
Alpha equals
those
193 in
slashing
a FFG vote.
penalties
Checkpoint edge, single arc
of
edge, 64, 2, B.
inactivity
Rightward arrow,
and the
180,
other one that
3,
I
for
forgot.
alpha. We use slot numbers for blocks, so block 0 is just Genesis.
But
Blocks in red are
obviously
justified
it's more
in G.
nuanced than
Double
that,
edges
and
corresponding to supermajority
I
links.
still have a
Example
hard time
4.8.
understanding
A validator runs HLMD, G,
the
on her view G to obtain her head of the chain, which is block
nuances.
193. She is then
It's gonna
supposed
be
to
hard
attest to
to understand the
193 with an
code as
attestation
well, I
alpha.
think.
On chain 193, portrayed in figure
So
5,
that's
LE,
why
alpha
I
equals
think I should read this
183,
off
even
stream
though
and
EP
probably
180
read
equals 2,
once
because our
more
attestation has epoch 3, and we were
another
looking for
time.
364 equals 192 but did not see it.
This
One
has
can
to be the
imagine.
first thing that
Since
I
we have
read,
tyrannically
I think,
overworked the
another
notation of
time.
u by this point, but there should be no ambiguity when we know the
The
type of its
problem is
parameter.
that
Like in our
I
figure,
always
that
have
we pull up block
issues
180
with
to
the
show
way
that it is
that
ep
people
193
write
3.
stuff on these papers
Input
as
view
well because of the
193 equals
mathematics.
view 180.
It's
The
very
last justified
confusing the
by
way
epoch
that
number,
is written.
not slot. Pair is 64 2.
A
So
lot of
LJ alpha
times
equals
there are a
64
lot
2.
of easier
Note that
ways
this
to
relies on view
explain, but then
180
because it is
to include
on
attestations worth at
like
least
this
2
paper
n slash 3.
format,
Stake
yeah,
pointing
it
to
should be
64
written
2.
with that notation. That
It would be
is
possible to have a case where this
gets
did not happen by
confusing.
180, but the chain does see 2 n slash
But
3
the
worth of
algorithm
attestations by
doesn't seem to be
193.
difficult to
In this case,
understand. A
64
greedy
2
algorithm
is in J,
to
G, but 64
determine the
2 is
canonical
not in
chain.
J.
And then obviously the concept
193.
is
So the resulting checkpoint
you're
edge would
gonna
be
have
example
forks
64 1
because
B.
of this
Rightward
either
arrow
latency or
183
inactivity
instead as
from
summing the attestations for
some
64
of the
1 are in view
nodes
180.
or
The checkpoint
from
edge could even end up being
attacks, and
0
then
0
you
V.
decide
Rightward
which
arrow
one is going to be
183 if
the one,
100
then
and 80
use
did not see those
the algorithm
attestations.
to
Note that
do
this
it
is very possible if the attestations for
based on
64
this
1
weight
were only
of
included in the blocks that forked off of
attestations.
chain 193,
not
such as block
that
130,
hard,
as the
the
forking may be an
concepts.
indication of network problems
The
causing
hard-
those
hardest
attestations to
part
be
is
temporarily
understanding
unavailable to
the nuance
validators on
and then
chain
the context of
193. Everything here is analogous
thinking
to Casper
about
FFG.
potential
Inside the chain
exploits
of block,
of
alpha,
MEVs.
is a subchain created by the epoch boundary blocks of that chain, starting from Genesis and ending at B equals LEBB, alpha. We want to focus on this subchain of blocks,
Oh, looks
represented
like
by pairs to allow for
this
boundary cases,
is
and justify
running
epoch boundary
still.
pairs with many attestations. This subchain is exactly what's captured by view.
I think I'm just. I think that was running the whole time I was talking. I didn't notice because I'm using the other headphone. Yeah, whatever. I'm gonna read that later. I think I will finish reading this once here, and then I'm gonna take a break, and then I think I'm gonna read the rest of the documentation off stream. Maybe I think actually what I'm gonna do, because I think I wanted to read the yellow paper on stream as well. But I'm thinking about reading the other ones off stream and then saving this one to read on stream tomorrow before I start studying the code. I also have to finish this article here about MEV, and then because the thing is I want to finish these documents first before, because the idea that I have now is I'm going to finish all of this stuff, then I get like a superficial understanding. Oh, like, yeah, superficial understanding, then I'm gonna write these articles, and then as I write these articles, I'm gonna have to get the links for the other stuff, and then I'm gonna review them as I write them. So that's the plan. After I finish all of these documents here, then I'm gonna go finish these articles here, and then as I finish the articles, I go back to reading the stuff to complement the articles. And then after that, I study the code, I think. Yep. Okay, so we're just gonna read the rest of the stuff. I'll think about it later.
An explanation of the sharding plus DOS proposal. Along with proof of sharding plus DOS proposal. Along with proof of stake, the other central feature in the Eth2 design is sharding. This proposal introduces a limited form of sharding, called data sharding. As per the rollup-centric roadmap, the shards would store data and attest to the availability of 250 KB-sized blobs of data. This availability verification provides a secure and high-throughput data layer for layer 2 protocols such as rollups. To verify the availability of high volumes of data without requiring any single node to personally download all of the data, two techniques are stacked on top of each other: I, attestation by randomly sampled committees, and 2, data availability sampling, DOS. Eli 5, randomly sampled committees. Suppose you have a big amount of data, think 16 megabytes, the average amount that the Eth2 chain will actually process per slot, at least initially. You represent this data as 64 blobs of 256 KB each. You have a proof of stake system with 6,400 validators. How do you check all of the data without I, requiring anyone to download the whole thing, or 2, opening the door for an attacker who controls only a few validators to sneak an invalid block through? We can solve the first problem by splitting up the work. Validators 100 have to download and check the first blob, validators 101, 200 have to download and check the second blob, and so on. The validators in each of these subgroups, or committees, simply make a signature attesting that they have verified the blob, and the network as a whole only accepts the blob if they have seen signatures from the majority of the corresponding commit. But this leads to a problem. What if the attacker controls some contiguous subset of validators, e.g. 1971, 2070? If this were the case, then even though the attacker controls only 1.5% of the whole validator set, they would dominate a single committee. In this case, they would have 70% of committee 20, containing validators 2001, 2100, and so they would be able to control the committee and push even invalid/unavailable blobs into the chain. Random sampling solves this by using a random shuffling algorithm to select the committees. We use some hash as the seed of a random number generator, which we then use to randomly shuffle the list 1, 6400. The first 100 values in the shuffled list are the first committee, the next 100 are the second committee, etc. The RNG seed is chosen after validators deposit and each validator's index is fixed, so the attacker has no way to try to put all their validators into a single commit. They may get lucky once in a while by random chance, but only if they control a very large fraction, 1/3, of all validators. Eli 5, Data Availability Sampling. Data availability sampling is in some ways a mirror image of randomly sampled committees. There is still sampling going on, in that each node only ends up downloading a small portion of the total data, but the sampling is done client-side, and within each blob rather than between blob. Each node, including client nodes that are not participating in staking, checks every blob, but instead of downloading the whole blob, they privately select n random indices in the blob, each n equals 20, and attempt to download the data at just those positions. The goal of this task is to verify that at least half of the data in each blob is available. If less than half of the data is available, then it is almost certain that at least one of the indices that any given client samples will not be available, and so the client will reject the blob. Note that this mechanism is efficient, as a client only needs to download a small portion of each blob to verify its availability, and also 2, highly secure, as even a 51% attacker cannot trick a client into accepting unavailable blob. To cover the case that an attacker makes available 50 to 99% of the data, which can easily lead to some clients accepting and other clients rejecting the blob at first, we use a technology called erasure code. Erasure coding allows us to encode blobs in such a way that if at least half of the data in a blob is published, anyone in the network can reconstruct and republish the rest of the data. Once that republished data propagates, the clients that initially rejected the blob will converge to accept it. Note, there is no time limit to accepting a blob. A client accepts a blob as available whenever it has received responses to all of its sample indices. The simplest mathematical analogy to understand erasure coding is the idea that 2 points are always enough to recover a line. If I construct the file consisting of 4 points, 1, 4, 2, 7, 3, 10, 4, 13, all of which are on one line, then if you have any 2 of those points, you can reconstruct the line and compute the remaining 2 points. We assume the x coordinates 1, 2, 3, 4 are a fixed parameter of the system, not the file creator's choice. With higher degree polynomials, we can extend this idea to create 3 of 6 files, 4 of 8 files, and generally n of 2 n files for any arbitrary n, with the property that if you have any endpoints of the file, you can compute the remaining ones out of 2 n which are missing. It is also possible that an attacker by default makes none of the block available, and only selectively publishes chunks in response to sample queries that it sees, but this would only fool a small number of clients before the attacker would need to publish more than half the block to answer all the queries. We assume clients publicly rebroadcast all responses they receive. We use polynomial commitments, specifically, k commitments, instead of Merkle roots as pointers to these data blobs, because polynomial commitments let us easily prove that a given value actually is the correct evaluation of a particular degree and polynomial at the desired coordinate. Otherwise, we would have to either prove, using SNARKs, for example, that a Merkle root encodes a low-degree polynomial, the likely eventual solution once we need something post-quantum, but too expensive for now, or rely on fraud proofs which can be broadcast in case of incorrect encoding, adding high complexity and more synchronicity assumptions. Why not use just committees and not DOS? Using only committees has the following weaknesses. Weaker protection in case of an actual 51% attack. In current, non-scalable blockchains, a 51% attack can only revert transactions or censor. It cannot push through invalid block. A committee-based system would remove this guarantee. Furthermore, requires a specific threshold. Furthermore, it would be very difficult to effectively penalize a 51% attacker, as only a very small portion of their deposits, the deposits that participated in that particular committee, would be provably implicated in the malicious behavior and could conceivably be penalized. Requires a specific threshold. What percentage of a committee needs to approve a blob for the chain to accept it? If that threshold is high, then the sharding functionality shuts down entirely in periods where few validators are online. If the threshold is low, or is some dynamic mechanism like a threshold share only of recently online validators, then an attacker can try to knock many nodes offline to increase their share of the remaining online nodes and push a bad blob through. DOS is slightly easier to make quantum proof than committees, which would require post-quantum aggregate signatures. Why not just use DOS and not committee? Using only DOS has the following weaknesses. DOS is a new and untested technology, with key components, e.g. this, having literally been developed in the last year, so having committees as a backstop seems wise, in case DOS breaks or takes an unexpectedly long time to develop. DOS has higher latency than committee. DOS has more edge cases, which committees can help plug. One particular example is that in a DOS-only system, it's difficult to avoid the beacon block proposer being one of the first actors to make DOS queries to verify blob availability. This creates heightened risk that an attacker will publish unavailable blobs and release responses only to the proposer's queries. This will not cause the rest of the network to accept the unavailable blobs, but it may lead to easy attacks with the goal of causing beacon blocks constructed by honest proposers to be rejected and fork away from the canonical chain. Committees can remedy this. Committees are more forward compatible with future edition of in-shard execution. Why is data availability important and why is it hard to solve? This has been discussed at length in other materials too long to copy here. I recommend a note on data availability and erasure coding, the original introduction to the data availability problem. The paper by Alberto Sonino, Mustafa Al-Bassam, and Vitalik Buterin expanding on these concepts. The base layers in functionality escape velocity. The data availability problem. A key takeaway is that BitTorrent, IPFS and similar systems do not solve data availability. While BitTorrent is a good scalable data publishing source, it does not provide a guarantee of consensus about whether or not a piece of data is available, leaving open the possibility of inextricable edge case attacks where nodes disagree on when a piece of data was published, preventing hybrid layer 2 protocols from work. To achieve consensus on data availability, the stronger techniques described in this document are required. How does sharding work on the P2P layer? In order to achieve the scalability gains of sharding, we need a P2P system that avoids the need for every node to download all the data. Fortunately, we have a form of P2P layer sharding already live in phase 0. Specifically, there are 64 subnets that are being used for aggregation of attestation. Each validator need only be on the main, global subnet, and 2, their own attestation aggregation subnet. They do not receive any data from the other 63 attestation aggregation subnet. In committee plus DOS sharding, we expand this out to a grid structure, with 2048 horizontal subnets, 1 for each shard, slot, parent and epoch, and 2048 vertical subnets, 1 for each index within a blob. During each slot, we select a proposer for each shard. Each proposer is entitled to propose a blob, a lump of arbitrary data of size up to 512 KB, which we interpret as a collection of samples of 512 bytes each, along with the erasure code extension as well as extra proofs to allow each part of the blob to be independently verified. Structure of a blob. The full body of a blob consists of the original data, the extended data, and the proofs, though if desired, for data efficiency the extended data can be left out as it is relatively fast for each node receiving the blob to reconstruct it. The header of a blob is the kate commitment to the blob, plus a bit of other miscellaneous data, slot, shard, length proof, and a signature from the proposed blob publication process. When a blob is published, the header is published on the global subnet, and the blob is published on the horizontal subnet corresponding to the slot number and shard I for each 3 and 0. Samples underscore per underscore block 1. The ITH sample is published on vertical subnet 3, along with the proof that the ITH sample actually is the evaluation of the polynomial committed to in the header at the ITHX coordinate. In practice, there would be 2048 horizontal subnets to allow one horizontal subnet per shard, slot, combo in each epoch. This is done to ensure that each validator can join a single horizontal subnet where they will only receive the blob corresponding to the committee that they were assigned to, in addition to the small number of vertical subnets they join to participate in sampling. Each validator must join the following subnets. The global subnet, the horizontal subnet corresponding to the shard, slot, combo, i.e. the committee, that they were assigned to, the vertical subnets corresponding to indices that they are assigned to. Each validator computes this for themselves using a private seed. There is a procedure by which a blob, broadcasting blocks. There is a procedure by which a blob proposer can distribute the samples to all subnets without the proposer being part of the subnets themselves. This procedure is as follows. Publication, the proposer publishes the blob, along with a proof for each sample, on the appropriate horizontal subnet. Direct sample distribution, the other participants on the horizontal subnet publish the chunks to each vertical subnet that they personally are in. Indirect sample distribution, proposers reveal a few, think, 4, of the vertical subnets they are on to their peers. Hence, each participant in the horizontal subnet can also look at the vertical subnets that their peers are on, and broadcast the appropriate chunks to those peers. For example, if the chunk size is 512 bytes, and the maximum data blob size, without erasure code expansion, is 512 KB, then with erasure code expansion it's 1 megabyte, so there would be 2048 vertical subnet. If each node has 15 private vertical subnets and 5 public vertical subnets, and 50 peers, and assuming a worst-case scenario where there are 128 members in each horizontal subnet, just the committee, then the subnet members alone would directly publish to 128 * 20 equals 2,560 subnets, 1461 after taking into account redundant publishing, and including peers this would increase to 128 * 4 * 50 equals 25,600 subnets, all 2048 subnets 99.2% of the time after taking into account redundant publishing. Note that it is theoretically possible for a malicious block proposer to publish samples to the vertical subnets without publishing the full block. To cover this case, we add a procedure by which a partially published, meaning equals 50% available but not 100% available, block can be self-healed. The self-healing procedure has 3 basic steps. Reverse distribute, a procedure identical to the distribution procedure above is used, except that in this case peers on a vertical subnet propagate samples from that vertical subnet to the horizontal subnet corresponding to the blob that the sample is a part of. Reconstruct, if there are equals 1024 samples on the horizontal subnet, or generally, half of the sample count, anyone can reconstruct the full blob, and publish the reconstructed blob to the horizontal subnet. Distribute, the distribution procedure above is repeated. How does the beacon chain work? In each slot, we randomly select a proposer for each of the 64 shard. The proposer has the right to create a shard blob, and broadcast it using the procedure above, as well as broadcasting the shard header of the blob to the global subnet. The shard header can be included in the beacon chain in that slot or any subsequent slot in the same or next epoch. The beacon chain keeps track of a list of pending shard header object. A pending shard header stores I, the key information in a shard header, the shard in slot, a commitment to the blob, and its length, and 2, a bit field keeping track of which validator is out of a randomly selected committee. In fact, the same committees is already introduced in phase 0, signed off on the blob. The attestation data struct is expanded to include a shard underscore header underscore root, a root hash of the shard header that the given attester is voting for. Attesters can also vote for an empty root if they see no valid and available shard blob for the shard slot pair they have been assigned to. If a shard header gets the support of 2/3 of the committee, it is confirmed immediately. If a shard header has the support of a larger share of the committee than any other shard header, including the default empty one, at the end of the next epoch, then it is confirmed at the end of that epoch. Fork choice rule. The fork choice rule is changed so that a block is only eligible for consideration if all blobs confirmed in that block or its ancestors have passed an availability check. This is called tight coupling. If a chain points to, meaning, has confirmed, even a single invalid blob, the whole chain is considered invalid. This is a key difference from sidechain architectures, where it's possible for a sidechain to fail while the central chain remains valid. See here for a further exploration of tight coupling and why it's valuable. The low validator count case. If there are less than 262,144 validators, 32 slots * 64 shards * 128 minimum committee size, then instead of selecting a proposer for all shards, we select a proposer for a limited subset of shards, cycling through the shards. If there were 32 * 128 * 50 validators, and its slot n the start shard was 0, then slot n will assign a proposer for shards 0, 49, slot n plus 1 will assign a proposer for shards 50, 63 and 0, 35, slot n plus 2 will assign a proposer for shards 36, 63 and 0, 21, etc. This is done to ensure that committee sizes remain sufficient even under conditions of low participation. Gas prices for shard data. An EIP 1559-like mechanism is added by which shard data is charged for per byte, and this price is adjusted. If blocks are on average more than 50% full, it is increased, and if blocks are on average less than 50% full, it is decreased. Hence, an average block size of 50% is targeted. Security assumptions. The data blob only sharding design is powerful because it is surprisingly light on security assumptions compared to other sharding schemes. In particular, it avoids both honest majority assumptions, as DOS can detect unavailable blobs pushed by a majority, and timing assumptions, as unlike earlier DOS schemes, this scheme uses kate commitments instead of fraud proofs, and so does not rely on any assumption that fraud proofs will be broadcasted quickly enough. A malicious 51% coalition can censor blobs, but 51% censorship is possible in non-sharded chains as well. The main new assumption that is added is the honest minority DOS assumption, that there are enough nodes sampling that an attacker cannot satisfy them without publishing more than half the blob. If there are 2048 samples in a blob, with 1024 needed to recover, 2048 * ln, 2, equals 1419 taking into account that some clients will sample the same points, and each client takes 20 samples, then the system is secure if more than 70 clients are sampling each shard. Forward compatibility. The data blob only sharding design is forward compatible with many approaches for adding execution in shards if this is later desired. In particular, the scheme could be modified to require blobs to include a pre-state and post-state root, and we could use either fraud proofs or ZK snarks to verify that the state transition in a blob is correct. Note that in either option, ensuring correctness of execution in shards would not depend on any honest majority assumption. Enjoy. 8. Other resources. Proto-Lambda is work in progress implementation. KZG polynomial commitments. KZG. Introduction. I want to try and give an introduction to the commitment scheme introduced by K. Zavarosha and Goldberg. This post does not aim to be mathematically or cryptographically rigorous or complete. It is meant to be an introduction. This scheme is often also called K polynomial commitment scheme, pronounced Kate. As a polynomial commitment scheme, it allows a prover to compute a commitment to a polynomial, with the properties that this commitment can later be opened at any position. The prover shows that the value of the polynomial at a certain position is equal to a claimed value. It is called a commitment, because having sent the commitment value, an elliptic curve point, to someone, the verifier, the prover cannot change the polynomial they are working with. They will only be able to provide valid proofs for one polynomial, and if they are trying to cheat, they will either fail to produce a proof or the proof will be rejected by the verifier. Prerequisites. I highly recommend reading Vitalik Buterin's post on elliptic curve pairings, if you aren't familiar with finite fields, elliptic curves, and pairing. Comparison to Merkle trees. If you are familiar with Merkle trees, I want to try to give a bit more of an intuition on the difference between those and K commitment. A Merkle tree is what cryptographers call a vector commitment. Using a Merkle tree of depth dd, you can compute a commitment to a vector, that is, a list of elements of fixed length, a 0, a 2 d1 a underscore 0, backslash l dots, a underscore 2 caret d1. Using the familiar Merkle proofs, you can provide a proof that an element a underscore I is a member of this vector at position 2 using dd hashes. We can actually make a polynomial commitment out of Merkle trees. Recall that a polynomial p(x) of degree n is nothing other than a function. P(x) equals sigma ni equals 0 pi zip, x equals backslash sum underscore I equals 0 caret n p underscore ix caret I, where the pip underscore I are the coefficient of the polynomial. We can easily commit to a polynomial of degree n equals 2 d1 n equals 2 caret d-1 by setting a I equals p underscore I equals p underscore I and computing the Merkle root of its coefficients. Proving an evaluation means that the prover wants to show to the verifier that p z equals y p z equals y for some z's. The prover can do this by sending the verifier all the pip underscore I and the verifier computing that p z is indeed y. This is of course an extremely stupid polynomial commitment, but it will help us understand what the advantages of real polynomial commitments are. Let's haze a look at the properties. The commitment size is a single hash, the Merkle root. A cryptographic hash of sufficient security typically needs 256 bits, 32 bytes. To prove an evaluation, the prover needs to send all the pip underscore I, so the proof size is linear in the degree of the polynomial, and the verifier needs to do linear work. They need to evaluate the polynomial at the place z by computing p z equals sigma ni equals 0 pitsub z equals backslash sum underscore I equals 0 caret n p underscore I z caret I. The scheme does not hide anything about the polynomial. The prover sends the whole polynomial in the clear, coefficient by coefficient. Now let's look at what the Kate scheme achieves on these metrics. The commitment size is one group element of an elliptic group that admits pairings. For example, with BLS 12 underscore 381, that would be 48 bytes. The proof size, independent from the size of the polynomial, is also always only one group element. Verification, also independent from the size of the polynomial, requires a two-group multiplications and two pairings, no matter what the degree of the polynomial is. The scheme mostly hides the polynomial. Indeed, an infinite number of polynomials will have exactly the same Kate commitment. However, it is not perfectly hiding. If you can guess the polynomial, for example because it is very simple or in a small set of possible polynomials, you can find out which polynomial was committed. Additionally, it is actually possible to combine the proof for any number of evaluations in one group element. These properties make the Kate scheme very attractive for zero-knowledge proof systems, such as Plunk and Sun, but they also make it very interesting for a more mundane purpose and use it as a vector commitment, which we will come to below. On elliptic curves and pairing. As mentioned in the prerequisites, I strongly recommend Vitalik Buterin's post on elliptic curve pairings. It includes all the basics needed to understand this post, in particular finite fields, elliptic curves, and pairing. Let g1 backslash math g underscore 1 and g2 backslash math g underscore 2 be two elliptic curves with a pairing e.g. 1 times g2 rightward arrow gte, backslash math g underscore 1 backslash times backslash math g underscore 2 backslash right arrow backslash math g underscore t. Let pp be the order of g1 backslash math g underscore 1 and g2 backslash math g underscore 2, and gg and hh be generators of g1 backslash math g underscore 1 and g2 backslash math g underscore. We will use a very useful shorthand notation. For any X set membership symbol FPX backslash in backslash math def underscore p trusted setup. Let's assume we have a trusted setup, so that for some secret SS, the elements si1 s caret I underscore 1 and si2 s caret I underscore 2 are available to both prover and verifier for I equals 0, and 1 I equals 0, backslash l dots, and 1. One way to get this secret setup is to have an air-gapped computer compute a random number SS, compute all the group elements SIXS caret I underscore X, and only send those elements, and not SS, over a wire, and then burn that compute. Of course this is not a great solution because you would have to trust whoever operated that computer that they didn't build a secret communication channel that tells them the secret SS. In practice this is usually implemented via a secure multi-party computation, MPC, which allows creating these group elements by a group of computers in a way such that no single computer will know the secret SS, and all of them would have to collude, or be compromised, in order to reveal it. Note one thing that is not possible. You can't do this by just selecting a random group element S1 S underscore 1, for which SS is unknown, and compute the other group elements from it. It is impossible to compute S2 1 S caret 2 underscore 1 without knowing SS. Now, elliptic curve cryptography basically tells us that it's impossible to find out what SS actually is from the trusted setup group element. It's a number in FP backslash math def underscore p, but the prover cannot find the actual number. They can only do certain computations with the elements that they are given. So for example, they can easily compute things like CSI1 equals CSIG equals CSI1 CS caret I underscore 1 equals CS caret IG equals CS caret I underscore 1 by elliptic curve multiplication, and since they can add elliptic curve points, they can also compute something like CSI1 plus DSJ1 equals CSI plus DSJ, G equals CSI plus DSJ1 CS caret I underscore 1 plus DS caret J underscore 1 equals CS caret I plus DS caret J, G equals CS caret I plus DS caret J underscore 1. In fact, if p x equals sigma ni equals 0 pi zip, x equals backslash sum underscore I equals 0 caret n p underscore I x caret I is a polynomial, the prover can compute. This is interesting. Using this trusted setup, everyone can basically evaluate a polynomial at some secret point SS that nobody knows, except they don't get the output as a natural number. They only get the elliptic curve point p s 1 equals p s g p s underscore 1 equals p s g. But it turns out that this is already really powerful. K commitment. In the K commitment scheme, the element c equals p s 1 c equals p s underscore 1 is the commitment to the polynomial p x p x. Now you may ask the question, could the prover, without knowing SS, find another polynomial q x is not equal to p x q x backslash n p x that has the same commitment, such that p s 1 equals q s 1 p s underscore 1 equals q s underscore 1. Let's assume that this were the case. Then it would mean that p s q s 1 equals 0 1 p s q s underscore 1 equals 0 underscore 1, implying p s q s equals 0 p s q s equals 0. Now r x equals p x q x r x equals p x q x is itself a polynomial. We know that it's not constant because p x is not equal to q x p x backslash n q x. It is a well-known fact that any non-constant polynomial of degree n can have at most n zeros. This is because if r, z, equals 0 r, z, equals 0, then r, x, is divisible by the linear factor xz, since we can divide by one linear factor for each 0, and each division reduces the degree by 1, so there can't be more than n.2. Since the prover doesn't know ss, the only way they could achieve that p, s, q, s, equals 0 p, s, q, s, equals 0 is by making p, x, q, x, equals 0 p, x, q, x, equals 0 in as many places as possible. But since they can do that in at most n places, as we've just proved, they are very unlikely to succeed, since n is much smaller than the degree of the curve pp. The probability that ss will be one of the points they chose to make p, x, equals q, x, p, x, equals q, x, will be vanishingly tiny. To get a feeling for this probability, suppose we use the largest trusted setups currently in existence, where n equals 228, n equals 2^28, and compare it to the curve order p2256 p backslash approximate 2^256. The probability that any given polynomial q, x, that the attacker has crafted to agree with p, x, in as many points as possible, n equals 228, n equals 2^28 points, results in the same commitment, p, s, equals q, s, p, s, equals q, s, will only be 228/2256 equals 228 256 2106 92^28. That is an incredibly low probability and in practice means the attacker cannot pull this off. Multiplying polynomials. So far we have seen that we can evaluate a polynomial at a secret point ss, and that gives us a way to commit to one unique polynomial, in the sense that while there are many polynomials with the same commitment c equals p, s, 1c equals p, s, underscore 1, they are impossible to actually compute in practice. Cryptographers call this computationally binding. However, we are still missing the ability to open this commitment without actually sending the whole polynomial over to the verifier. In order to do this, we need to use the pair above. We noticed that we can do some linear operations with the secret elements. For example, we can compute p, s, 1p, s, underscore 1 is a commitment to p, x, and we could also add two commitments for p, x, and q, x, to make a combined commitment for p, x, plus q, x, plus q, x, p, s, 1 plus q, s, 1 equals p, s, plus q, s, 1p, s, underscore 1 plus q. If we can do that, what we're missing is an ability to multiply two polynomials. If we can do that, we can use some cool properties of polynomials to achieve what we want. While elliptic curves themselves don't allow this, luckily we can do it with pairings. We have that, where we introduce the new notation xt equals e, gh, xx underscore t equals e, g, h, caret x. So while we unfortunately can't just multiply two field elements inside an elliptic curve and get their product as an elliptic curve element, this would be a property of so-called fully homomorphic encryption or FHE. Elliptic curves are only additively homomorphic. We can multiply two field elements if we committed to them in different curves. One in g1 backslash math g underscore 1 and one in g2 backslash math g underscore 2, and the output is a gt backslash math g underscore t element. This gets us to the core of the Kate proof. Remember what we said about linear factors earlier. A polynomial is divisible by xz if it has a 0 at z. It is easy to see that the converse is also true. If it is divisible by xz, then it clearly has a 0 at zz. Being divisible by xz means that we can write p, x, equals xz, q, x, p, x, equals xz, backslash dot q, x, for some polynomial q, x, and this is clearly 0 at x equals z, x equals z. Now let's say we want to prove that p, z, equals yp, z, equals y. We will use the polynomial p, x, yp, x, y. This polynomial is clearly 0 at zz, so we can use the knowledge about linear factor. Let q, x, be the polynomial p, x, yp, x, y divided by the linear factor xz, xz, i.e. which is equivalent to saying that q, x, xz, equals p, x, yq, x, xz, equals p, x. Kate proofs. Now a Kate proof for the evaluation p, z, equals yp, z, equals y is defined as pi equals q, s, 1 backslash pi equals q, s, underscore 1. Remember the commitment to the polynomial p, x, is defined as c equals p, s, 1c equals p, s, underscore 1. The verifier checks this proof using the following equation. Note that the verifier can compute sc to sc underscore 2, because it is just a combination of the element s to s underscore 2 from the trusted setup, and zz is the point at which the polynomial is evaluated. Equally they know yy is the claimed value p, z, thus they can compute y1 y underscore 1 as well. Now why should this check convince the verifier that p, z, equals yp, z, equals y, or more precisely, that the polynomial committed to by cc evaluated at zz is y? We need to evaluate two properties, correctness and soundness. Correctness means that, if the prover followed the steps as we defined, they can produce a proof that will check out. This is usually the easy part. Soundness is the property that they cannot produce an incorrect proof. They cannot trick the verifier into believing that p, z, equals yp, z, equals y for some y is not equal to yy backslash n. Let's start by writing out the equation in the pairing group. Correctness should now be immediately apparent. This is just the equation q, x, xz, equals p, x, yq, x, xz, equals p, x, y evaluated at the random point ss that nobody knows. Now, how do we know it's sound and the prover cannot create fake proofs? Let's think of it in terms of polynomials. If the prover wants to follow the way we sketched out to construct a proof, they have to somehow divide p, x, yp, x, y by xz, but p, z, yp, z, y is not 0, so they cannot perform the polynomial division, as there will always be a remainder. So this clearly doesn't work. So then they can try to work directly in the elliptic group. What if, for some commitment cc, they could compute the elliptic group element? If they could do this, they could obviously just prove anything they want. Intuitively, this is hard because you have to exponentiate by something that involves ss, but you don't know anything about ss. To prove it rigorously, you need a cryptographic assumption about proofs with pairings, the so-called QQ strong SDH assumption 3. Multi-proofs. So far we have shown how to prove an evaluation of a polynomial at a single point. Note that this is already pretty amazing. You can show that some polynomial that could be any degree, say 2282/28, at some point takes a certain value, by only sending a single group element, that could be 4848 bytes, for example in BLS 12_381. The toy example of using Merkle trees as polynomial commitments would have needed to send 2282/28 elements, all the coefficients of the polynomial. Now we will go one step further and show that you can evaluate a polynomial at any number of points and prove this, still using only one group element. In order to do this, we need to introduce another concept, the interpolation polynomial. Let's say we have a list of kk points, z0 y0, z1 y1, zk1 yk1, z underscore 0, y underscore 0, z underscore 1, y underscore 1, backslash l dots, z underscore k1, y underscore k1. Then we can always find a polynomial of degree less than kk that goes through all of these points. One way to see this is to use Lagrange interpolation, which give an explicit formula for this polynomial I, x. Now let's assume that we know p, x, goes through all these points. Then the polynomial p, x, will clearly be 0 at each z0, z1, zk1, z underscore 0, z underscore 1, backslash l dots, z underscore k1. This means that it is divisible by all the linear factors, xz0, xz1, xzk1, xz underscore 0, xz underscore 1, backslash l dots, xz underscore k1. We combine them all together in the so-called zero polynomial. Now, we can compute the quotient. Note that this is possible because p x I x p x I x is divisible by all the linear factors in z x z x, so it is divisible by the whole of z x z x. We can now define the Kate multi-proof for the evaluations z0y0, comma, z1y1, comma, zk1yk1, z underscore 0, y underscore 0, z underscore 1, y underscore 1, backslash l dots, z underscore k1, y underscore k1 pi equals q, s, 1 backslash pi equals q, s, underscore 1. Note that this is still only one group element. Now, to check this, the verifier will also have to compute the interpolation polynomial I, x, and the zero polynomial z, x, z, x. Using this, they can compute z, s, 2z, s, underscore 2 and I, s, 1I, s, underscore 1, and thus verify the pairing equation. By writing out the equation in the pairing group, we can easily verify it checks out the same way the single point Kate proof does. This is actually really cool. You can prove any number of evaluation, even a million, by providing just one group element. That's only 48 bytes to prove all these evaluations. Kate is a vector commitment. While the Kate commitment scheme is designed as a polynomial commitment, it actually also makes a really nice vector commitment. Remember that a vector commitment commits to a vector a0, and 1 a underscore 0, backslash l dots, a underscore n1 and lets you prove that you committed to a underscore I for some 2. We can reproduce this using the Kate commitment scheme. Let p x be the polynomial that for all 2 evaluates as p I equals I equals a underscore. We know there is such a polynomial, and we can for example compute it using Lagrange interpolation. P x equals n1 sigma I equals 0 and 1 pi j equals 0 j. Now using this polynomial, we can prove any number of elements in the vector using just a single group element. Note how much more efficient, in terms of proof size, this is compared to Merkle trees. A Merkle proof would cost long backslash log n hashes to even just prove one element. Further reading. We are currently exploring the use of Kate commitments in order to achieve a stateless version of Ethereum. As such, I highly recommend searching for Kate in the ETH research forums to find interesting topics of current research. Another great read from here is Vitalik's Introduction to Plunk, which makes heavy use of polynomial commitments, and the Kate scheme is the primary way this is instantiated. https://www.iac. This result is often misquoted as fundamental theorem of algebra. But the fundamental theorem of algebra is actually the inverse result, only valid in algebraically closed fields, that over the complex numbers, every polynomial of degree n has n linear factors. The simpler result here unfortunately doesn't come with a short catchy name, despite arguable being more fundamental to algebra. Dark mode toggle. How do trusted setups work? 2022 March 4 airing. See also Dang Krad Feist's article on KZG polynomial commitments. Special thanks to Justin Drake, Dang Krad Feist, and Chi-Cheng Liang for feedback and review. Many cryptographic protocols, especially in the areas of data availability sampling and ZK snarks, depend on trusted setups. A trusted setup ceremony is a procedure that is done once to generate a piece of data that must then be used every time some cryptographic protocol is generating. This data requires some secret information. The trust comes from the fact that some person or some group of people has to generate these secrets, use them to generate the data, and then publish the data and forget the secret. But once the data is generated, and the secrets are forgotten, no further participation from the creators of the ceremony is required. There are many types of trusted setup. The earliest instance of a trusted setup being used in a major protocol is the original Zcash ceremony in 2016. This ceremony was very complex, and required many rounds of communication, so it could only have 6 participants. Everyone using Zcash at that point was effectively trusting that at least one of the 6 participants was honest. More modern protocols usually use the powers of tau setup, which has a 1 of n trust model with n typically in the 100. That is to say, hundreds of people participate in generating the data together, and only one of them needs to be honest and not publish their secret for the final output to be secure. Well-executed setups like this are often considered close enough to trustless in practice. This article will explain how the KZG setup works, why it works, and the future of trusted setup protocol. Anyone proficient in code should also feel free to follow along this code implementation. 8. What does a powers of tau setup look like? A powers of tau setup is made up of 2 series of elliptic curve points that look as follows. G1, G1s, G1s2, G1sn11. G2, G2s, G2s2, G2sn21. G1 and G2 are the standardized generator points of the 2 elliptic curve groups. In BLS 12-381, G1 points are, in compressed form, 48 bytes long and G2 points are 96 bytes long. N1 and N2 are the lengths of the G1 and G2 sides of the setup. Some protocols require N2 equals 2, others require N1 and N2 to both be large, and some are in the middle. Ethereum's data availability sampling in its current form requires N1 equals 4096 and N2 equals 16. S is the secret that is used to generate the points, and needs to be forgotten. To make a KZG commitment to a polynomial p, x, equals sigma I 6c, we simply take a linear combination sigma ICI SI, where SI equals G1 SI, the elliptic curve points in the trusted setup. The G2 points in the setup are used to verify evaluations of polynomials that we make commitments to. I won't go into verification here in more detail, though Dang Krad does in his post. Intuitively, what value is the trusted setup providing? It's worth understanding what is philosophically going on here, and why the trusted setup is providing value. A polynomial commitment is committing to a piece of size n data with a size O1 object, a single elliptic curve point. We could do this with a plain Peterson commitment. Just set the SI values to be n random elliptic curve points that have no known relationship with each other, and commit to polynomials with sigma ICI SI as before. And in fact, this is exactly what IPA evaluation proofs do. However, any IPA-based proofs take O(n) time to verify, and there's an unavoidable reason why. A commitment to a polynomial p, x, using the base points s0, s1, si, sn1 would commit to a different polynomial if we use the base points s0, s1, si2, sn1. A valid commitment to the polynomial 3x3 plus 8x2 plus 2x plus 6 under one set of base points is a valid commitment to 3x3 plus 4x2 plus 2x plus 6 under a different set of base points. If we want to make an IPA-based proof for some statement, say, that this polynomial evaluated at x equals 10 equals 3826, the proof should pass with the first set of base points and fail with the second. Hence, whatever the proof verification procedure is cannot avoid somehow taking into account each and every one of the SI values, and so it unavoidably takes O(n) time. But with the trusted setup, there is a hidden mathematical relationship between the points. It's guaranteed that SI plus 1 equals SSI with the same factor S between any 2 adjacent points. If S0, S1, SI, SN1 is a valid setup, the edited setup S0, S1, SI2, SN1 cannot also be a valid setup. Hence, we don't need O(n) computation. Instead, we take advantage of this mathematical relationship to verify anything we need to verify in constant time. However, the mathematical relationship has to remain secret. If S is known, then anyone could come up with a commitment that stands for many different polynomials. If C commits to P, X, it also commits to P, X, XS, or P, X, X plus S, or many other things. This would completely break all applications of polynomial commitments. Hence, while some secret S must have existed at one point to make possible the mathematical link between the SI values that enables efficient verification, the S must also have been forgotten. How do multi-participant setups work? It's easy to see how one participant can generate a setup. Just pick a random S and generate the elliptic curve points using that S. But a single participant trusted setup is insecure. You have to trust one specific person. The solution to this is multi-participant trusted setups, where by multi we mean a lot of participants. Over 100 is normal, and for smaller setups it's possible to get over 1000. Here is how a multi-participant powers of tau setup works. Take an existing setup. Note that you don't know S, you just know the points. G1, G1S, G1S2, G1SN11. G2, G2S, G2S2, G2SN21. Compute. G1, G1S, T, G1S2, T2, G1SN11, TN21. Notice that this is equivalent to G1, G1, ST, G1, ST, 2, G1, G2, G. That is to say, you've created a valid setup with the secret ST. You never give your T to the previous participants, and the previous participants never give you their secrets that went into S. And as long as any one of the participants is honest and does not reveal their part of the secret, the combined secret does not get revealed. In particular, finite fields have the property that if you know no S but not T, and T is securely randomly generated, then you know nothing about S. Verifying the setup. To verify that each participant actually participated, each participant can provide a proof that consists of I, the G1S point that they received, and 2, G2T, where T is the secret that they introduced. The list of these proofs can be used to verify that the final setup combines together all the secrets, as opposed to, say, the last participant just forgetting the previous values and outputting a setup with just their own secret, which they keep so they can cheat in any protocols that use the setup. S1 is the first participant's secret, S2 is the second participant's secret, etc. The pairing check at each step proves that the setup at each step actually came from a combination of the setup at the previous step and a new secret known by the participant at that step. Each participant should reveal their proof on some publicly verifiable medium, e.g. personal website, transaction from their .eth address, Twitter. Note that this mechanism does not prevent someone from claiming to have participated at some index where someone else has, assuming that other person has revealed their proof, but it's generally considered that this does not matter. If someone is willing to lie about having participated, they would also be willing to lie about having deleted their secret. As long as at least one of the people who publicly claim to have participated is honest, the setup is secure. In addition to the above check, we also want to verify that all the powers in the setup are correctly constructed, they're powers of the same secret. To do this, we could do a series of pairing checks, verifying that SI plus 1 G2 equals SI T1, where T1 is the G2S value in the setup, for every I. This verifies that the factor between each SI and SI plus 1 is the same as the factor between T1 and G2. We can then do the same on the G2 side. But that's a lot of pairings and is expensive. Instead, we take a random linear combination L1 equals sigma I equals 0 and 1 2 or ISI, and the same linear combination shifted by 1, L2 equals sigma I equals 0 and 1 2 or ISI plus 1. We use a single pairing check to verify that they match up, L2 G2 equals L1 T1. We can even combine the process for the G1 side and the G2 side together. In addition to computing L1 and L2 as above, we also compute L3 equals sigma I equals 0 and 2 2 GTI. G is another set of random coefficients, and L4 equals sigma I equals 0 and 2 2 GTI plus 1, and check L2 L3 equals L1 L4. Setups in Lagrange form. In many use cases, you don't want to work with polynomials in coefficient form, e.g. P x equals 3x3 plus 8x2 plus 2x plus 6. You want to work with polynomials in evaluation form, e.g. P x is the polynomial that evaluates to 19,146, 9,187 on the domain 1,189,336,148 modulo 337. Evaluation form has many advantages, e.g. you can multiply and sometimes divide polynomials in O, n, time, and you can even use it to evaluate in O, n, time. In particular, data availability sampling expects the blobs to be in evaluation form. To work with these cases, it's often convenient to convert the trusted setup to evaluation form. This would allow you to take the evaluations, 19,146, 9,187 in the above example, and use them to compute the commitment directly. This is done most easily with the fast Fourier transform, FFT, but passing the curve points as input instead of number. I'll avoid repeating a full detailed explanation of FFTs here, but here is an implementation. It is actually not that difficult. The future of trusted setup. Powers of tau is not the only kind of trusted setup out there. Some other notable, actual or potential, trusted setups include the more complicated setups in older ZK-SNARK protocols, see here, which are sometimes still used, particularly Groth16, because verification is cheaper than Plunk. Some cryptographic protocols, e.g. dark, depend on hidden order groups where it is not known what number an element can be multiplied by to get the zero element. Fully trustless versions of this exist. See, class groups, but by far the most efficient version uses RSA groups. Powers of X mod n equals PQ where P and Q are not known. Trusted setup ceremonies for this with one of n trust assumptions are possible, but are very complicated to implement. If /when indistinguishability obfuscation becomes viable, many protocols that depend on it will involve someone creating and publishing an obfuscated program that does something with a hidden internal secret. This is a trusted setup. The creator, S, would need to possess the secret to create the program, and would need to delete it afterwards. Cryptography continues to be a rapidly evolving field, and how important trusted setups are could easily change. It's possible that techniques for working with IPAs and Halo-style ideas will improve to the point where KZG becomes outdated and unnecessary, or that quantum computers will make anything based on elliptic curves non-viable 10 years from now and we'll be stuck working with trusted setup free hash-based protocol. It's also possible that what we can do with KZG will improve even faster, or that a new area of cryptography will emerge that depends on a different kind of trusted setup. To the extent that trusted setup ceremonies are necessary, it is important to remember that not all trusted setups are created equal. 176 participants is better than 6, and 2000 would be even. A ceremony small enough that it can be run inside a browser or phone application, e.g. the Zcopra setup is web-based, could attract far more participants than one that requires running a complicated software packet. Every ceremony should ideally have participants running multiple independently built software implementations and running different operating systems and environments, to reduce common mode failure risk. Ceremonies that require only one round of interaction per participant, like Powers of Tau, are far better than multi-round ceremonies, both due to the ability to support far more participants and due to the greater ease of writing multiple. Ceremonies should ideally be universal, the output of one ceremony being able to support a wide range of protocols. These are all things that we can and should keep working on, to ensure that trusted setups can be as secure and as trusted as possible.
I think a good idea is gonna be doing the same thing that I did in one of the graph algorithms that used some stuff from linear algebra. I forgot the name of the thing. I know it was linear combination and then linear independence, but the other one, matroids. So, and it was the two-tip polynomial, I think. Then I didn't know how those things worked, and I made an article for each. I think here is gonna be a good strategy to do the same thing. So I think what I'm gonna do is read this two here now, read this two, then read the yellow paper now on stream, then read the rest of the stuff off stream, and then I'm gonna finish this article here and write this one. I think I'm gonna do just a basic version of this. And then for each thing that I mentioned here, I'm going to open up branches, and then I'm gonna do one article for each of these things. And I think that's gonna be an efficient way to study all of this stuff, because then I can make articles at the same time that I understand or learn how these things work, which is gonna allow me to look at the code for each one. I'm trying to think about different possible ways to collect MEV, but it's hard because there's so much information. Like, I'm overloaded with a bunch of stuff. So I think that's why it's a better strategy to do one article for each, I think. And then I'm gonna clarify more everything after building like each part. And then only after that I focus more on the other stuff, like the other consensus protocols. Because the other ones are gonna be hard. It's probably not worth it to do like a description. Like, I don't want to do something that is like the other articles that I'm reading now. I wanna concentrate on extracting the first principles and then making the article based on the first principles instead of explaining how it works. So more of the overall picture of what's happening, let's say. Like, build the articles from that point of view. Like, explain the difference, like the fundamentals, where blockchain is going to be a network, and then this network has a consensus, and then it also has a flow of information of transactions that make that are the whole point of the network. And then because of the latency and the differences in flow of information, that you generate MEV. And because of that, and because of the order of transactions, and then you have these data structures that are based on hash and cryptography that allows you to reach this synchronization process. So I want to build the articles based on that line of thinking. But it would also be nice to incorporate the algorithms, I think. It's probably, what I have to organize more is the topics, I think. So it's probably going to be worth it to build a spreadsheet like this and then go over each topic so I can clarify more what stuff to write about first, because there's so many things. I think ideally first I would write articles about this stuff, which is very complicated. So maybe, yeah, Lagrange interpolation, I think, would be a good one to write an article about. Then this linear combination and this pairing thing. So I'm gonna grab something to read now, and I'm gonna read this one, and then I'm gonna read the yellow paper after, and then I think I'm gonna stop and do the rest off stream, read the rest of the documents off stream, or I might leave to read them tomorrow as well, depending on what I decide to do later. I'll be right back.
Dark mode toggle. Fast Fourier transforms. 2019 May 12th. See all posts. Trigger warning, specialized mathematical topic. Special thanks to Karl Floerst for feedback. One of the more interesting algorithms in number theory is the fast Fourier transform, FFT. FFTs are a key building block in many algorithms, including extremely fast multiplication of large numbers, multiplication of polynomials, and extremely fast generation and recovery of erasure code. Erasure codes in particular are highly versatile. In addition to their basic use cases in fault-tolerant data storage and recovery, erasure codes also have more advanced use cases such as securing data availability in scalable blockchains and Stark. This article will go into what fast Fourier transforms are, and how some of the simpler algorithms for computing them work. Background. The original Fourier transform is a mathematical operation that is often described as converting data between the frequency domain and the time domain. What this means more precisely is that if you have a piece of data, then running the algorithm would come up with a collection of sine waves with different frequencies and amplitudes that, if you added them together, would approximate the original data. Fourier transforms can be used for such wonderful things as expressing square orbits through epic eclipse and deriving a set of equations that can draw an elephant. Okay, fine. Fourier transforms also have really important applications in signal processing, quantum mechanics, and other areas, and help make significant parts of the global economy. But come on, elephants are cooler. Running the Fourier transform algorithm in the inverse direction would simply take the sine waves and add them together and compute the resulting values at as many points as you wanted to sample. The kind of Fourier transform we'll be talking about in this post is a similar algorithm, except instead of being a continuous Fourier transform over real or complex numbers, it's a discrete Fourier transform over finite fields. See the A Modular Math Interlude section here for a refresher on what. Instead of talking about converting between frequency domain and time domain, here we'll talk about two different operations: multi-point polynomial evaluation, evaluating a degree. Degree. The kind of Fourier transform we'll be talking about in this post is a similar algorithm, except instead of being a continuous Fourier transform over real or complex numbers, it's a discrete Fourier transform over finite fields. See the A Modular Math Interlude section here for a refresher on what finite fields are. Instead of talking about converting between frequency domain and time domain, here we'll talk about two different operations: multi-point polynomial evaluation, evaluating a degree. For example, if we are operating in the prime field with modulus 5, then the polynomial superscript 2y equals x superscript 2 plus 3. For convenience, we can write the coefficients in increasing order: 3, 0, 1. Evaluated at the points 0, 1, 2 gives the values 3, 4, 2, not 3, 4, 7 because we're operating in a finite field where the numbers wrap around at 5, and we can actually take the evaluations 3, 4, 2 and the coordinates they were evaluated at 0, 1, 2 to recover the original polynomial 3, 0, 1. There are algorithms for both multi-point evaluation and interpolation that can do either operation in O and 2 time. Multi-point evaluation is simple: just separately evaluate the polynomial at each point. Here's Python code for doing that. Def eval underscore poly underscore at self poly x modulus y equals 0. Power underscore of underscore x equals 1. For coefficient in poly, y plus equals power underscore of underscore x asterisk coefficient. Power underscore of underscore x asterisk equals x. Return y percent modulus. The algorithm runs a loop going through every coefficient and does one thing for each coefficient, so it runs in O, n, time. Multi-point evaluation involves doing this evaluation at n different points, so the total runtime is O, n2. Lagrange interpolation is more complicated. Search for Lagrange interpolation here for a more detailed explanation. The key building block of the basic strategy is that for any domain d in point x, we can construct a polynomial that returns 1 for x and 0 for any value in d other than x. For example, if d equals 1, 2, 3, 4 and x equals 1, the polynomial is y equals x2, x3, x4, 1, 2, 1, 3, 1, 4. You can mentally plug in 1, 2, 3, and 4 to the above expression and verify that it returns 1 for x equals 1 and 0 in the other three cases. We can recover the polynomial that gives any desired set of outputs on the given domain by multiplying and adding these polynomials. If we call the above polynomial p1, and the equivalent ones for x equals 2, x equals 3, x equals 4, p2, p3, and p4, then the polynomial that returns 3, 1, 4, 1 on the domain 1, 2, 3, 4 is simply 3p1 plus p2 plus 4p3 plus p4. Computing the pi polynomials takes O, n2, time. You first construct the polynomial that returns to 0 on the entire domain, which takes O, n2, time, then separately divided by x11 for each 11, and computing the linear combination takes another O, n2, time, so it's O, n2, runtime to. What fast Fourier transforms let us do is make both multi-point evaluation and interpolation much faster. Fast Fourier transforms. There is a price you have to pay for using this much faster algorithm, which is that you cannot choose any arbitrary field in any arbitrary domain. Whereas with Lagrange interpolation, you could choose whatever x coordinates and y coordinates you wanted, and whatever field you wanted. You could even do it over plain old real numbers, and you could get a polynomial that passes through them. With an FFT, you have to use a finite field, and the domain must be a multiplicative subgroup of the field, that is, a list of powers of some generator value. For example, you could use the finite field of integers modulo 337, and for the domain use 1, 85, 148, 111, 336, 252, 189, 226. That's the powers of 85 in the field e.g. 853% 337 equals 111. It stops at 226 because the next power of 85 cycles back to 1. Furthermore, the multiplicative subgroup must have size 2n. There's ways to make it work for numbers of the form 2m, 3n, and possibly slightly higher prime powers, but then it gets much more complicated and inefficient. The finite field of int irigers modulo 59, for example, would not work, because there are only multiplicative subgroups of order 2, 29, and 58. 2 is too small to be interesting, and the factor 29 is far too large to be FFT friendly. The symmetry that comes from multiplicative groups of size 2n lets us create a recursive algorithm that quite cleverly calculate the results we need from a much smaller amount of work. To understand the algorithm and why it has a low runtime, it's important to understand the general concept of recursion. A recursive algorithm is an algorithm that has two cases: a base case where the input to the algorithm is small enough that you can give the output directly, and the recursive case where the required computation consists of some glue computation plus one or more uses of the same algorithm to smaller input. For example, you might have seen recursive algorithms being used for sorting lists. If you have a list, e.g. 1, 8, 7, 4, 5, 6, 3, 2, 9, then you can sort it using the following procedure. If the input has one element, then it's already sorted, so you can just return the input. If the input has more than one element, then separately sort the first half of the list and the second half of the list, and then merge the two sorted sublists. Call them A and B, as follows. Maintain two counters, oppos and pis, both starting at 0, and maintain an output list, which starts empty. Until either oppos or pis is at the end of the corresponding list, check if A oppos or B pis is small. Whichever is smaller, add that value to the end of the output list, and increase the counter by 1. Once this is done, add the rest of whatever list has not been fully processed to the end of the output list, and return the output list. Note that the glue in the second procedure has runtime O, and if each of the two sublists has n elements, then you need to run through every item in each list once, so it's O, n, computation to. So the algorithm as a whole works by taking a problem of size n, and breaking it up into two problems of size n2, plus O, n, of glue execution. There is a theorem called the master theorem that lets us compute the total runtime of algorithms like this. It has many subcases, but in the case where you break up an execution of size n into k subcases of size nk with O, n, glue, as is the case here, the result is that the execution takes time O, n log, n. An FFT works in the same way. We take a problem of size n, break it up into two problems of size n2, and do O, n, glue work to combine the smaller solutions into a bigger solution, so we get O, n log, n, runtime total, much faster than O, n2. Here's how we do it. I'll describe first how to use an FFT for multi-point evaluation, i.e. for some domain D and polynomial p, calculate p, x, for every x in D, and it turns out that you can use the same algorithm for interpolation with a minor tweak. Suppose that we have an FFT where the given domain is the powers of x in some field, where x2k equals 1, e.g. in the case we introduced above, the domain is the powers of 85 modulo 337, and 8523 equals 1. We have some polynomial, e.g. y equals 6x7 plus 2x6 plus 9x5 plus 5x4 plus x3 plus 4x2 plus x plus 3. We'll write it as p equals 3, 1, 4, 1, 5, 9, 2, 6. We want to evaluate this polynomial at each point in the domain, i.e. at each of the 8 powers of 85. Here's what we do. First, we break up the polynomial into two parts, which we'll call evens and odds. Evens equals 3, 4, 5, 2 and odds equals 1, 1, 9, 6. Or evens equals 2x3 plus 5x2 plus 4x plus 3 and odds equals 6x3 plus 9x2 plus x plus 1. Yes, this is just taking the even degree coefficients and the odd degree coefficients. Now, we note a mathematical observation, p, x, equals evens, x2, plus x odds, x2, and p, x, equals evens, x2, x odds, x2. Think about this for yourself and make sure you understand it before going further. Here, we have a nice property, evens and odds are both polynomials half the size of p, and furthermore, the set of possible values of x2 is only half the size of the original domain, because there is a 2-to-1 correspondence, x and x are both part of D. In our current domain 1, 85, 148, 111, 336, 252, 189, 226, 1 and 336 are negatives of each other, as 336 equals 1%, 337, as are 85,252, 148,189, and 111,226. And x and x always both have the same square. Hence, we can use an FFT to compute the result of evens, x, for every x in the smaller domain consisting of squares of numbers in the original domain, 1,148,336,189, and we can do the same for odds. And voila, we've reduced a size n problem into half-size problems. The glue is relatively easy, and in runtime we receive the evaluations of evens and odds as size n2 lists, so we simply do p I equals evens underscore result I plus domain I odds underscore result I and pn2 plus I equals evens underscore result I domain I odds underscore result I for each index. Here's the full code. Def FFT, vals, modulus, domain. If len, vals, equals 1, return vals. L equals FFT, vals colon 2, modulus, domain colon 2. R equals FFT, vals 1, 2, modulus, domain colon 2. O equals 0 for I and vals. For I, x, y, and enumerate, zip, L, R. Y underscore times underscore root equals y asterisk domain I. OI equals x plus y underscore times underscore root, percent modulus. OI plus len, L, equals xy underscore times underscore root, percent modulus. Return. We can try running it. FFT, 3, 1, 4, 1, 5, 9, 2, 6, 337, 1, 85, 148, 100, and we can check the result. Evaluating the polynomial at the position 85, for example, actually does give the result 70. Note that this only works if the domain is correct. It needs to be of the form 11% modulus for I in range, n, where xn equals 1. An inverse FFT is surprisingly simple. Def inverse underscore FFT, vals, modulus, domain. Vals equals FFT, vals, modulus, domain. Return x asterisk modular underscore inverse, len, vals, modulus, percent modulus for x and vals 0 plus. Basically, run the FFT again, but reverse the result, except the first item stays in place, and divide every value by the length of the list. Domain equals 1, 85, 148, 111, 336, 252, 189, 226. Def mod. Now, what can we use this for? Here's one fun use case. We can use FFTs to multiply numbers very quickly. Suppose we wanted to multiply 1253 by 1895. Here's what we would do. First, we would convert the problem into one that turns out to be slightly easier. Multiply the polynomials 3, 5, 2, 1 by 5, 9, 8, 1. That's just the digits of the two numbers in increasing order, and then convert the answer back into a number by doing a single pass to carry over 10's digit. We can multiply polynomials with FFTs quickly, because it turns out that if you convert a polynomial into evaluation form, i.e. f, x, for every x in some domain D, then you can multiply two polynomials simply by multiplying their evaluation. So what we'll do is take the polynomials representing our two numbers in coefficient form, use FFTs to convert them to evaluation form, multiply them pointwise, and convert back. P1 equals 3, 5, 2, 1, 0, 0, 0. This requires 3 FFTs, each O, n log, n, time, and 1 pointwise multiplication, O, n, time, so it takes O, n log, n, time altogether, technically a little bit more than O, n log, n, because for very big numbers you would need replace 337 with a bigger modulus and that would make multiplication harder, but close enough. This is much faster than schoolbook multiplication, which takes O, n2, time, 3, 5, 2, 1, 5, 15, 25, 10, 5, 9, 27, 45, 18, 9, 8, 24, 40, 16, 8, 1, 3, 5, 2, 1, 15, 52, 79, 66, 30, 10, 1. So now we just take the result, and carry the 10's digits over. This is a walk through the list once and do one thing at each point algorithm, so it takes O, n, time. 15, 52, 79, 66, and if we read the digits from top to bottom, we get 237, 4435. Let's check the answer, 1253 asterisk 1. Yay, it worked. In practice, on such small inputs, the difference between O, n log, n, and O, n2, isn't that large, so schoolbook multiplication is faster than this FFT-based multiplication process just because the algorithm is simpler, but on large inputs it makes a really big difference. But FFTs are useful not just for multiplying numbers, as mentioned above. Polynomial multiplication and multi-point evaluation are crucially important operations in implementing erasure coding, which is a very important technique for building many kinds of redundant fault-tolerant system. If you like fault tolerance and you like efficiency, FFTs are your friend. FFTs and binary fields. Prime fields are not the only kind of finite field out there. Another kind of finite field, really a special case of the more general concept of an extension field, which are kind of like the finite field equivalent of complex numbers, are binary field. In a binary field, each element is expressed as a polynomial where all of the entries are 0 or 1, e.g. x3 plus x plus 1. Adding polynomials is done modulo 2, and subtraction is the same as addition, as 1 equals 1 mod 2. We select some irreducible polynomial as a modulus, e.g. x4 plus x plus 1. x4 plus 1 would not work because x4 plus 1 can be factored into x2 plus 1, x2 plus 1, so it's not irreducible. Multiplication is done modulo that modulate. For example, in the binary field mod x4 plus x plus 1, multiplying x2 plus 1 by x3 plus 1 would give x5 plus x3 plus x2 plus 1 if you just do the multiplication, but x5 plus x3 plus x2 plus 1 equals x4 plus x plus 1, x plus x3 plus x plus 1, so the result is the remainder x3 plus x plus 1. We can express this example as a multiplication table. First multiply 1, 0, 0, 1, i.e. x3 plus 1, by 1, 0, 1, i.e. x2 plus 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 1. The multiplication result contains an x5 term, so we can subtract x4 plus x plus 1, x. 110101, 11001, x plus 1, shifted right by 1 to reflect being multiplied by x. 110100. And we get the result, 1, 1, 0, 1, or x3 plus x plus 1. Addition and multiplication tables for the binary field mod x4 plus x plus 1. Field elements are expressed as integers converted from binary. x3 plus x2 rightward arrow 1100 rightward arrow. Binary fields are interesting for two reasons. First of all, if you want to erase your code binary data, then binary fields are really convenient because n bytes of data can be directly encoded as a binary field element, and any binary field elements that you generate by performing computations on it will also be n bytes long. You cannot do this with prime fields because prime field size is not exactly a power of 2. For example, you could encode every 2 bytes as a number from 0, 65536 in the prime field modulo 65537, which is prime, but if you do an FFT on these values, then the output could contain 65536, which cannot be expressed in 2 bytes. Second, the fact that addition and subtraction become the same operation, and 1 plus 1 equals 0, creates some structure which leads to some very interesting consequences. One particularly interesting and useful oddity of binary fields is the freshman's dream theorem, x plus y, 2 equals x2 plus y2, and the same for exponents 4, 8, 16. Basically any power of 2. But if you want to use binary fields for erasure coding, and do so efficiently, then you need to be able to do fast Fourier transforms over binary fields. But then there is a problem. In a binary field, there are no non-trivial multiplicative groups of order 2n. This is because the multiplicative groups are all order 2n1. For example, in the binary field with modulus x4 plus x plus 1, if you start calculating successive powers of x plus 1, you cycle back to 1 after 15 steps, not 16. The reason is that the total number of elements in the field is 16, but one of them is 0, and you're never going to reach 0 by multiplying any non-zero value by itself in a field. So the powers of x plus 1 cycle through every element but 0, so the cycle length is 15, not 16. So what do we do? The reason we needed the domain to have the structure of a multiplicative group with 2n elements before is that we needed to reduce the size of the domain by a factor of 2 by squaring each number in it. The domain 1, 85, 148, 111, 336, 252, 189, 226 gets reduced to 1,148,336,189 because 1 is the square of both 1 and 336, 148 is the square of both 85 and 252, and so forth. But what if in a binary field there's a different way to have the size of a domain? It turns out that there is. Given a domain containing 2k values, including 0, technically the domain must be a subspace. We can construct a half-sized new domain D by taking x plus k, for x and d using some specific k and d. Because the original domain is a subspace, since k is in the domain, any x in the domain has a corresponding x plus k also in the domain, and the function f, x, equals x plus k, returns the same value for x and x plus k, so we get the same kind of 2-to-1 correspondence that squaring gives us x. So now, how do we do an FFT on top of this? We'll use the same trick, converting a problem with an n-sized polynomial and n-sized domain into two problems each with an n2-sized polynomial and n2-sized domain, but this time using different equation. We'll convert a polynomial p into two polynomials evens and odds such that p, x, equals evens, x, kx, plus x. Note that for the evens and odds that we find, it will also be true that p, x plus k, equals evens, x, kx, so we can then recursively do an FFT to evens and odds on the reduced domain x, kx, for x and d, and then we use these two formulas to get the answers for two halves of the domain, one offset by k from the other. Converting p into evens and odds as described above turns out to itself be non-trivial. The naive algorithm for doing this is itself O, n2, but it turns out that in a binary field, we can use the fact that x2kx, 2 equals x4k2x2, and more generally, x2kx, 2i equals x2i plus 1k2i x2i, to create yet another recursive algorithm to do this in O, n log, n, and if you want to do an inverse FFT, to do interpolation, then you need to run the steps in the algorithm in reverse order. You can find the complete code for doing this here, https://github.com/e3um/research/tree/binary_fft, and a paper with details on more optimal algorithms here, http://www.math.clemson.edu/tilde/sgao/papers/gm10.pd. So what do we get from all of this complexity? Well, we can try running the implementation, which features both a naive O, n2, multi-point evaluation and the optimized FFT-based one, and time both. Here are my results. Import binary_FFT, and as the size of the polynomial gets larger, the naive implementation, _simple_FT, gets slower much more quickly than the FFT. F equals b, and voila, we have an efficient, scalable way to multi-point evaluate and interpolate polynomials. If we want to use FFTs to recover erasure-coded data where we are missing some pieces, then algorithms for this also exist, though they are somewhat less efficient than just doing a single FFT. Dark mode toggle. Mirror exploring elliptic curve pairings. 2017 January 14th. See all posts. This is a mirror of the post at H. Trigger warning, math. One of the key cryptographic primitives behind various constructions, including deterministic threshold signatures, ZK snarks and other simpler forms of zero-knowledge proofs is the elliptic curve pair. Elliptic curve pairings, or bilinear maps, are a recent addition to a 30-year-long history of using elliptic curves for cryptographic applications including encryption and digital signatures. Pairings introduce a form of encrypted multiplication, greatly expanding what elliptic curve-based protocols can. The purpose of this article will be to go into elliptic curve pairings in detail, and explain a general outline of how they work. You are not expected to understand everything here the first time you read it, or even the 10th time. This stuff is genuinely hard, but hopefully this article will give you at least a bit of an idea as to what is going on under the hood. Elliptic curves themselves are very much a non-trivial topic to understand, and this article will generally assume that you know how they work. If you do not, I recommend this article here as a primer. As a quick summary, elliptic curve cryptography involves mathematical objects called points. These are literal two-dimensional points with x, y coordinates, with special formulas for adding and subtracting them, for calculating the coordinates of r equals p plus q, and you can also multiply a point by an integer, i.e. pn equals p plus p. Here's how point addition looks like graphically. There exists a special point called the point at infinity, O, the equivalent of 0 in point arithmetic. It's always the case that p plus O equals. Also, a curve has an order. There exists a number n such that pn equals O for any p, and of course, p n plus 1. There exists a special point called the point at infinity, O, the equivalent of 0 in point arithmetic. It's always the case that p plus O equals p. Also, a curve has an order. There exists a number n such that pn equals O for any p, and of course, p n plus 1 equals pp, 7n plus 5 equals p5, and so on. There is also some commonly agreed upon generator point, g, which is understood to in some sense represent the number 1. Theoretically, any point on a curve, except O, can be g. All that matters is that g is standardized. Pairings go a step further in that they allow you to check certain kinds of more complicated equations on elliptic curve points. For example, if p equals g, pq equals gq, and r equals gr, you can check whether or not pq equals r, having just pq and r as input. This might seem like the fundamental security guarantees of elliptic curves are being broken, as information about p is leaking from just knowing p, but it turns out that the leakage is highly contained specifically. The decisional Diffie-Hellman problem is easy, but the computational Diffie-Hellman problem, knowing p and q in the above example, computing r equals gpq, and the discrete logarithm problem, recovering p from p, remain computationally infeasible, at least, if they were before. A third way to look at what pairings do, and one that is perhaps most illuminating for most of the use cases that we are about, is that if you view elliptic curve points as one-way encrypted numbers, that is, encrypt p equals pg equals p, then whereas traditional elliptic curve math lets you check linear constraints on the numbers, e.g., if p equals g, pq equals gq, and r equals gr, checking 5p plus 7q equals 1 1r is really checking that 5p plus 7q equals 1 1r. Pairings let you check quadratic constraints, e.g., checking e, pq, e, gg5 equals 1 is really checking that pq plus 5 equals 0. And going up to quadratic is enough to let us work with deterministic threshold signatures, quadratic arithmetic programs, and all that other good stuff. Now, what is this funny e, pq operator that we introduced above? This is the pairing. Mathematicians also sometimes call it a bilinear map. The word bilinear here basically means that it satisfies the constraints. E, pq plus r equals e, e, p plus sq, e. Note that plus and can be arbitrary operators. When you are creating fancy new kinds of mathematical objects, abstract algebra doesn't care how plus and are defined, as long as they are consistent in the usual ways. E, a plus b equals b plus a, ab, c equals a, bc, and ac plus bc equals a plus b, c. If p, q, r, and s were simple numbers, then making a simple pairing is easy. We can do e, xy equals 2xy. Then, we can see e 3, 4 plus 5 equals 239 equals 227, e 3, 4, e 3, 5, e. It's bilinear. However, such simple pairings are not suitable for cryptography because the objects that they work on are simple integers and are too easy to analyze. Integers make it easy to divide, compute logarithms, and make various other computations. Simple integers have no concept of a public key or a one-way function. Additionally, with the pairing described above you can go backwards. Knowing x, and knowing e, xy, you can simply compute a division in a logarithm to determine. We want mathematical objects that are as close as possible to black boxes, where you can add, subtract, multiply, and divide, but do nothing else. This is where elliptic curves and elliptic curve pairings come in. It turns out that it is possible to make a bilinear map over elliptic curve points, that is, come up with a function e, pq, where the inputs p and q are elliptic curve points, and where the output is what's called an fp, 12 element, at least in the specific case we will cover here. The specifics differ depending on the details of the curve. More on this later, but the math behind doing so is quite complex. First, let's cover prime fields and extension fields. The pretty elliptic curve in the picture earlier in this post only looks that way if you assume that the curve equation is defined using regular real numbers. However, if we actually use regular real numbers in cryptography, then you can use logarithms to go backwards, and everything breaks. Additionally, the amount of space needed to actually store and represent the numbers may grow arbitrarily. Hence, we instead use numbers in a prime field. A prime field consists of the set of numbers 0, 1, 2, p1, where p is prime, and the various operations are defined as follows. A plus b, percent p a b a b, percent p a b a b, percent p a slash b a b p2, percent p. Basically, all math is done modulo p. See here for an introduction to modular math. Division is a special case. Normally, 32 is not an integer, and here we want to deal only with integers, so we instead try to find the number x such that x2 equals 3, where of course refers to modular multiplication as defined above. Thanks to Fermat's little theorem, the exponentiation trick shown above does the job, but there is also a faster way to do it, using the extended Euclidean algorithm. Suppose p equals 7. Here are a few examples. 2 plus 3 equals 5%, 7 equals 5. 4 plus 6 equals 10%, 7 equals 3. 2 5 equals 3%, 7 equals 4. 6 3 equals 18%, 7 equals 4. 3 slash 2 equals 3 2 5%, 7 equals 5. 5 2 equals 10%, 7 equals 3. If you play around with this kind of math, you'll notice that it's perfectly consistent and satisfies all of the usual rules. The last two examples above show how a slash b, b equals a. You can also see that a plus b c equals a plus b plus c, comma, a plus b c equals ac plus bc. And in elliptic curves in reality, the points and equations are usually computed in prime fields. Now, let's talk about extension fields. You have probably already seen an extension field before. The most common example that you encounter in math textbooks is the field of complex numbers, where the field of real numbers is extended with the additional element 1 equals. Basically, extension fields work by taking an existing field, then inventing a new element and defining the relationship between that element and existing elements. In this case, I2 plus 1 equals 0, making sure that this equation does not hold true for any number that is in the original field, and looking at the set of all linear combinations of elements of the original field and the new element that you have just created. We can do extensions of prime fields too. For example, we can extend the prime field mod 7 that we described above with I, and then we can do 2 plus 3i, plus 4 plus 2i, equals 6 plus 5, 5 plus 2i, plus 3 equals 1 plus 2i, 6 plus 2i, 2 equals 5 plus 4i, 4i, 2 plus I, equals 3 plus I. That last result may be a bit hard to figure out. What happened there was that we first decomposed the product into 4i2 plus 4i, which gives 8i4, and then because we are working in mod 7 math that becomes I plus 3, to divide, we do a slash bab, p22, percent p. Note that the exponent for Fermat's little theorem is now p2 instead of p, though once again if we want to be more efficient we can also instead extend the extended Euclidean algorithm to do the job. Note that xp21 equals 1 for any x in this field, so we call p21 the order of the multiplicative group in the field. With real numbers, the fundamental theorem of algebra ensures that the quadratic extension that we call the complex numbers is complete. You cannot extend it further, because for any mathematical relationship, at least, any mathematical relationship defined by an algebraic formula that you can come up with between some new element j and the existing complex numbers, it's possible to come up with at least one complex number that already satisfies that relationship. With prime fields, however, we do not have this issue, and so we can go further and make cubic extensions, where the mathematical relationship between some new element w and existing field elements is a cubic equation, so 1w and w2 are all linearly independent of each other, higher order extensions, extensions of extensions, etc. And it is these kinds of supercharged modular complex numbers that elliptic curve pairings are built on. For those interested in seeing the exact math involved in making all of these operations written out in code, prime fields and field extensions are implemented here. Now, onto elliptic curve pairings. An elliptic curve pairing, or rather, the specific form of pairing we'll explore here, there are also other types of pairings, though their logic is fairly similar, is a map g2 times g1 rightward arrow gt, where G1 is an elliptic curve, where points satisfy an equation of the form y2 equals x3 plus b, and where both coordinates are elements of fp, i.e. they are simple numbers, except arithmetic is all done modulo some prime number. G2 is an elliptic curve, where points satisfy the same equation as G1, except where the coordinates are elements of fp, 12, i.e. they are the supercharged complex numbers we talked about above. We define a new magic number, w, which is defined by a 12th degree polynomial like w12 18w6 plus 82 equals 0. GT is the type of object that the result of the elliptic curve goes into. In the curves that we look at, GT is fp, 12, the same supercharged complex number as used in G2. The main property that it must satisfy is bilinearity, which in this context means that pq plus r equals pq, p plus qr equal. There are two other important criteria. Efficient computability, e.g. we can make an easy pairing by simply taking the discrete logarithms of all points and multiplying them together, but this is as computationally hard as breaking elliptic curve cryptography in the first place, so it doesn't count. Non-degeneracy, sure, you could just define pq equals 1, but that's not a particularly useful pairing. So how do we do this? The math behind why pairing functions work is quite tricky and involves quite a bit of advanced algebra going even beyond what we've seen so far, but I'll provide an outline. First of all, we need to define the concept of a divisor, basically an alternative way of representing functions on elliptic curve points. A divisor of a function basically counts the zeros and the infinities of the function. To see what this means, let's go through a few examples. Let us fix some point p equals px pi and consider the following function. F, xy, equals xpx. The divisor is p plus p2o. The square brackets are used to represent the fact that we are referring to the presence of the point p in the set of zeros and infinities of the function, not the point p itself. P plus q is not the same thing as p plus q. The reasoning is as follows. The function is equal to 0 at p, since x is px, so xpx equals 0. The function is equal to 0 at p, since p and p share the same x coordinate. The function goes to infinity as x goes to infinity, so we say the function is equal to infinity at o. There's a technical reason why this infinity needs to be counted twice, so o gets added with a multiplicity of 2, negative because it's an infinity and not a 0, 2 because of this double counting. The technical reason is roughly this, because the equation of the curve is x3 equals y2 plus by goes to infinity 1.5 times faster than x does in order for y2 to keep up with x3. Hence, if a linear function includes only x then it is represented as an infinity of multiplicity 2, but if it includes y then it is represented as an infinity of multiplicity 3. Now, consider a line function colon. X plus by plus c equals 0, where a, b and c are carefully chosen so that the line passes through points p and q. Because of how elliptic curve addition works, see the diagram at the top. This also means that it passes through pq, and it goes up to infinity dependent on both x and y, so the divisor becomes p plus pq3o. We know that every rational function, i.e. a function defined only using a finite number of plus, and slash operations on the coordinates of the point, uniquely corresponds to some divisor, up to multiplication by a constant. If two functions f and g have the same divisor, then f equals gk for some constant k. For any two functions f and g, the divisor of fg is equal to the divisor of f plus the divisor of g. In math textbooks, you'll see fg equals f plus g. So for example, if f, xy, equals pxx, then f3 equals 3p plus 3p60. P and p are triple counted to account for the fact that f3 approaches 0 at those points 3 times as quickly in a certain mathematical sense. Note that there is a theorem that states that if you remove the square brackets from a divisor of a function, the points must add up to o. P plus pq3o clearly fits, as p plus pq3o equals o, and any divisor that has this property is the divisor of a function. Now, we're ready to look at Tate pairings. Consider the following functions, defined via their divisors. Fp equals np and o, where n is the order of g1. Np equals o for any p. Fq equals nq and o. G equals p plus q pq plus o. Now, let's look at the product fp fqgn. The divisor is np and o plus nq and o plus np plus q np and q plus no, which simplifies neatly to np plus q no. Notice that this divisor is of exactly the same format as the divisor for fp and fq above. Hence, fp fqgn equals fp plus q. Now, we introduce a procedure called the final exponentiation step, where we take the result of our functions above, fp fq, etc., and raise it to the power z equals p12(1)/n, where p12(1) is the order of the multiplicative group in fp12. For any x set membership symbol, fp12x p12(1) equals 1. Notice that if you apply this exponentiation to any result that has already been raised to the power of n, you get an exponentiation to the power of p12(1), so the result turns into 1. Hence, after final exponentiation, gn cancels out and we get fpz fqz equals fp plus q, z. There's some bilinearity for you. Now, if you want to make a function that's bilinear in both arguments, you need to go into spookier math, where instead of taking fp of a value directly, you take fp of a divisor, and that's where the full Tate pairing comes from. To prove some more results you have to deal with notions like linear equivalence and while reciprocity, and the rabbit hole goes on from there. You can find more reading material on all of this here and here. For an implementation of a modified version of the Tate pairing, called the optimal Tate pairing, see here. The code implements Miller's algorithm, which is needed to actually compute f. Note that the fact pairings like this are possible is somewhat of a mixed blessing. On the one hand, it means that all the protocols we can do with pairings become possible, but it also means that we have to be more careful about what elliptic curves we use. Every elliptic curve has a value called an embedding degree, essentially, the smallest k such that pk1 is a multiple of n, where p is the prime used for the field and n is the curve order. In the fields above, k equals 12, and in the fields used for traditional ECC, i.e. where we don't care about pairings, the embedding degree is often extremely large, to the point that pairings are computationally infeasible to compute. However, if we are not careful then we can generate fields where k equals 4 or even 1. If k equals 1, then the discrete logarithm problem for elliptic curves, essentially, recovering p knowing only the point p equals gp, the problem that you have to solve to crack an elliptic curve private key, can be reduced into a similar math problem over fp, where the problem becomes much easier. This is called the MOV attack. Using curves with an embedding degree of 12 or higher ensures that this reduction is either unavailable, or that solving the discrete log problem over pairing results is at least as hard as recovering a private key from a public key, the normal way. Computationally infeasible. Do not worry, all standard curve parameters have been thoroughly checked for this issue. Stay tuned for a mathematical explanation of how zk snarks work, coming soon. Special thanks to Christian Reed Wiesner, Ariel Gabizin, from Zcash, and Alfred Menezes for reviewing and making corrections. Ethereum, a secure decentralized generalist transaction ledger. Berlin version 8 via 825, August 22, 2022. Introduction. With ubiquitous internet connections in most places of the world, global information transmission has become incredibly cheap. Technology-rooted movements like Bitcoin have demonstrated through the power of the default, consensus mechanisms, and voluntary respect of the social contract, that it is possible to use the internet to make a decentralized value transfer system that can be shared across the world and virtually free to use. This system can be said to be a very specialized version of a cryptographically secure, transaction-based state machine. Follow-up systems such as Namecoin adapted this original, currency application of the technology into other applications, albeit rather simplistic ones. Ethereum is a project which attempts to build the generalist technology on which all transaction-based state machine concepts may be built. Moreover, it aims to provide to the end developer a tightly integrated end-to-end system for building software on a hitherto unexplored compute paradigm in the mainstream, a trustful object messaging compute framework. 1.1 Driving factors. There are many goals of this project. One key goal is to facilitate transactions between consenting individuals who would otherwise have no means to trust one another. This may be due to geographical separation, interfacing difficulty, or perhaps the incompatibility, incompetence, unwillingness, expense, uncertainty, inconvenience, or corruption of existing legal systems. By specifying a state change system through a rich and unambiguous language, and furthermore architecting a system such that we can reasonably expect that an agreement will be thus enforced autonomously, we can provide a means to this end. Dealings in this proposed system would have several attributes not often found in the real world. The incorruptibility of judgment, often difficult to find, comes naturally from a disinterested algorithmic interpreter. Transparency, or being able to see exactly how a state or judgment came about through the transaction login rules or instructional codes, never happens perfectly in human-based systems since natural language is necessarily vague. Information is often lacking, and plain old prejudices are difficult to shake. Overall, we wish to provide a system such that users can be guaranteed that no matter with which other individuals, systems, or organizations they interact, they can do so with absolute confidence in the possible outcomes and how those outcomes might come about. 1.2 Previous work. Buter in 2013 first proposed the kernel of this work in late November 2013. Though now evolved in many ways, the key functionality of a blockchain with a Turing-complete language and an effectively unlimited inter-transaction storage capability remains unchanged. Work in Nair 1992 provided the first work into the usage of a cryptographic proof of computational expenditure, proof of work, as a means of transmitting a value signal over the internet. The value signal was utilized here as a spam deterrence mechanism rather than any kind of currency, but critically demonstrated the potential for a basic data channel to carry a strong economic signal, allowing a receiver to make a physical assertion without having to rely upon trust. Back 2002 later produced a system in a similar vein. The first example of utilizing the proof of work as a strong economic signal to secure a currency was by Vishnumurthy et al. 2003 In this instance, the token was used to keep peer-to-peer file trading in check, providing consumers with the ability to make micropayments to suppliers for their services. The security model afforded by the proof of work was augmented with digital signatures in a ledger in order to ensure that the historical record couldn't be corrupted and that malicious actors could not spoof payment or unjustly complain about service delivery. 5 years later, Nakamoto 2008 introduced another such proof of work secured value token, somewhat wider in scope. The fruits of this project, Bitcoin, became the first widely adopted global decentralized transaction ledger. Other projects built on Bitcoin's success, the altcoins introduced numerous other currencies through alteration to the protocol. Some of the best known are Litecoin and Primecoin, discussed by Sprankle 2013. Other projects sought to take the core value content mechanism of the protocol and repurpose it. Aaron 2012 discusses, for example, Ethereum, a secure decentralized generalist transaction ledger Berlin version 2. The Namecoin project which aims to provide a decentralized name resolution system. Other projects still aim to build upon the Bitcoin network itself, leveraging the large amount of value placed in the system and the vast amount of computation that goes into the consensus mechanism. The Mastercoin project, first proposed by Willett 2013, aims to build a richer protocol involving many additional high-level features on top of the Bitcoin protocol through utilization of a number of auxiliary parts to the core protocol. The Colored Coins project, proposed by Rosenfeld et al. 2012, takes a similar but more simplified strategy, embellishing the rules of a transaction in order to break the fungibility of Bitcoin's base currency and allow the creation and tracking of tokens through a special Chroma Wallet protocol-aware piece of software. Additional work has been done in the area with discarding the decentralization foundation, Ripple, discussed by Boutelier and Hines in 2014, has sought to create a federated system for currency exchange, effectively creating a new financial clearing system. It has demonstrated that high efficiency gains can be made if the decentralization premise is discarded. Early work on smart contracts has been done by Szabo 1997 and Miller 1997. Around the 1990s it became clear that algorithmic enforcement of agreements could become a significant force in human cooperation. Though no specific system was proposed to implement such a system, it was proposed that the future of law would be heavily affected by such systems. In this light, Ethereum may be seen as a general implementation of such a crypto law system. For a list of terms used in this paper, refer to Appendix A. To the blockchain paradigm. Ethereum, taken as a whole, can be viewed as a transaction-based state machine. We begin with a genesis state and incrementally execute transactions to morph it into some current state. It is this current state which we accept as the canonical version of the world of Ethereum. The state can include such information as account balances, reputations, trust arrangements, data pertaining to information of the physical world. In short, anything that can currently be represented by a computer is admissible. Transactions thus represent a valid arc between two states. The valid part is important. There exist far more invalid state changes than valid state changes. Invalid state changes might, example, be things such as reducing an account balance without an equal and opposite increase elsewhere. A valid state transition is one which comes about through a transaction. Formally, 1, sigma t plus 1 upsilon, sigma t, t, where upsilon is the Ethereum state transition function. In Ethereum, upsilon, together with sigma are considerably more powerful than any existing comparable system. Upsilon allows components to carry out arbitrary computation, while sigma allows components to store arbitrary state between transactions. Transactions are collated into blocks. Blocks are chained together using a cryptographic hash as a means of reference. Blocks function as a journal, recording a series of transactions together with the previous block and an identifier for the final state, though do not store the final state itself. That would be far too big. They also punctuate the transaction series with incentives for nodes to mine. This incentivization takes place as a state transition function, adding value to a nominated account. Mining is the process of dedicating effort, working, to bolster one series of transactions, a block, over any other potential competitor block. It is achieved thanks to a cryptographically secure proof. This scheme is known as a proof of work and is discussed in detail in section 11.5. Formally, we expand to sigma t plus 1 pi, sigma t, b, 2. b, t0, t1, 3. Pi, sigma, b, b, upsilon, sigma, t0, t1, 4. Where is the block finalization state transition function, a function that rewards a nominated party? B is this block, which includes a series of transactions amongst some other components, and pi is the block level state transition function. This is the basis of the blockchain paradigm, a model that forms the backbone of not only Ethereum, but all decentralized consensus-based transaction systems to date. 2.1 Value. In order to incentivize computation within the network, there needs to be an agreed method for transmitting value. To address this issue, Ethereum has an intrinsic currency, Ether, known also as ETH and sometimes referred to by the Old English D. The smallest subdenomination of Ether, and thus the one in which all integer values of the currency are counted, is the way. 1 Ether is defined as being 1018 way. There exist other subdenominations of Ether. Multiplier name. 100 way 1012 Sabo 1015 Fini 1018 Ether. Throughout the present work, any reference to value, in the context of Ether, currency, a balance, or a payment, should be assumed to be counted in way. 2.2 Which history? Since the system is decentralist and all parties have an opportunity to create a new block on some older pre-existing block, the resultant structure is necessarily a tree of blocks. In order to form a consensus as to which path, from root, the genesis block, to leaf, the block containing the most recent transactions, through this tree structure, known as the blockchain, there must be an agreed upon scheme. If there is ever a disagreement between nodes as to which route to leaf path down the block tree is the best blockchain, then a fork occurs. This would mean that past a given point in time, block, multiple states of the system may coexist, some nodes believing one block to contain the canonical transactions, other nodes believing some other block to be canonical, potentially containing radically different or incompatible transactions. This is to be avoided at all costs as the uncertainty that would ensue would likely kill all confidence in the entire system. The scheme we use in order to generate consensus is a simplified version of the Ghost protocol introduced by Sompolinsky and Zohar 2013. This process is described in detail in Section 10. Ethereum, a secure decentralist generalist transaction ledger Berlin version 3. Sometimes, a path follows a new protocol from a particular height, block number. This document describes one version of the protocol, namely the Berlin version defined by BICO ETAL 2021b. In order to follow back the history of a path, one must reference multiple versions of this document. Here are the block numbers of protocol updates on the Ethereum main network. Name first block number. F Homestead 115.00000 F Tangerine Whistle 24. Occasionally actors do not agree on a protocol change, and a permanent fork occurs. In order to distinguish between diverged blockchains, EIP 155 by Buterin 2016b introduced the concept of chain ID, which we denote by beta. For the Ethereum main network, 5, beta equals 1. 3 conventions. We use a number of typographical conventions for the formal notation, some of which are quite particular to the present work. The two sets of highly structured, top-level, state values, are denoted with bold lowercase Greek letters. They fall into those of world state, which are denoted sigma, or a variant thereupon, and those of machine state, mu. Functions operating on highly structured values are denoted with an uppercase Greek letter, e.g. upsilon, the Ethereum state transition function. For most functions, an uppercase letter is used, e.g. C, the general cost function. These may be subscripted to denote specialized variants, e.g. XStore, the cost function for the store operation. For specialized and possibly externally defined functions, we may format as typewriter text, e.g. the Cupcake 256 hash function, as per version 3 of the winning entry to the SHA-3 contest by Bertoni ETAL 2011, rather than the final SHA-3 specification, is denoted kek, and generally referred to as plain Cupcake. Also, kek 512 refers to the Cupcake 512 hash function. Tuples are typically denoted with an uppercase letter, e.g. T, is used to denote an Ethereum transaction. This symbol may, if accordingly defined, be subscript to refer to an individual component, e.g. Tn, denotes the nonce of said transaction. The form of the subscript is used to denote its type, e.g. uppercase subscripts refer to tuples with subscriptable components. Scalars in fixed size byte sequences, or, synonymously, arrays, are denoted with a normal lowercase letter, e.g. N is used in the document to denote a transaction nonce. Those with a particularly special meaning may be Greek, e.g. delta, the number of items required on the stack for a given operation. Arbitrary length sequences are typically denoted as a bold lowercase letter, e.g. O is used to denote the byte sequence given as the output data of a message call. For particularly important values, a bold uppercase letter may be used. Throughout, we assume scalars are non-negative integers and thus belong to the set n. The set of all byte sequences is B, formally defined in Appendix B. If such a set of sequences is restricted to those of a particular length, it is denoted with a subscript. Thus the set of all byte sequences of length 32 is named B32 and the set of all non-negative integers smaller than 2256 is named N256. This is formally defined in Section 4.3. Square brackets are used to index and to reference individual components or subsequences of sequences, e.g. mus0 denotes the first item on the machine stack. For subsequences, ellipses are used to specify the intended range, to include elements at both limits, e.g. mu-m031 denotes the first 32 items of the machine's memory. In the case of the global state sigma, which is a sequence of accounts, themselves tuples, the square brackets are used to reference an individual account. When considering variants of existing values, we follow the rule that within a given scope for definition, if we assume that the unmodified input value be denoted by the placeholder, then the modified and utilizable value is denoted as, and intermediate values would be, NC. On very particular occasions, in order to maximize readability and only if unambiguous in meaning, we may use alphanumeric subscripts to denote intermediate values, especially those of particular note. When considering the use of existing functions, given a function f, the function f denotes a similar, element-wise version of the function mapping instead between sequences. It is formally defined in Section 4.3. We define a number of useful functions throughout. One of the more common is, which evaluates to the last item in the given sequence. 6, x, xx1. 4 blocks, state, and transactions. Having introduced the basic concepts behind Ethereum, we will discuss the meaning of a transaction, a block, and the state in more detail. 4.1 World state. The world state, is a mapping between addresses, 160-bit identifiers, and account states, a data structure serialized as RLP, see Appendix B. Though not stored on the blockchain, it is assumed that the implementation will maintain this mapping in a modified Merkle-Patricia tree, see Appendix D. The tree requires a simple database backend that maintains a mapping of byte arrays to byte arrays. We name this underlying database the state database. This has a number of benefits. Firstly, the root node of this structure is cryptographically dependent on all internal data and as such its hash can be used as a secure identity for the entire system state. Secondly, being an immutable data structure, it allows any previous state, whose root hash is known, to be recalled by simply altering the root hash accordingly. Since we store all such root hashes in the blockchain, we are able to trivially revert to old states. Ethereum, a secure decentralized generalist transaction ledger Berlin version 4. The account state, sigma A, comprises the following four fields. Nonce, a scalar value equal to the number of actions sent from this address or, in the case of accounts with associated code, the number of contract creations made by this account. For account of address A and state sigma, this would be formally denoted sigma A and balance, a scalar value equal to the number of way owned by this address. Formally denoted sigma AB. Storage root, a 256-bit hash of the root node of A. Merkle Patricia tree that encodes the storage contents of the account, a mapping between 256-bit integer values, encoded into the tree as a mapping from the cupcake 256-bit hash of the 256-bit integer keys to the RLP encoded 256-bit integer values. The hash is formally denoted sigma AS code hash, the hash of the EVM code of this account. This is the code that gets executed should this address receive a message call. All such code fragments are contained in the state database under their corresponding hashes for later retrieval. This hash is formally denoted sigma AC, and thus the code may be denoted as B, given that kek B equals sigma AC. Since we typically wish to refer not to the tree's root hash but to the underlying set of key/value pairs stored within, we define a convenient equivalence. 7. Tree L I sigma AS. Sigma AS. The collapse function for the set of key/value pairs in the tree, Li, is defined as the element-wise transformation of the base function Li, given as 8 Li K V kek K RLP V, where 9 K set membership symbol B32 V set membership symbol N. It shall be understood that sigma AS is not a physical member of the account and does not contribute to its later serialization. If the code hash field is the cupcake 256 hash of the empty string, i.e. sigma AC equals kek, then the node represents a simple account, sometimes referred to as a non-contract account. Thus we may define a world state collapse function ls 10 ls sigma p a sigma a6 equals where 11 p a kek a RLP sigma an sigma ab sigma as sigma ac. This function ls is used alongside the tree function to provide a short identity hash of the world state. We assume 12 turned a sigma a equals a set membership symbol b20 v sigma a, where v is the account validity function. 13 v x xn set membership symbol n256 x b set membership symbol n256 xs set membership symbol b32 x c set membership symbol b32. An account is empty when it has no code, 0 nonce, and 0 balance. 14 empty sigma a sigma ac equals kek sigma a n equals 0 sigma ab equals 0. Even callable precompiled contracts can have an empty account state. This is because their account states do not usually contain the code describing its behavior. An account is dead when its account state is non-existent or empty. 15 dead sigma a equals empty sigma a. 4.2 The transaction. A transaction, formally, T, is a single cryptographically signed instruction constructed by an actor externally to the scope of Ethereum. The sender of a transaction cannot be a contract. While it is assumed that the ultimate external actor will be human in nature, software tools will be used in its construction and dissemination. 1. EIP 2718 by Zalta 2020 introduced the notion of different transaction types. As of the Berlin version of the protocol, there are 2 transaction types, 0, legacy, and 1, EIP 2930 by Buterin and Swen 2020b. Further, there are 2 subtypes of transactions, those which result in message calls and those which result in the creation of new accounts with associated code, known informally as contract creation. All transaction types specify a number of common fields. Type, EIP 2718 transaction type, formally TX nonce, a scalar value equal to the number of actions sent by the sender, formally TN gas price, a scalar value equal to the number of way to be paid per unit of gas for all computation costs incurred as a result of the execution of this transaction, formally TP. Gas limit, a scalar value equal to the maximum amount of gas that should be used in executing this transaction. This is paid up front, before any computation is done and may not be increased later, formally TG. 2. The 160-bit address of the message calls recipient. And/or, for a contract creation transaction, used here to denote the only member of B0, formally TT. Value, a scalar value equal to the number of way to be transferred to the message calls recipient or, in the case of contract creation, as an endowment to the newly created account, formally TV. R, S, values corresponding to the signature of the transaction and used to determine the sender of the transaction, formally TR and TS. This is expanded in Appendix F. EIP 2930, Type 1, transactions also have access list of access entries to warm up. 4. Malita. Each access list entry E is a tuple of an account address and a list of storage keys, E, EA, ES. Chain ID, formally DC must be equal to the network chain ID beta Y parity, signature Y parity, formally TI. 1. Notably, such tools could ultimately become so causally removed from their human-based initiation or humans may become so causally neutral that there could be a point at which they rightly be considered autonomous agents. E.g. contracts may offer bounties to humans for being sent transactions to initiate their execution. Ethereum, a secure decentralized generalist transaction ledger Berlin version 5. Legacy transactions do not have an access list, TI equals, while chain ID and Y parity for legacy transactions are combined into a single value. W, a scalar value encoding Y parity in posse. Bly chain ID, formally TW equals 27 plus TI or TW equals 2 beta plus 35 plus TI, CEIP 155 by Buterin 2016b. Additionally, a contract creation transaction, regardless whether legacy or EIP 2930, contains in it an unlimited size byte array specifying the EVM code for the account initialization procedure, formally TI. In it is an EVM code fragment. It returns the body, a second fragment of code that executes each time the account receives a message call, either through a transaction or due to the internal execution of code. In it is executed only once at account creation and gets discarded immediately thereafter. In contrast, a message call transaction contains data, an unlimited size byte array specifying the input data of the message call, formally TD. Appendix F specifies the function S, which maps transactions to the sender, and happens through the EXA of the SECP256K1 curve, using the hash of the transaction, accepting the latter 3 signature fields, as the datum to sign. For the present we simply assert that the sender of a given transaction T can be represented with S, T, 16, LT, T, TN, TP, TG, TT, TV, P, TW, TR, TS, if TX equals 0. TC, TN, TP, TG, TT, TV, P, TA, TI, TR, TS, if TX equals 1. Where 17, P, Ti if TT equals TD otherwise. Here, we assume all components are interpreted by the RLP as integer values, with the exception of the access list TI and the arbitrary length byte arrays TI and TD. 18. TX set membership symbol 0, 1 TC equals beta T and set. The address hash TT is slightly different. It is either a 20-byte address hash or, in the case of being a contract creation transaction, and thus formally equal to, it is the RLP empty byte sequence and thus the member of B0. 20. TT set membership symbol. B20 if TT6 equals B0 otherwise. 4.3 The block. The block in Ethereum is the collection of relevant pieces of information, known as the block header, H, together with information corresponding to the comprised transactions, T, and a set of other block headers U that are known to have a parent equal to the present block's parent's parent. Such blocks are known as omers 2. The block header contains several pieces of information. Parent hash, the cupcake 256-bit hash of the parent. Block's header, in its entirety, formerly HP. Omers hash, the cupcake 256-bit hash of the OM. MERS list portion of this block, formerly HO beneficiary, the 160-bit address to which all fees collected from the successful mining of this block be transferred, formerly HC. State root, the cupcake 256-bit hash of the root. Node of the state tree, after all transactions are executed and finalizations applied, formerly HR transactions root, the cupcake 256-bit hash of the root node of the tree structure populated with each transaction in the transactions list portion of the block, formerly HT receipts root, the cupcake 256-bit hash of the root. Node of the tree structure populated with the receipts of each transaction in the transactions list portion of the block, formerly he. Logs Bloom, the Bloom filter composed from index. Able information, logger address and log topics, contained in each log entry from the receipt of each transaction in the transactions list, formerly HB. Difficulty, a scalar value corresponding to the difficulty level of this block. This can be calculated from the previous block's difficulty level and the timestamp, formerly HD. Number, a scalar value equal to the number of ancestor blocks. The Genesis block has a number of 0, formerly high. Gas limit, a scalar value equal to the current limit of gas expenditure per block, formerly HL gas used, a scalar value equal to the total gas used. In transactions in this block, formerly HG timestamp, a scalar value equal to the reasonable output of Unix's time, at this block's inception, formerly HS extra data, an arbitrary byte array containing data relevant to this block. This must be 32 bytes or fewer, formerly HX. Mix hash, a 256-bit hash which, combined with the nonce, proves that a sufficient amount of computation has been carried out on this block, formerly whom. Nonce, a 64-bit value which, combined with the mix hash, proves that a sufficient amount of computation has been carried out on this block, formerly HN. The other two components in the block are simply a list of Omer block headers, of the same format as above, bulleted in a series of the transactions, BT. Formally, we can refer to a block B. 21, B, BH, BT, bulletin. 2 Omer is a gender-neutral term to mean, sibling of parent, chttps://nonbinary.miraes.org/wiki/gender_neutral transaction receipt. In order to encode information about a transaction concerning which it may be useful to form a zero-knowledge proof, or index, and search, we encode a receipt of each transaction containing certain information from its execution. Each receipt, denoted BRI for the ith transaction, is placed in an index-keyed tree and the root recorded in the header as he. The transaction receipt, R, is a tuple of 5 items comprising the type of the transaction, RX, the status code of the transaction, RZ, the cumulative gas used in the block containing the transaction receipt as of immediately after the transaction has happened, RU, the set of logs created through execution of the transaction, RL, and the Bloom filter composed from information in those logs, RB. 22, R, RX, RZ, RU, RB, RL. RX is equal to the type of the corresponding transaction. The function LR prepares a transaction receipt for being transformed into an RLP serialist byte array. 23, LR, R, RZ, RU, RB, RL. We assert that the status code RZ is a non-negative integer. 24, RZ set membership symbol N. We assert that RU, the cumulative gas used, is a non-negative integer and that the logs Bloom, RB, is a hash of size 2048 bits, 256 bytes. 25, RU set membership symbol N, RB set membership symbol B256. The sequence RL is a series of log entries, 00, 01. A log entry, O, is a tuple of the logger's address, OA, a possibly empty series of 32-byte log topics, OT, and some number of bytes of data, OD. 26, O, OA, OT0, OT1, OD. 27, OA set membership symbol B20 turned to X set membership symbol OT, X set membership symbol B32 OD set membership symbol B. We define the Bloom filter function, M, to reduce a log entry into a single 256-byte hash. 28, M, O. X set membership symbol OA union set symbol OT. M3:2048, X. Where M3:2048 is a specialized Bloom filter that sets 3 bits out of 2048, given an arbitrary byte sequence. It does this through taking the low order 11 bits of each of the first 3 pairs of bytes in a cupcake 256 hash of the byte sequence .3 formally. M3:2048, X, X set membership symbol B, Y, Y set membership symbol B256 where 29. Y equals 0, 0, 0, except 30. Turned AI set membership symbol 0, 2, 4, B2047M, XI, where B is the bit reference function such that BJ, X, equals the bit of index J, indexed from 0, in the byte array X notably, it treats X as big endian, more significant bits will have smaller indices. 4.3.2 Holistic validity. We can assert a block's validity if and only if it satisfies several conditions. It must be internally consistent with the Omer and transaction block hashes and the given transactions BT, as specified in SEC 11, when executed in order on the base state sigma, derived from the final state of the parent block, result in a new state of the identity HR. 33, HR tree, LS, pi, sigma, B. Hokek, RLP, LH, bulletin, HT tree, turned AI. HB. R set membership symbol BR. RB. Where PT, K, V, and PR, K, V, are pairwise RLP transformations, but with a special treatment for EIP 2718 transactions. 34. PT, K, T, R is the concatenation of byte arrays. Furthermore. 36. Thus tree, LS, sigma, is the root node hash of the Merkle-Patricia tree structure containing the key value pairs of the state sigma with values encoded using RLP, and P, BH, is the parent block of B, defined directly. The values stemming from the computation of transactions, specifically the transaction receipts, BR, and that defined through the transaction state accumulation function, pi, are formalized later in section 11.4. 4.3.3 Serialization. The function LB and LH are the preparation functions for a block and block header respectively. We assert the types and order of the structure for when the RLP transformation is required. LH, H, HP, HO, HC, HR, HT, He, HB, HD. Hi. Takes a special care of EIP 2718 transaction. And LH being element-wise sequence transformations, thus 40, F, X0, X1. The component types are defined thus. 41, HP. We now have a rigorous specification for the construction of a formal block structure. The RLP function RLP, see Appendix B, provides the canonical method for forming this structure into a sequence of bytes ready for transmission over the wire or storage locally. 4.3.4 block header validity. We define P, BH, to be the parent block of B, formally. The canonical difficulty of a block of header H is defined as D, H, 45, D, H, 234 if high equals 0 max. The Homestead difficulty parameter, 2, is used to affect a dynamic homeostasis of time between blocks, as the time between blocks varies, as discussed below, as implemented in EIP2 by Buter in 2015. In the Homestead release, the exponential difficulty symbol causes the difficulty to slowly increase every 100,000 blocks at an exponential rate, and thus increasing the block time difference, and putting time pressure on transitioning to proof of stake. This effect, known as the difficulty bomb, or ice age, was explained in EIP 649 by Skoeden and Buter in 2017, and delayed and implemented earlier in EIP2. 2 was also modified in EIP 100 with the use of X, the adjustment factor above, and the denominator 9, in order to target the mean block time including Uncle blocks by Buter in 2016a. In the Byzantium release, with EIP 649, the ice age was delayed by creating a fake block number, HI, which is obtained by subtracting 3 million from the actual block number, which in other words reduced in the time difference between blocks, in order to allow more time to develop proof of stake and preventing the network from freezing up. Subsequently, EIP 1234 by Skoeden. 2018, EIP 23. HS is the timestamp, and Unix is time, of block H and this mechanism enforces a homeostasis in terms of the time between blocks. A smaller period between the last two blocks results in an increase in the difficulty level and thus additional computation required, lengthening the likely next period. Conversely, if the period is too large, the difficulty, and expected time to the next block, with n, m, equals pow, hn, d, where hn is the new block's header h, but without the nonce and mix hash components, d being the current DAG. A large data set needed to compute the mix hash, and pow is the proof of work function. See section 11.5. This evaluates to an array with the first item being the mix hash, to prove that a correct DAG has been used, and the second item being a pseudo-random number cryptographically dependent on h and d. Given an approximately uniform distribution in the range 0, 264, the expected time to find a solution is proportional to the difficulty, HD. This is the foundation of the security of the blockchain, and is the fundamental reason why a malicious node can not propagate newly created blocks that would otherwise overwrite, rewrite, history. Because the nonce must satisfy this requirement, and because its satisfaction depends on the contents of the block and in turn its composed transactions, creating new, valid, blocks is difficult and Ethereum, a security centralist generalist transaction ledger Berlin version 8. Over time, requires approximately the total compute power of the trustworthy portion of the mining peers. Thus we are able to define the block header validity function v, h, where n, m, equals pow, hn, d. Noting additionally that extra data must be at most 32 bytes. 5 gas and payment. In order to avoid issues of network abuse and to sidestep the inevitable questions stemming from Turing completeness, all programmable computation in Ethereum is subject to fees. The fee schedule is specified in units of gas. See Appendix G for the fees associated with various computation. Thus any given fragment of programmable computation, this includes creating contracts, making message calls, utilizing and accessing account storage and executing operations on the virtual machine, has a universally agreed cost in terms of gas. Every transaction has a specific amount of gas associated with it, gas limit. This is the amount of gas which is implicitly purchased from the sender's account balance. The purchase happens at the according gas price, also specified in the transaction. The transaction is considered invalid if the account balance cannot support such a purchase. It is named gas limit since any unused gas at the end of the transaction is refunded, at the same rate of purchase, to the sender's account. Gas does not exist outside of the execution of a transaction. Thus for accounts with trusted code associated, a relatively high gas limit may be set and left alone. In general, ether used to purchase gas that is not refunded is delivered to the beneficiary address, the address of an account typically under the control of the miner. Transactors are free to specify any gas price that they wish, however miners are free to ignore transactions as they choose. A higher gas price on a transaction will therefore cost the sender more in terms of ether and deliver a greater value to the miner and thus will more likely be selected for inclusion by more miners. Miners, in general, will choose to advertise the minimum gas price for which they will execute transactions and transactors will be free to canvass these prices in determining what gas price to offer. Since there will be a weighted distribution of minimum acceptable gas prices, transactors will necessarily have a trade-off to make between lowering the gas price and maximizing the chance that their transaction will be mined in a timely manner. 6. Transaction execution. The execution of a transaction is the most complex part of the Ethereum protocol. It defines the state transition function upsilon. It is assumed that any transactions executed first pass the initial tests of intrinsic validity. These include 1. The transaction is well-formed RLP, with no additional trailing bytes. 2. The transaction signature is valid. 3. The transaction nonce is valid, equivalent to the sender account's current nonce. 4. The sender account has no contract code deployed. See EIP 3607 by Feist ETAL 2021. 5. The gas limit is no smaller than the intrinsic gas. G0, used by the transaction, and 6. The sender account balance contains at least the cost, V0, required in upfront payment. Formally, we consider the function upsilon, with t being a transaction and sigma the state. 57. Sigma equals upsilon, sigma, t. Thus sigma is the post-transactional state. We also define upsilon g to evaluate to the amount of gas used in the execution of a transaction, upsilon l to evaluate to the transaction's accrued log items, and upsilon z to evaluate to the status code resulting from the transaction. These will be formally defined later. 6.1 Substate. Throughout transaction execution, we accrue certain information that is acted upon immediately following the transaction. We call this the accrued transaction substate, or accrued substate for short, and represent it as A, which is a tuple. 58. A, as. The tuple contents include as, the self-destruct set, a set of accounts that will be discarded following the transaction's completion. Al is the log series. This is a series of archived and indexable checkpoints in VM code execution that allow for contract calls to be easily tracked by onlookers external to the Ethereum world, such as decentralized application front ends. Ed is the set of touched accounts, of which the empty ones are deleted at the end of a transaction. AR is the refund balance, increased through using the store instruction in order to reset contract storage to 0 from some non-zero value. Though not immediately refunded, it is allowed to partially offset the total execution costs. Finally, EIP 2929 by Buterin and Swen 2020 introduced AA, the set of accessed account addresses, and AK, the set of accessed storage keys. More accurately, each element of AK is a tuple of a 20-byte account address in a 32-byte storage slot. We define the empty accrued substate A0 to have no self-destructs, no logs, no touched accounts, 0 refund balance, all precompiled contracts in the accessed addresses, and no accessed storage. 59. A0, 0, pi. Where pi is the set of all precompiled addresses. Ethereum, a secure decentralized generalist transaction ledger Berlin version 9. 6.2 Execution. We define intrinsic gas G0, the amount of gas this transaction requires to be paid prior to execution. Where TD means the series of bytes of the transaction's associated data and initialization EVM code, depending on whether the transaction is for contract creation or message call. Create is added if the transaction is contract creating, but not if a result of EVM code. Gauch list address and Gauch list storage are the costs of warming up account and storage access, respectively. G is fully defined in Appendix G. The upfront cost V0 is calculated as 61 V0 TGTP plus TV. The validity is determined as 62 S T 6 equals sigma S T C equals. Note the final condition, the sum of the transaction's gas limit, TG, and the gas utilized in this block prior, given by BR, U, must be no greater than the block's gas limit, BHL. Also, with a slight abuse of notation, we assume that sigma S, T, C equals. The execution of a valid transaction begins with an irrevocable change made to the state. The nonce of the account of the sender, S, T, is incremented by 1 and the balance is reduced by part of the upfront cost, TGTP. The gas available for the preceding computation, G, is defined as TGG0. The computation, whether contract creation or a message call, results in an eventual state, which may legally be equivalent to the current state, the change to which is deterministic and never invalid. There can be no invalid transactions from this point. We define the checkpoint state sigma 0. Sigma 0 sigma except 63. Evaluating sigma p from sigma 0 depends on the transaction type, either contract creation or message call. We define the tuple of post-execution provisional state sigma p, remaining gas G. Accrued substate A and status code Z, 66. Sigma p, G, A, Z. Lambda 4, sigma 0, A, S, T, S. And G is the amount of gas remaining after deducting the basic amount required to pay for the existence of the transaction. 70, GTGG0. Note we use theta 4 and lambda 4 to denote the fact that only the first 4 components of the function's values are taken. The final represents the message call's output value, a byte array, and is unused in the context of transaction evaluation. After the message call or contract creation is processed, the refund counter has to be incremented for the accounts that were self-destruct throughout its invocation. 71, ARAR plus. Sigma. I set membership symbol as. Then the state is finalized by determining the amount to be refunded, G from the remaining gas, G, plus some allowance from the refund counter, to the total refundable amount is the legitimately remaining gas G, added to AR, with the latter component being capped up to a maximum of half, rounded down, of the total amount used TGG. Therefore, G is the total gas that remains after the transaction has been executed. The ether for the gas is given to the miner, whose address is specified as the beneficiary of the present block B. So we define the pre-final state sigma in terms of the provisional state sigma P. Sigma P. The final state, sigma, is reached after deleting all accounts that either appear. And finally, we specify upsilon G, the total gas used in this transaction upsilon L, the logs created by this transaction and Ethereum, a secure decentralized generalist. Upsilon Z, the status code of this transaction. Upsilon G, sigma, T. These are used to help define the transaction receipt and are also used later for state and nonce validation. 7 Contract creation. There are a number of intrinsic parameters used when creating an account. Sender, S, original transactor 4, O, available gas, G, gas price, P, endowment, V, together with an arbitrary length byte array, I, the initialization EVM code, the present depth of the message call / contract creation stack, E, the salt for new account's address, zeta, and finally the permission to make modifications to the state, W. The salt zeta might be missing, zeta equals, formally, 83, zeta set membership symbol B32 union set symbol B0. If the creation was caused by create2, then zeta 6 equals. We define the creation function formally as the function lambda, which evaluates from these values, together with the state sigma and the accrued substate A, to the tuple containing the new state, remaining gas, new accrued substate, status code, and output, sigma, G, Z, O. 84, sigma, G, Z. The address of the new account is defined as being the rightmost 160 bits of the CUCK256 hash of the RLP encoding of the structure containing only the sender and the account nonce. For create2 the rule is different and is described in EIP 1014 by Buterin 2018. Combining the two cases, we define the resultant address for the new account A address, where is the concatenation of byte arrays, BAB, X, evaluates to a binary value containing the bits of indices in the range A, B of the binary data X, and sigma X is the address state of X, or if none exists. Note we use one fewer than the sender's nonce value. We assert that we have incremented the sender account's nonce prior to this call, and so the value used is the sender's nonce at the beginning of the responsible transaction or VM operation. The address of the new account is added to the set of accessed accounts. 88, AAA except AAA union set symbol A. The account's nonce is initially defined as 1, the balance is the value passed, the storage is empty and the code hash is the cupcake 256-bit hash of the empty string. The sender's balance is also reduced by the value passed. Thus the mutated state becomes sigma 89, sigma sigma except sigma A equals 1, V plus V, tree, kick, 90, sigma S. Finally, the account is initialized through the execution of the initializing EVM code I according to the execution model, see section 9. Code execution can affect several events that are not internal to the execution state. The account's storage can be altered, further accounts can be created and further message calls can be made. As such, the code execution function psi evaluates to a tuple of the resultant state sigma, available gas remaining G, the resultant accrued substate A and the body code of the account O. 94, sigma, G, A, O. IH has no special treatment and is determined from the blockchain. Code execution depletes gas, and gas may not go below 0, thus execution may exit before the code has come to a natural halting state. In this, and several other, exceptional cases we say an out of gas, OOG, exception has occurred. The evaluated state is defined as being the empty set, and the entire create operation should have no effect on the state, effectively leaving it as it was immediately prior to attempting the creation. If the initialization code completes successfully, a final contract creation cost is paid, the code deposit cost, C, proportional to the size of. If there is not enough gas remaining to pay this, i.e. If the creation was conducted as the reception of a transaction, then this doesn't affect payment of the intrinsic cost of contract creation, it is paid regardless. However, the value of the transaction is not transferred, for which can differ from the sender in the case of a message call or contract creation not directly triggered by a transaction but coming from the execution of EVM code. Ethereum, a secure decentralized generalist transaction ledger to the aborted contract's address when we are out of gas, thus the contract's code is not stored. If such an exception does not occur, then the remaining gas is refunded to the originator and the now altered state is allowed to persist. Thus formally, we may specify the resultant state, gas, accrued substate, and the exception in the determination of sigma dictates that O, the resultant byte sequence from the execution of the initialization code, specifies the final body code for the newly created account. Note that intention is that the result is either a successfully created new contract with its endowment, or no new contract with no transfer of value. In addition, observe that if the execution of the initializing code reverts, sigma equals 06 equals, the resultant gas G is not depleted, provided there was no other exception, but no new account is created. 7.1 Subtleties. Note that while the initialization code is executing, the newly created address exists but with no intrinsic body code 5. Thus any message call received by it during this time causes no code to be executed. If the initialization execution ends with a self-destruct instruction, the matter is moot since the account will be deleted before the transaction is completed. For a normal stop code, or if the code returned is otherwise empty, then the state is left with a zombie account, and any remaining balance will be locked into the account forever. 8 Message call. In the case of executing a message call, several parameters are required: sender, S, transaction originator, O, recipient, R, the account whose code is to be executed, C, usually the same as recipient, available gas, G, value, V, and gas price, P, together with an arbitrary length byte array, D, the input data of the call, the present depth of the message call / contract creation stack, E, and finally the permission to make modifications to the state, W. Aside from evaluating to a new state and accrued transaction substate, message calls also have an extra component, the output data denoted by the byte array O. This is ignored when executing transactions. However, message calls can be initiated due to VM code execution, and in this case note that we need to differentiate between the value that is to be transferred, V, from the value apparent in the execution context, V, for the delegate call instruction. We define sigma 1, the first transitional state, as the original state but with the value transferred from sender to recipient. Throughout the present work, it is assumed that if sigma 1R was originally undefined, it will be created as an account with no code or state and zero balance in nonce. Thus the previous equation should be taken. The account's associated code, identified as the fragment whose cupcake 256 hash is sigma cc, is executed according to the execution model, see section 9. Just as with contract creation, if the execution halts in an exceptional fashion, i.e. due to an exhausted gas supply, stack underflow, invalid jump destination or invalid instruction, then no gas is refunded to the caller and the state is reverted to the point immediately prior to balance transfer, i.e. sigma 5 during initialization code execution, ext code size on the address should return 0, which is the length of the code of the account, while code size should. It is assumed that the client will have stored the pair, kek, IB, at some point prior in order to make the determination of IB feasible. As can be seen, there are 9 exceptions to the usage of the general execution framework psi for evaluation of the message call. These are so-called precompiled contracts, meant as a preliminary piece of architecture that may later become native extensions. The contracts in addresses 1 to 9 execute the elliptic curve public key recovery function, the SHA-2 256-bit hash scheme, the RIPAMD 160-bit hash scheme, the identity function, arbitrary precision modular exponentiation, elliptic curve addition, elliptic curve scalar multiplication, an elliptic curve pairing check, and the Blake 2 compression function F respectively. Their full formal definition is in Appendix E. We denote the set of the addresses of the precompiled contracts by pi. 133. The execution model specifies how the system state is altered given a series of bytecode instructions and a small tuple of environmental data. This is specified through a formal model of a virtual state machine, known as the Ethereum Virtual Machine, EVM. It is a quasi-Turing complete machine. The quasi-qualification comes from the fact that the computation is intrinsically bounded through a parameter, gas, which limits the total amount of computation done. 9.1 Basics. The EVM is a simple stack-based architecture. The word size of the machine, and thus size of stack items, is 256-bit. This was chosen to facilitate the cupcake 256 hash scheme and elliptic curve computations. The memory model is a simple word-addressed byte array. The stack has a maximum size of 1024. The machine also has an independent storage model. This is similar in concept to the memory, but rather than a byte array, it is a word-addressable word array. Unlike memory, which is volatile, storage is non-volatile and is maintained as part of the system state. All locations in both storage and memory are well defined initially as 0. The machine does not follow the standard von Neumann architecture. Rather than storing program code in generally accessible memory or storage, it is stored separately in a virtual ROM interactable only through a specialized instruction. The machine can have exceptional execution for several reasons, including stack underflows and invalid instructions. Like the out-of-gas exception, they do not leave state changes intact. Rather, the machine halts immediately and reports the issue to the execution agent, either the transaction processor or, recursively, the spawning execution environment, which will deal with it separately. 9.2 Fees Overview. Fees, denominated in gas, are charged under 3 distinct circumstances, all 3 as prerequisite to the execution of an operation. The first and most common is the fee intrinsic to the computation of the operation, see Appendix G. Secondly, gas may be deducted in order to form the payment for a subordinate message call or contract creation. This forms part of the payment for create to, call and call code. Finally, gas may be paid due to an increase in the usage of the memory. Over an account's execution, the total fee for memory usage payable is proportional to smallest multiple of 32 bytes that are required such that all memory indices, whether for read or write, are included in the range. This is paid for on a just-in-time basis. As such, referencing an area of memory at least 32 bytes greater than any previously indexed memory will certainly result in an additional memory usage fee. Due to this fee, it is highly unlikely addresses will ever go above 32-bit bounds. That said, implementations must be able to manage this eventuality. Storage fees have a slightly nuanced behavior to incentivize minimization of the use of storage, which corresponds directly to a larger state database on all nodes. The execution fee for an operation that clears an entry in the storage is not only waived, a qualified refund is given. In fact, this refund is effectively paid upfront since the initial usage of a storage location costs substantially more than normal usage. See Appendix H for a rigorous definition of the EVM gas cost. Ethereum, a secure decentralized generalist transaction ledger Berlin version 13. 9.3 Execution environment. In addition to the system state sigma, the remaining gas for computation G, and the accrued substate A, there are several pieces of important information used in the execution environment that the execution agent must provide. These are contained in the tuple I. IA, the address of the account which owns the code that is executing. IO, the sender address of the transaction that orig. In this execution. IP, the price of gas in the transaction that origi. Nate this execution. ID, the byte array that is the input data to this execution. If the execution agent is a transaction, this would be the transaction data. Is, the address of the account which caused the code to be executing. If the execution agent is a transaction, this would be the transaction sender. 4. The value, in way, passed to this account as part of the same procedure as execution. If the execution agent is a transaction, this would be the transaction value. IB, the byte array that is the machine code to be executed. IH, the block header of the present block, i.e., the depth of the present message call or contract creation, i.e., the number of calls or create, s being executed at present. IW, the permission to make modifications to the state. The execution model defines the function psi, which can compute the resultant state sigma, the remaining gas G, the resultant accrued substata and the resultant output, O, given these definitions. For the present context, we will define it as 134, sigma, G, O, psi, sigma, G, A, I. Execution overview. We must now define the psi function. In most practical implementations this will be modeled as an iterative progression of the pair comprising the full system state, sigma, and the machine state, mu. Formally, we define it recursively with the function x. This uses an iterator function O, which defines the result of a single cycle of the state machine, together with function z which determines if the present state is an exceptional halting state of the machine and h, specifying the output data of the instruction if and only if the present state is a normal halting state of the machine. The empty sequence, denoted, is not equal to the empty set, denoted. This is important when interpreting the output of h, which evaluates to when execution is to continue but a series, potentially empty, when execution should halt. Psi, sigma, G, A, I. Note that, when we evaluate psi, we drop the fourth element I and extract the remaining gas mu G from the resultant machine state mu. X is thus cycled, recursively here, but implementations are generally expected to use a simple iterative loop, until either Z becomes true indicating that the present state is exceptional and that the machine must be halted and any changes discarded or until H becomes a series, rather than the empty set, indicating that the machine has reached a controlled halt. 9.4.1 Machine state. The machine state mu is defined as the tuple, G, PC, M, I, S, which are the gas available, the program counter PC set membership symbol N256, the memory contents, the active number of words in memory, counting continuously from position 0, and the stack contents. The memory contents mu m are a series of zeros of size 2256. For the ease of reading, the instruction mnemonics, written in small caps, e.g. add, should be interpreted as their numeric equivalents. The full table of instructions and their specifics is given in Appendix H. For the purposes of defining Z, H, and O, we define W as the current operation to be executed. 148. We also assume the fixed amounts of delta and alpha, specifying the stack items removed and added, both subscriptable on the instruction and an instruction cost function C evaluating to the full cost, in gas, of executing the given instruction. Ethereum, a secure decentralized generalist transaction ledger Berlin version 14. This states that the execution is in an exceptional halting state if there is insufficient gas, if the instruction is invalid, and therefore its delta subscript is undefined, if there are insufficient stack items, if a jump/jumpy destination is invalid, the new stack size would be larger than 1024 or state modification is attempted during a static call. The astute reader will realize that this implies that no instruction can, through its execution, cause an exceptional halt. Also, the execution is in an exceptional halting state if the gas left prior to executing unstore instruction is less than or equal to the call stipend. See EIP 2200 by Tang 2019 for more information. 9.4.3 Jump destination validity. We previously used D as the function to determine the set of valid jump destinations given the code that is being run. We define this as any position in the code occupied by a jump dest instruction. All such positions must be on valid instruction boundaries, rather than sitting in the data portion of push operations and must appear within the explicitly defined portion of the code, rather than in the implicitly defined stop operations that trail it. Where n is the next valid instruction position in the code, skipping the data of a push instruction, if any. 153. N, I, W. I plus W push 1 plus 2. If W set membership symbol push. Normal halting. The normal halting function H is defined. The data returning halt operations, return, and revert, have a special function return. Note also the difference between the empty sequence and the empty set as discussed here. 9.5 The execution cycle. Stack items are added or removed from the leftmost, lower indexed portion of the series. All other items remain unchanged. O, sigma. The gas is reduced by the instruction's gas cost and for most instructions, the program counter increments on each cycle. For the 3 exceptions, we assume a function J, subscript by one of 2 instructions, which evaluates to the according value. In general, we assume the memory, accrued substate, and system. However, instructions do typically alter one or several components of these values. Altered components listed by instruction are noted in Appendix H, alongside values for alpha and delta and a formal description of the gas requirements. 10. Block tree to blockchain. The canonical blockchain is a path from root to leaf through the entire block tree. In order to have consensus over which path it is, conceptually we identify the path that has had the most computation done upon it, or the heaviest path. Clearly, one factor that helps determine the heaviest path is the block number of the leaf, equivalent to the number of blocks, not counting the unmined genesis block, in the path. The longer the path, the greater the total mining effort that must have been done in order to arrive at the leaf. This is akin to existing schemes, such as that employed in Bitcoin-derived protocols. Since a block header includes the difficulty, the header alone is enough to validate the computation done. Any block contributes toward the total computation or total difficulty of a chain. Ethereum, a secure decentralized generalist transaction ledger. Thus we define the total. As such, given a block B, BT is its total difficulty, B is its parent block and BD is its difficulty. 11. Block finalization. The process of finalizing a block involves 4 stages. 1. Validate, or, if mining, determine, omers. 2. Validate, or, if mining, determine, transactions. 3. Apply rewards. 4. Verify, or, if mining, compute a valid, state and block nonce. 11.1 Omer validation. The validation of Omer headers means nothing more than verifying that each Omer header is both a valid header and satisfies the relation of nth generation Omer to the present block where n less than or equal to 6. The maximum of Omer headers is 2. Formally, 100. The given gas used must correspond faithfully to the transactions listed, BHG. The total gas used in the block must be equal to the accumulated gas used according to the final reward application. The application of rewards to a block involves raising the balance of the accounts of the beneficiary address of the block in each Omer by a certain amount. We raise the block's beneficiary account by block. For each Omer, we raise the block's beneficiary by an additional 132 of the block. If there are collisions of the beneficiary addresses between Omers and the block, i.e. 2 Omers with the same beneficiary address or an Omer with the same beneficiary address as the present block, additions are applied cumulatively. State and nonce validation. We may now define the function, gamma, that maps a block B to its initiation. Here, tree, ls, sigma I, means the hash of the root node of a tree of state sigma I. It is assumed that implementations will store this in the state database, which is trivial and efficient since the tree is by nature an immutable data structure. And finally we define phi, the block transition function, which maps an incomplete block B to a complete block B. With D being a data set as specified in Appendix J. As specified at the beginning of the present work, pi is the state transition function, which is defined in terms of the block finalization function and upsilon, the transaction evaluation function, both now well defined. As previously detailed, RNZ, RNL and RNU are the nth corresponding status code, logs and cumulative gas used after each transaction. RNB, the fourth component in the tuple, has already been defined in terms of the logs. We also define the nth state sigma n, which is defined simply as the state resulting from applying the corresponding transaction to the state resulting from the previous transaction, or the block's initial state in the case of the first such transaction. In the case of BRNU, we take a similar approach defining each item as the gas used in evaluating the corresponding transactions. Finally, we define pi as the new state given the block reward function applied to the final transaction's resultant state, sigma 1. Thus the complete block transition mechanism is defined, except for POW, the proof of work function. 11.5 Mining proof of work. The mining proof of work, POW, exists as a cryptographically secure nonce that proves beyond reasonable doubt that a particular amount of computation has been expended in the determination of some token value n. It is utilized to enforce the blockchain security by giving meaning and credence to the notion of difficulty, and, by extension, total difficulty. However, since mining new blocks comes with an attached reward, the proof of work not only functions as a method of securing confidence that the blockchain will remain canonical into the future, but also as a wealth distribution mechanism. For both reasons, there are two important goals of the proof of work function. Firstly, it should be as accessible as possible to as many people as possible. The requirement of, or reward from, specialized and uncommon hardware should be minimized. This makes the distribution model as open as possible, and, ideally, makes the act of mining a simple swap from electricity to ether at roughly the same rate for anyone around the world. Secondly, it should not be possible to make superlinear profits, and especially not so with a high initial barrier. Such a mechanism allows a well-funded adversary to gain a troublesome amount of the network's total mining power and as such gives them a superlinear reward, thus skewing distribution in their favor, as well as reducing the network security. One plague of the Bitcoin world is ASICs. These are specialized pieces of compute hardware that exist only to do a single task. Smith 1997. In Bitcoin's case the task is the SHA-256 hash function, Courtois et al. 2014. While ASICs exist for a proof of work function, both goals are placed in jeopardy. Because of this, a proof of work function that is ASIC resistant, i.e. difficult or economically inefficient to implement in specialized compute hardware, has been identified as the proverbial silver bullet. Two directions exist for ASIC resistance. Firstly, make it sequential memory hard, i.e. engineer the function such that the determination of the nonce requires a lot of memory and bandwidth such that the memory cannot be used in parallel to discover multiple nonces simultaneously. The second is to make the type of computation it would need to do general purpose. The meaning of specialized hardware for a general purpose task set is, naturally, general purpose hardware, and as such commodity desktop computers are likely to be pretty close to specialized hardware for the task. For Ethereum 1.0 we have chosen the first path. More formally, the proof of work function takes the form of POW, 1, where HN is the new block's header but without the nonce and mix hash components. HN is the nonce of the header. D is a large data set needed to compute the mix hash, and HD is the new block's difficulty value, i.e. the block difficulty from section 10. POW is the proof of work function which evaluates to an array with the first item being the mix hash and the second item being a pseudo-random number cryptographically dependent on H and D. The underlying algorithm is called Ethish and is described below. 1.5.1 Ethish. Ethish is the POW algorithm for Ethereum 1.0. It is the latest version of Dagger Hashimoto, introduced by Buter in 2013 and Drija 2014, although it can no longer appropriately be called that since many of the original features of both algorithms were drastically changed with RND from February 2015 until May 4, 2015, Yench 2015. The general route that the algorithm takes is as follows. There exists a seed which can be computed for each block by scanning through the block headers up until that point. From the seed, one can compute a pseudo-random cache, Jcache in bytes in initial size. Like clients store the cache. From the cache, we can generate a dataset, JDataset in bytes in initial size, with the property that each item in the dataset depends on only a small number of items from the cache. Full clients and miners store the dataset. The dataset grows linearly with time. Mining involves grabbing random slices of the dataset and hashing them together. Verification can be done with low memory by using the cache to regenerate the specific pieces of the dataset that you need, so you only need to store the cache. The large dataset is updated once every JPEG blocks, so the vast majority of a miner's effort will be reading the dataset, not making changes to it. The mentioned parameters as well as the algorithm is explained in detail in Appendix J12. Implementing contracts. There are several patterns of contracts engineering that allow particular useful behaviors. Two of these that we will briefly discuss are data feeds and random numbers. 12.1 Data feeds. A data feed contract is one which provides a single service. It gives access to information from the external world within Ethereum. The accuracy and timeliness of this information is not guaranteed, and it is the task of a secondary contract author, the contract that utilizes the data feed, to determine how much trust can be placed in any single data feed. The general pattern involves a single contract within Ethereum which, when given a message call, replies with some timely information concerning an external phenomenon. An example might be the local temperature of New York City. This would be implemented as a contract that returned that value of some known point in storage. Of course, this point in storage must be maintained with the correct such temperature, and thus the second part of the pattern would be for an external server to run an Ethereum node, and immediately on discovery of a new block, creates a new valid transaction, sent to the contract, updating said value in storage. The contract's code would accept such updates only from the identity contained on said server. 12.2 Random numbers. Providing random numbers within a deterministic system is, naturally, an impossible task. However, we can approximate with pseudo-random numbers by utilizing data which is generally unknowable. Ethereum. At the time of transacting. Such data might include the block's hash, the block's timestamp, and the block's beneficiary address. In order to make it hard for malicious miners to control those values, one should use the block hash operation in order to use hashes of the previous 256 blocks as pseudo-random numbers. For a series of such numbers, a trivial solution would be to add some constant amount in hashing the result. 13 Future directions. The state database won't be forced to maintain all past state tree structures into the future. It should maintain an age for each node and eventually discard nodes that are neither recent enough nor checkpoints. Checkpoints, or a set of nodes in the database that allow a particular block's state tree to be traversed, could be used to place a maximum limit on the amount of computation needed in order to retrieve any state throughout the blockchain. Blockchain consolidation could be used in order to reduce the amount of blocks a client would need to download to act as a full mining node. A compressed archive of the tree structure at given points in time, perhaps one in every 10,000th block, could be maintained by the peer network, effectively recasting the genesis block. This would reduce the amount to be downloaded to a single archive plus a hard maximum limit of blocks. Finally, blockchain compression could perhaps be conducted. Nodes in state tree that haven't sent/received a transaction in some constant amount of blocks could be thrown out, reducing both ether leakage and the growth of the state database. 13.1 Scalability. Scalability remains an eternal concern. With a general least state transition function, it becomes difficult to partition and parallelize transactions to apply the divide and conquer strategy. Unaddressed, the dynamic value range of the system remains essentially fixed, and as the average transaction value increases, the less valuable of them become ignored, being economically pointless to include in the main ledger. However, several strategies exist that may potentially be exploited to provide a considerably more scalable protocol. Some form of hierarchical structure, achieved by either consolidating smaller lighter weight chains into the main block or building the main block through the incremental combination and adhesion, through proof of work, of smaller transaction sets, may allow parallelization of transaction combination and block building. Parallelism could also come from a priorithized set of parallel blockchains, consolidating each block and with duplicate or invalid transactions thrown out accordingly. Finally, verifiable computation, if made generally available and efficient enough, may provide a route to allow the proof of work to be the verification of final state. 14 Conclusion. We have introduced, discussed, and formally defined the protocol of Ethereum. Through this protocol, the reader may implement a node on the Ethereum network and join others in a decentralized, secure social operating system. Contracts may be authored in order to algorithmically specify and autonomously enforce rules of interaction. 15 Acknowledgements. Many thanks to Aaron Buchanan for authoring the Homestead revisions, Christoph Jentsch for authoring the Ethish algorithm, and Yoichi Hirei for doing most of the EIP 150 changes. Important maintenance, useful corrections, and suggestions were provided by a number of others from the Ethereum dev organization and Ethereum community at large, including Gustav Simonsen, Powell Bilica, Yuta Steiner, Nick Savers, Victor Tiaron, Marco Simovic, Giacomo Tazzari, and, of course, Vitalik Buterin. 16 Availability. The source of this paper is maintained at https://github.com/ethereum/yellowpaper/. An auto-generated PDF is located at https://e3um.github. io/yellowpaper/paper.pdf. References. Jacob Aaron. Bitcoin software finds new life. New Scientist. 213, 284720, 2012. URL http://www.science.direct.com/science/article/pi/s0262407912601055. Adam Back. Hashcash, amortizable publicly auditable. Cost functions, 2002. URL http://www.hashcash.org/papers/amortizable.pdf. Tim Byko, James Hancock.
I'm going to stop here. And probably, I'm not sure if I'm gonna read anymore. I'm tired. So I'm gonna take a break and I will see. If I don't read, then I'm probably gonna start tomorrow streaming, reading this stuff here. So the ones that are left are these ones, these three, I think, that I have to read. Then after I read these ones, then I'm going to do these articles here, I think. I'm gonna finish the MEV first, and the MEV article, and the proposer builder separation, which is gonna be very simplified. And then after I finish this shoe, then I'll work on these other ones and any other ones that come up along the way, I think. So yeah, so probably come back tomorrow. And then if I don't come back tomorrow for whatever reason, then very likely 2 days from now, come back.